let me know if visual and audio coming through. Audio as in music, audio as in mic. I know the music loud. Yeah. Let me know if audio coming through. Mic and desktop audio.
Hello, good day, sir. We are doing a survey. We want to know why you just come on YouTube and watch Spurwin.
Because after I
watch Spurwin live stream
and I kiss my babes, it sends shivers up her spine.
Ooh, it can't get better than that.
Because it freshens your breath.
Brother, tell me why you just watch Spurwin.
Because no matter where I go, no matter what I do, I must always do my best.
Because it's refreshing.
For me, it's the only thing that can relieve my upset stomach.
I's a smoker.
That Spurwin live stream
It does help freshen my breath and take away all the smokiness.
It is very good. It is very useful.
It keeps my breath fresh. Full stop.
Need to keep it fresh all the time.
So you're from Tobago?
Yes, I'm from Tobago. Yes, I love Spurwin. Original.
Spurwin.
God, you're real spit in there. All right, Sam.
What is this whole Spurwin thing about? What is it about?
What that question mean?
Tell me what this whole Spurwin thing is about.
What you mean?
Mr. Montano, tell me, how come all these people watching Spurwin? How come you just come on YouTube and watch Spurwin?
Let me explain something to all you. I live in with a higher understanding of life. And I will tell you something about life. Right? I love every being, every human being. It doesn't mean I have to be intimate with them.
Correct.
It doesn't mean I have to be intimate with them. But I love them the same. Remember, I tell you, if you pay attention to life, life will pay attention to you.
Hey!
Let me tell you something about CXC. Nah, not this cinema CXC. The Caribbean Examination Council. CXC is amazing. Oh my God, you don't need nothing else when you have CXC. First, you have your paper ones. Amazing. Multiple choice exams. You shade little dark circles and come closer. Come closer. Let me tell you a secret. When in doubt, choose C. Better yet, all you have to do is a bunch of paper ones from before, and you're guaranteed to have done at least 50 out of 60 questions by the time you write the exam. Thank God for Google Drive. Incredible. And you get questions like somebody get paid to draw this, yes? But then you have your paper tools. They call these the structured questions. You just answer the questions. Simple as that. Explain to Sunil the advantage of his testes being carried outside body. What, you stupid? Just answer the question, dummy. And then you have your paper trees, labs, SBAs. See, the trick is to not do your labs and SBAs, and then at the last minute let pressure build up and then steal somebody else's book and copy all of their labs. You're guaranteed to do real good. CXC is gangster. See, what you do is you pay them to write exams that you don't want to do, while they just do whatever they want. It have hurricane, exam, volcano, exam, pandemic, exam. Even when things go wrong and a bunch of people receive the wrong grades, like in 2020, they denied for years because they can never be anomalies. Oh my God, what a beast! CXC is the best. 10 out of 10. Would recommend for everybody.
Jesus, exam thing.
Hey,
Who's that, me?
yes, you. Fix that face now. What happened?
Another red man. Not the red man I'm looking for.
The rain is way harder and the wind is...
We wish all our candidates the very best in making the final preparation for your
This is what you're reading?
Jesus, exam thing.
Just right.
In Trinidad, this going on?
That is real ginger beer.
You want to hear the secret to being successful at CSEC?
Yeah, tell me now.
Balancing at top one sideways.
Really? That is your big secret?
Yes. This man real good.
Real ginger beer.
I went from alright to real good.
The letter of the day is
J. J is for
Jesus, exam thing.
Plenty people dying, but we can't do nothing about that. If it's dead, they go dead.
correct. 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 B is for
Bias, Sabayan, or Bati Bias.
And the answer.
Alright, I ain't that.
correct.
Wait, you wanna help me study later?
Study. Study the Guardian CSEC practice
Correct.
test.
Jesus, exam thing.
you will do well. May God bless you richly.
Who's that, me?
As the adage says, you give a poor man a fish and you feed him for a day. You teach him to fish, you give him no. Cue.
Spurwin. Dear Spurwin. Of course it's you, who else could they send, who else could be trusted? All I'm saying is just wait and please just hear me out because this is not an episode, relapse, screw up. I'm begging you Spurwin. I'm begging you. Try to make believe this is not just madness because this is not just madness. 2 weeks ago CXC released the physics broad topics. But Spurwin, I realized I know nothing. I slept through all my online classes. I am a failure. Now my life is ruined. CXC physics is tomorrow. Paper 2. I know nothing. I'm going to fail. I am a failure. I am going to amount to nothing in life. I'm going to become a vagrant. Lenses. What the hell is the difference between real and virtual? I've got exactly 24 hours before this paper 2 exam. I freeze, I can't move, and I'm suddenly consumed with the overwhelming sensation that I'm covered in some sort of film. It's in my hair, my face. It's like a glaze, a patina, and at first I thought, oh my god, I know what this is. This is some sort of amniotic embryonic fluid. I'm drenched in afterbirth, I've breached the chrysalis, I've been reborn. But then I look at everything. The graphs, my calculator, my pencils. His is some kind of giddy illusion of renewal that happens in the final moment before death. And then I realize no, this is completely wrong because I look back at my past papers and I had the most stunning moment of clarity. I realized Spurwin, that I had emerged not from my own life but from the Caribbean Examination Council, an organism whose sole function is to excrete the poison, the ammo, the defoliant necessary for other, larger, more powerful organisms to destroy the miracle of humanity. And that I had been coated in this for the best part of my life. The stench of it and the sting of it would in all likelihood take the rest of my life to undo. And you know what I did? I took a deep cleansing breath and I put that notion aside. I said to myself, as clear as this may be, as potent a feeling as this is, as true a thing as I believe I witnessed today, it must wait. It must stand the test of time. And Sperwin. The time is now.
Listen to me. I know who the imposter is. Activate overdrive. Let's go.
Sperwin. Dear Sperwin. Of course it's you. Who else could they send? Who else could be trusted? I know it's a long way and you're ready to go to work. All I'm saying is just wait and please just hear me out because this is not an episode, relapse, screw up. I'm begging you Sperwin. I'm begging you. Try to make believe this is not just
Yeah, all yeah. Did we get started? Alright, that's not. I'm gonna just put some tunes on here. Let me know if volume good. Too loud. Too soft. Let me know. Did we get started? Good afternoon, everybody. Welcome to Sperwin live streams. This is running from 2 p.m. to 10 p.m. There'll be probably a break in a little bit, but what you do, I have real stamina all day. I could go the whole 8 hours. So let me explain what we're doing today. So today we're gonna go through the theory of the work. I assume your teachers will go through some past papers where we'll go through them as well. But how we doing it is that I will go through the past papers and use it to explain theory, right? So the past papers kind of gonna be a, gonna be a baseline for what we're gonna do. So I know the past papers, some of you would have do it already. That's fine. But we're using it to go through theory because, the questions don't come the same in the paper too. There we go. So hope all you're hyped, hope all you're ready to go. That there to hype all you up. This is not your normal live stream. This is a whole show just for all you. So I hope you're ready. Nobody here going to be a failure once you sit in for this stream. You're going to be good, you're going to be fine, you're going to mash up that CXC, man. What you gonna say? You're gonna have real skills. But speaking of skills, let me take a few minutes to talk to you about a website called Skillshare. Have you ever wanted to try to learn something out of the ordinary, something interesting? Well, you can. Just take a few classes online at Skillshare.com. It's better than lessons.
You want me to show you tough? I'll show you tough.
Where you're taught by instructors and have their own class rosters. Hell, I learned how to juggle and make a peanut butter and jelly sandwich the right way using Skillshare. What are you waiting for?
I never lose.
It had dozens of online courses that you could take, ranging from physics all the way to finger painting, all the way to starting your own YouTube lesson channel. Come now, man. Skillshare. Nice, man. Let me get started. Back to the live stream. All right. So just now, I'll make sure everything's showing good. I'll make sure everything's showing nice. Right. So I say we're going to go through some past papers here. The scrap iron, old battery buying man passing here. So I just let me just wait for him to go. So we're doing some broad topic questions, but as we're going through theory at the same time. This is a long live stream. I cannot guarantee you that the live stream will stay up. That is not up to me. Anyhow. So let me start here. We're not going in any particular order. Let me know if everything's showing good. This is June 2013. I'm gonna just wait for the scrap iron man to finish passing there. Because I can't hear myself if he go on there. Alright, then we look at this first one here. So this first one here deals with lenses, right? And what we know, we have convex lenses and concave lenses. They mostly ask, like when it comes to actually determining the images of an object, they mostly ask about convex lenses, right? This one here is pretty simple. They're just asking you to draw a label diagram showing a conversion lens, right? With these four things: principal axis, principal focus, focal length, focal plane. And pretty simple question. I think is 1 mark each. As you know, a convex lens, it is thicker on the ends, right? Sorry, thicker on the in the middle. So it's thicker in this middle part here, and it's thinner on the, along the vertical axis. So what we have here, when we have a horizontal line cutting across the optical center of the lens, the optical center is the middle of the lens, right? When you have a horizontal line cutting across that there is called the principal axis. So that's this part here. If I was to draw here, and this will be a real rough drawing, if I was to draw here a convergent lens, if we say here we have a convergent lens, right? And this is the principal axis here. And I was to draw some light rays propagating through this thing. So these light rays will come like this. So I'll have one in the middle coming through here, where this will be undeviated. Let me say I have one here, and along the optical center, that there is gonna refract, is gonna bend, and these are going to bend towards the principal axis there. So this point here where all these converge, this is called the focal point or the principal focus. So if we draw a line perpendicular to this focal point, perpendicular to the principal axis in line with the focal point, that there is called a focal plane. It's pretty easy, and I'll explain like why, what's the point of having that. So if you was to draw a line coming down like this, that there's a focal plane. This for like a little P here. This is the focal plane. Pencil tick all here. But what are you gonna do? There's the focal plane. So we have the optical center, the convex lens, that's here, the principal axis going across, the focal point, and the distance between the optical center and the focal point. This distance here, this is called the focal length. Not hard at all. The focal plane, not in the middle of the lens. The focal plane is perpendicular to the principal axis in line with the focal point. So, not hard. I mean, there's your basic drawing diagram. And you'll take a look at it again. Not bad, or you could just look at a textbook. Right. So state the law of conservation of linear momentum. So let me explain that there. So I want you to imagine that we have, here, right, that we have a ball. Right, and we're calling this ball here A, and we have a ball here B. So let me say ball A and B, that they both have a mass of m. So they have the same mass, right? They have the same mass. Imagine it's like two pool balls, like two billiard balls. So let me say ball A hit ball B, and let me say that ball A is going at 6 meters per second, right? What's gonna happen if ball A hits B and it was to transfer or impart all of its momentum onto B? Well, that's easy. What's gonna happen here is that A is going to stop, right? So A is now going to be 0 meters per second, and then B is going to start moving. And that's going to start moving at the same velocity as A. So this is also going to move 6 meters per second. So basically, what's going to happen here is that when A hits B, A is going to stop moving and impart all of its momentum onto B. That is, so in this case here, because there was the same mass, this will go the same velocity. So basically, if you was to think about it, we could say is like this. We could say that mv before, this is before collision, is going to be equal to mv after collision. So if the mass is the same on both sides, the velocity is going to be the same. So let me sum up here a next basic example, right? But we're going to use two different sizes for these balls. Let me say that this is ball A, and this here, this big goonks here, this is ball B. So let me say A here moving at 6 meters per second, and A is moving at 6 meters per second and hitting B. B is stationary, right? And A now has a mass of 2 kg. B has a mass, let me say 6 kg, so 3 times as big. And we want to find out what velocity B is going to go. So remember now, to calculate momentum, we use the formula P is equal to mv. So why P, by the way? P actually originally meant something like push, because M stands for a lot of things. So they could, M is already mass, so they just use P. So yeah, momentum is part of forces. And So let me work out the momentum before collision. This will be 2 times 6. So before collision is going to be 12. And remember the unit here is going to be kilograms meters per second, which is basically a combination of mass and velocity. You could also say Newton seconds. Alright, that's now You could also say Newton seconds. It is the same thing, not newtons per second, right? Newton seconds. So if we are to determine the velocity of B, is very simple. We have to say 6 times what number? 6 times what number will give you 12. So in the case here, the momentum after is going to be 6V is going to be equal to 12 Newton seconds or kg meters per second, same thing. So this is easy. The velocity that this is going to go at is going to be 12 over 6, and that's going to be 2. Right, so this here, the velocity is going to be 2 meters per second. So I know the writing kind of all over the place. Yeah, you could use Newton seconds for impulse as well. Impulse more relates to the rate of change of momentum, but you could use either one for CXC, that's fine. So let me look at this question here. This is June 2013, by the way, right? So this is state the law of conservation of linear momentum. I don't think these things come in honestly because they came in January and describe a situation that demonstrates the law of conservation of linear momentum. So the law says in a system with no external forces, the total momentum before collision is equal to the total momentum after collision. Basically, the net momentum is equal to 0, or you could say the total momentum before and after collision is equal, same thing. So a real life example is you could use pool balls as an example. You could use Newton's cradle as an example. All of these here kind of demonstrate one object colliding with another, causing the other one to move. If all you ever hear about these things called Rube Goldberg machines, they're kind of cool. You could look them up, not now, but you could look them up. It have a music video with one, but obviously I can't show it here. Stream will get taken down by a band called OK Go. And I think the name of the song is This Too Shall Pass, kind of like CXC. That show like a real good example of multiple interactions with momentum. Don't watch it now though. So you use pool balls, Newton's cradle, car colliding with the next car, trolley, price car, trolley colliding with the next one. Whatever you want to do. One man running into our next man, who knows, all has momentum. Right. So let me get into how exactly we calculating this thing. So we have a truck, a gun with recoil is a good example too. This is like a common type of question that has come. So we have a truck of mass 1050 kilograms, right? Heading north, right? North, cross the median on the Jasper Highway, wherever that is, and slam head on at 25 meters per second into a 625 kilogram car heading south at 30 meters per second. So the question typically is, and this whole thing is 9 marks. Again, I don't think this coming because it came in January, but you never know, eh? You never know. It's still to know the thing. It's not to know the thing for examine, it's to know the thing for knowing the thing. What was the initial momentum of the truck? So first, we're going to calculate here for the truck. Now remember the truck here, it was 1250 kg, that was the mass, and it was heading north, and the velocity was 25. So here we have the 1250 mass, the 25 velocity, we multiply this, right? If we multiply this, we're going to get this answer. So this here is going to be the momentum of the truck. Now you have to remember now, and if I use this example here, let me find something here with momentum. Now remember, all this is part of forces, all Newton's laws, everything. So you have to think of it like this. Alright. So let me just change this. This is June 2013, not 19. Nice. So, if you look at this example here, we could see that we have a car and a truck, but they're heading in opposite directions, right? So, this is where they collide. So, here's where, this is where it'll be before collision. So, this is before collision. Putting BEF for before. And here, this is where it's going to be after collision. So the total momentum before collision is going to be the total momentum after collision, right? So in this case here, we need to calculate the momentum of the car and the momentum of the truck. We need to calculate that separately. So that's basically what you have to do for this question here. So this first calculation here is for the for the truck. And we multiply the mass of the truck times the velocity it was going. You get 31,250 kilogram/meter per second, and that truck is heading north, right? You don't need to mark the north here, but I just mark it here. Now we're going to calculate for the car. So the car now is 625 kilograms, so that's what you're seeing here, and they're heading 30 meters per second. So you might see here that I put negative 30 instead. You might be like, well, why did I put negative? Well, in this case here, you have to remember momentum is a vector. And a vector quantity is one that has both magnitude and direction. So in the case here, because it is heading in an opposite direction, it is opposing the other vector, the other truck momentum vector. So in this case here, you could think of it like the truck is heading north. Right? The truck is heading north, and there's a vector there. Then we have the car, which is heading south, and that is going opposite, so that's why we have it as negative. So there's a very common mistake a lot of students make, is that they forget to put the thing as negative if it's an opposing vector, if it's going in the opposite direction. Because remember, the impulse that is created by the rate of change of momentum, that's going to be negative, because it's going to be opposing the next one. So multiply these two, and you're going to get negative 18,750 kilogram/meter per second. Just to answer everybody's question, I can't determine if it will stay up. I wish it would stay up, but it's up to YouTube. This stream does have all kind of thing in it. So we can see. So now they say when this car is destructed, they're gonna collide, right? So they're gonna smash up, right? So they're gonna crash together, and they're gonna form one big wreckage. Magician, it doesn't matter which one is negative, but typically you do the second one as the negative one. Just one is positive, one is negative. It don't matter really. So when they smash up now, they form a wreckage, and that wreckage now we need to find the total mass of it, because imagine you're watching Fast and Furious or something, and one car hit the next one, right? They're gonna hit the next one, and then they're gonna drag the next one. So this total mass here, this is the mass of this wreckage, and this is gonna, when you just add up the mass of the truck and the mass of the car, you're gonna get this here. Now remember that this here, what we are counting for here, right? This is gonna be after collision, so this is gonna be after, because it done crash. So the total momentum of this is real simple now. So to say now, assuming that the car, we want to find the speed and direction of the wreck. So the total momentum, we need to find that first. That's simple. All we need to do is add these two numbers here. Of course, one of the numbers is negative. If they are going in the same direction, both of them are going to be positive. But if they go in opposite directions, they'll be negative. Some arrow. So the total momentum, in this case here, you add them, but since one negative, you basically subtract. Is easy maths. And you use the formula here. P is equal to mv. And we're going to transpose that. So P is equal to mv. And all the real going through if all can transpose a formula by now, but let me show you a shortcut to let me show you something to think about if you ever get trouble with this. Imagine P in its own house, this momentum in its own house, the M and the V, them in their own house, right? There's a house. So what we want to find for, the velocity. So V going to stay home by itself. Of course, you divide both sides by M to get rid of it. But if you can't do maths, think of V staying home by itself and M going next door. But when you go next door by somebody, right? You don't go upstairs in the bedroom and all kind of thing. You kind of stay downstairs. So since this in P house, what going on here? I shock just now, think I'm messing up a little bit. Let me show you here. Right. Since in P house, right? You go downstairs. So it could be P over M. That's real easy. Let me show you with a next formula here. What's the next thing that coming for? We say that we have E is equal to I VT, right? And you want to find for T. Again, T staying home, and I and V, them going next door. Again, they're going downstairs. So it could be T is equal to E over IV. All in real trouble if all they can do, but that's the shortcut. I can't teach all the maths now, but that's the shortcut. Just think of it like that. Somebody staying home, everybody going in the house next door, but they going downstairs. They can't go upstairs in the bedroom. None of them house, what you gonna do? Alright, let me come back there. So, transpose the formula. You get V is P over M. That's the total momentum. Let me get rid of all of this garbage here. Okay, looking real cluttered. Right, so you do V is P over M. 12,500. Remember, this is the total momentum that we just calculate from the sum of these two divided by the total mass, 1,875. You're going to get 6.67 meters per second. Somebody asks, why is this 9 marks? You get marks for every single step of this, right? You get a mark for the formula, P is equal to MV, the mark for each individual answer. So this is 1 mark here. So this is 1, this is 2 marks here, this is 3 marks here, this is 4 marks here, 5 marks for the unit, kilogram meter per second, 6 marks for getting the total momentum, 7 marks for transposing the formula, 8 marks for the answer, and 9 marks for stating the direction. So even though you feel like it's like a little bit of it's too much marks for the thing, there is mark each individual thing. So don't forget the units, don't forget to transpose, and I'll tell you something, like when I'm marking CXC, right? Let me say that you know how to transpose nothing, right? Let me say that you know how to transpose nothing. Let me tell you something. Let me say that you have to calculate current, right? And you know current is I is V over R. But instead you ship itself, go on and put I is R over V, right? Of course this is wrong. What gonna happen now? Well, you're basically gonna lose all your marks. The only mark you're probably gonna get is for your unit, right? Because you get your formula wrong, thus you're gonna get your answer wrong. You're gonna get the whole thing wrong. If it have a next question following this that using the current, you'll probably get an error carried forward and you'll probably get that correct. But this is how you could still get at least a mark for your formula. If your teacher didn't tell you this. Write V is equal to IR, right? Write the thing you know first. Write this, you'll still get the mark, even though if you transform, it's stupid. Not transform, transpose it. And you put therefore I is V over R. If all you know that, all you're going through. But if you'll still get the mark, of course. But if you put V equal IR, therefore I is R over V, you will actually still get the mark for the formula. So it's not all the time though. Usually if it's like a 3-mark question, you'll actually still get a mark for your formula and you might still get a mark for your unit. It's just that the calculation is stupidness. So, let me come back here. Well, this one easy. All you want to do this experiment here. Potential question that could come, you never know. Describe an experiment that can be used to determine the resistance of a metallic conductor. Easy, easy. All you have to do is this. You draw a diagram, you label it, and then you kind of describe what's going on. So in this case here, the circuit will consist of a battery, a switch, an ammeter, a rheostat or variable resistor, and the metallic conductor. All of these would be, whether it's a resistor or a lamp or a diode or whatever is the unknown resistance will be there. And then what we will have is the voltmeter will be connected in parallel. So it might be like, well, why exactly is the voltmeter in parallel? So this is because the voltmeter actually has a high resistance and the ammeter has a low resistance. So what you want to do is that you want to limit how much current will come down here. So the voltmeter has a high resistance. You limit how much current comes down here so you don't affect the rest of the circuit. There's actually bring questions where there's bring a table to ask those things. The ammeter has a low resistance and it's quite negligible. Sometimes it's close to 0, so it doesn't really impact the circuit as well. So that's really the reason for hooking it up like this. Now, first, when they ask you to describe this kind of experiment, you always have to, it actually don't matter which experiment I describe and all, you know, the standard thing is that you take at least 5 readings from something. You exactly get a mark for saying that. You have to take at least 5 readings, and then either you get the average or you plot the graph and get the gradient, which would then be like the average. So you plot at least 5 readings at probably 2 trials and find an average fit. And in this case here, resistance R is calculated by V over I. Therefore, the gradient of the graph showing voltage versus current will be equivalent to the average resistance of the metallic conductor. So in this case here, your graph will kind of look like this. Right? So your graph will look like this here. And if it's V versus I, you just have to find the gradient. If it's I versus V, you find the inverse of the gradient to get the resistance. Typically, you'll see it as I versus V. So, yeah, easy question. Now, let me take a while here now because circuits come in for all the thing, right? Let me take a while here to make all you understand and make it clear how you calculate for circuits. So magnetism now come in. Alright, so you look here. So here we have a series circuit, right? And let me explain how this thing does work. It only have one current part in a series circuit. All you know this. We had to go from positive to negative because we use conventional current. The reason why we go positive to negative, by the way, is because electricity was invented and the light bulb was invented and DC wiring and AC wiring was invented before J.J. Thomson invented discovered the electron. And by then they thought that it was positive charges moving. But when this blasted man discovered the electron, he discovered his negative charges. But by then everything was done wire up, everything was done label up, and this was worldwide. And by then they was too lazy to change the thing and call it electron flow. So this is why we use conventional current. Is because it's convenient. They should more call it convenient current because they don't want to change everything. So what we say instead is that we have positive charges flowing out of the positive terminal of the battery and then gets attracted back to the negative. That is not actually what happens. What happens is the opposite. Electrons get repelled out of the negative end and get attracted to the positive. That's why it's called electron flow. But because we didn't want to change everything, we just go with conventional current, right? Because everything is work like that. Because if we say positive charges flow in this way, which is not true, that's the same as saying negative charges flow in this way. It's the same blasted thing. It's the same thing. So anyway, so in a series circuit, we only have one current path. So if I was to break the circuit at any point, whether it is a slice the wire, break it apart, or remove a bulb, that means that no current is going to flow, because it's kind of like you break a bridge. So all you know this already. But what we need to remember is how we treat current and how we treat voltage. So current, we use something called Kirchhoff's law. I don't think all you would have learned that at this level, but you would know the theory behind it. Kirchhoff's law basically says that the current in a series circuit, or shared between components in series, is the same current that's going into a component is the same current that is coming out of a component. So in the case here, if I was to say that this is our current here, I'll just use an example. Let me say that this here is 1 amp, this here gonna be 1 amp, this here gonna be 1 amp, this here gonna be 1 amp, everywhere here gonna be 1 amp, 1 amp, 1 amp. It depends on, there's not 1 amp in this case, but if it is 2 amps, it'll be 2 amps, 2 amps, 2 amps, 2 amps, 2 amps, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, and so on. It wouldn't change. So the current through each component is going to be the same. Yeah. So in this case here, the voltage on the other hand is shared. So remember, the law of conservation of energy states that energy cannot be created nor destroyed. It can only be converted from one form to another. So this 6 volts here, you have to remember what this 6 volts mean. You have to remember what this means. 6 volts means 6 joules, right? 6 joules per unit charge, 6 joules per coulomb. So this is you can think of this as a measurement of energy per charge. So think of it like the voltage is the strength of the battery. Now, this 6 volts is shared between these two components here. So how exactly is calculate this? So let me say that we have to calculate the following: the total resistance, the current, and the voltage only through bulb A. How are we doing that day? Well, not hard at all. The total resistance, if you pass common entrance, well, not common entrance, if all you pass SC and all you could add, all you could do this. So all you have to do is add the total amount of resistance. In this case here, at this level, we don't count the wire. You have to remember the wires have resistance too, but all you learn that and keep resistivity and thing. But we just counting like the individual components here. So we have 2 bulbs. So we have 5 ohms and 3 ohms. It's easy to figure it out. There's going to be 8 ohms. Now the current is going to be I is equal to V over R. So the total voltage is going to be 6 volts, right? And the total resistance will be the sum of all the components. So if we had like 3 resistors, we just add them once they're in series. Now, in this case here, the current, we take the total voltage, which is 6, divided by the total resistance, which is 8, and that'll give you 0.75. Now, if you just wanted to find the voltage through one component, right? One component. Let me just say through A alone. What were you doing here, right? So IR. So this will be 0.75 times 5, and that will be the total current. Now remember the total, this will be 0.75 throughout. It'll be that in both bulbs, it'll be that in the battery, it'll be that in everything. So 0.75 times 5, that'll give you 3.75 volts. Now, if you wanted to find for this one, it's easy. You don't even need to do a formula really. You just have to say, well, what is the remainder? If this taking up 3.75 volts, right? And the total is 6 volts, this is going to take up the rest. So this here is going to be 6 minus that, which is going to be 2.25 volts. So it's easy. You just have to make the thing add up. You just have to make the voltages add up. It's as easy as that. Now, let me come back to some questions here. Let me look at this here. Figure 12. So there's a kind of hard one here. Figure 12 shows a 12-volt battery of negligible internal resistance connected to an arrangement of resistors. So we have 4 resistors here, R1, R4, and you see that these are connected differently compared to these, R2 and R3. Now, look at what we're doing here. Given that resistors R1 to R4 each have a resistance of 3 ohms, calculate the total resistance in the circuit. And what is the current drawn from the 12-volt battery? Now, look what happening here now. Remember, each one here is 3, right? 3 ohms. Each one here is 3. And I have a feeling all might get something like this because it's a little while since a little circuit question like this come. This is 2013. So we need to think about which ones in series. So the ones that are in series, right? And I put in it here, RS, the ones that are in series, that is R1 and R4. These in series. That's them two here. The ones that in parallel, right? And I put in it here. The ones that parallel, that are going to be R2 and R3. The key thing about doing these circuits, no matter how much resistors they give you, no matter how much components they throw in your face, right, is to simplify the damn thing. So look what you're doing. You're going to simplify R1 and R4. We're going to count that as like one quantity. So this is 3 and this is 3. Well, we know the sum of that is going to be 6, right? So the sum of these two are going to be 6. And this is 3 and this is 3. But how we work this out is a little different. So, I'll show you here. How exactly is work this out? And I say this is easy, you know. You just have to simplify the thing no matter how much thing that they throw in your face. All you have to do is simplify the thing. Right. Oh, shucks, just now. So, we're going to say R1 plus R2. And that's going to be 3 plus 3. And that's going to be 6 ohms. Now, if you had to work out these two in parallel, there are two formulas you could use, but I'll just use the LCM one. Or you could do in electrical and thing, or you know the next one, or probably if you're doing physics. So, how you're doing this is you're going to say 1 over RP is equal to 1 over 3 plus 1 over 3. Of course, that's 2 over 3, so we need to find an LCM there. But you have to remember now that this is 1 over R. So that means that RP is going to be the inverse of that. 3 over 2. And that'll be 1.5. And I've seen people done post today. But I say I take my time because we have some people here who are studying not, you know, they're probably going to fail. All we have to do is add this number here and add this number here, and the total of this is going to be 7.5 ohms. Easy. Physics easy. We need to be doing this. I'll upload, even if the stream get taken down, I'll go upload all these documents after. let me go through here on how to do a half-life graph, because the half-life graph is likely, you know, that's what's gonna come. So that's now, let me find that default here. So the half-life graph, I think that come in June 2015. Nice. Thing like this easy to do, you know. First, you know, you plot the thing. Time is always on the x-axis. Activity always on the y-axis, all you know that. So the graph, now let me show you what the graph will look like. So the graph now going to look like this. Right, so you're gonna see it look like this. So what are you doing now? This is easy. All you have to do now is this. So if all you see in this curve here, right? This is how you work this out. What we need to do is sometimes they say take 2 pairs of values or take 3 pairs of values. I think it's always safer to take 3, but you could take 2 and you could still get your marks, because they usually say 2 or 3. So here we have a half-life curve, right? And now you have to remember what half-life mean. Half-life is the time taken for, what type it here? Is the time taken for a radioactive substance to decay by half, or for its activity, its radioactivity, to be halved. Now, so that means if we have like 1,000 atoms, after a half-life you'll have 500 atoms, and then 250, and then 125, and so on. This is an estimate. It is not an exact thing, because radioactivity is random. It's actually one of the only random things in the universe. Other things that we just say it's so random, that are random, and say even dice rolls and things not truly random. The only one of the truly random things is radioactive decay, the rate at which these things, you know, just get released. Now, how do we actually, if I had to give you an example, right? Let me say that you get cancer, and they had to put that, use a tracer. Typically, they use iodine 131, right? Iodine 131 has a half-life of 8 days, right? So iodine 131, half-life of 8 days. So let me say that we want to figure out, oh well, how long this thing gonna stay in me? How long would it take for iodine 131 to decay to 1/32 of its original value, right? How are you gonna do that? Well, this is how you work it out. As I say, not hard at all. How long is it gonna take to decay to 1/32? Well, first we start with a whole number, and that whole number here is gonna be 1, or 1/1. After 8 days, they're going to decay by half. It'll be a half. After the next 8 days, you're going to get to a quarter. After the next one, you're going to get to 1/8. After the next 8 days, you get to 1/16. After the next 8 days, you get to 1/32. So typically at this point, what you just count is the number of arrows that you have, because that's the number of half-lives that pass. So we have 1, 2, 3, 4, 5 arrows. That's 5 half-lives. So if 5 half-lives, it take 5 half-lives, that'll be 8 times 5. It'll take 40 days to break. So at that point, most of it would be out of your body, if you know what I mean. So if you use a tracer, that's what happens there. So if I had to take our next example here, let me say, using the same iodine 131 as an example. Iodine 131 has a half-life of 8 days. If there are 2,000 atoms, right, in the beginning, how many days have to pass before it decays to 500 atoms? Number those atoms, let me say grams. 2,000 grams, 500 grams. So use actual mass. So, again, do the same concept. Same concept. What you have to do is this. Start with 2,000, that's the initial amount. Then 1,000. Then 500. And if we count how much half-lives there, how much times did we have to halve it? So this would be 1. This would be 2. So 2 half-lives. That would take 8 times 2. 16 days to get to that point. You don't have to get the curve perfectly honestly, because a lot of the time you're gonna get some points off the because it's just an estimate. So what you want to do is, well, I get 24 days, right? 16 days. Everybody gonna pay a lot. Yeah, so it's not gonna be perfect. The curve not gonna be perfect because it's an estimate. And that's actually something that there's actually too for like a mark. Why is the curve not absolutely smooth, or why does it not go through all the points to form a perfect exponential curve, something like that? That's because half-life is an estimate, because radioactive decay is random. Now, how do we determine the half-life from a graph? Well, if you look here, right? If we just look at the figures here. So this represents the activity, and this is the disintegrations per second. So this here is 40, starts with 40. And after one half-life, think about how much you're gonna have after one half-life pass. Well, in the case here, oh yeah, sorry, this would be 8 days, not hours, right? So I'm gonna scratch off hours, that's my bad. So after 40, think about how much you're gonna have. You're gonna have only half of that, which is 20. So the time it'll take to actually drop from 40 to 20, that will be a half-life. So how we're going to determine that is easy. All you have to do is draw a line coming straight across to the curve and cutting down here to 8. So you see here it touches 8. So this is an estimate of the half-life, but because it is random, what we need to do is do a next pair, right? Or even 3 pairs. So we don't reuse any of these. So when all you're doing all your exam on Monday and you have to do it, don't use 40. Let me say, for example, if you use 40 and 20, and then use 20 and 10 as the second pair, you're going to lose marks, right? You have to use 2 separate independent numbers. Now, it don't have to be 40 and 20. You could use 30 and 15. You could use 10 and 5. Right, which is what I use here. It's just once one is half of the next one. So in this case here, the easiest ones for me to use was 40 and 20. Now typically you see where the curves start to kind of flatten. Well, not flatten, but it start to kind of level off here. Try not to go too much down here. So where you're seeing like past 5, if you was to go down here, it'll get very difficult at this point here because it has so few atoms left. So in the case here we are 10 and 5, we carry this across. 10, we are 16, 5, it was about 24, right? Now typically what you do here now is that you say you write a calculation like this. T a half, that means half-life, that's going to be equal to the first pair, the difference between the first pair, T2 minus T1. In that case here, that is 8 minus 0. Right? So 8 minus 0. And that is, of course, equal to 8 days. Your second pair, you minus these two now, T4 minus T3. Easy. And that'll be 24 minus 16. And that's also going to be equal to 8. So at this point, if you was to get two numbers that was a little different, in this case here I get the same number for this past paper, but if you was to get two numbers that are different, if we say for example you was to get 7 here and 8 here, at that point there, what you want to do is find the average. So you say TR half average and then you find the sum of the two numbers divided by 2 and you're good. Now so coming back here now, these is the other things that you have to know about radioactive decay. Other potential things that could come is this, right? You have nuclear energy. So nuclear energy, fission versus fusion. Sometimes they ask you to define these two things. It's easy. Fission, sometimes, well, I never mark a physics paper, but I know how the process is. I know people who mark it and things. People just mix up fission and fusion, right? And sometimes I just can't remember. I find it easy. You watch Dragon Ball Z fusion, two of them fuse into one. I don't know, fusion, fuse. Fission means to split. Fisher means to split, like binary fission in bio. But what some people just put is fusion, and they just write it in a kind of way. I think they just write it like fusion. I don't know where this come from. They just write it kind of like this, because they can't remember which one is which one, and it just kind of look like fusion and fission now. So don't pull that, right? Yeah, because there is actually be extra careful to look out for the word fission and fusion. There's some people just put fusion or try to fuse the two things. Don't do that. You get it wrong. It is all kind of thing that is happening in the marks room, for HSB. People that doesn't know how to spell scrotum, that doesn't know how to spell testes, that is put ball sack and fun bags and all kind of thing. For diabetes, that is put sugar, not high blood sugar, it is put sugar, all kind of stupidness you to see. It had a time where they asked for ethical, like for genetic engineering, asked for ethical, dilemmas or ethical considerations to have with genetic engineering, and then put ethnic considerations like with race and ethnicity and things. Some people don't know like what they're doing. Oh, sorry, I didn't switch it back. Yeah. So fission and fusion, easy. All you should know this, pros and cons of nuclear energy, right? Usually they ask for 2 pros, 2 cons. And these are the typical ones they use. Our next one I did see was, what is the advantage of using fusion reactors over fission reactors? So fusion reactors don't exist yet, Like we'd probably use thorium fusion reactors or something. Like, remember the sun does experience fusion, and fusion does actually release real energy. So that would be like the pro if they ask that would come here. But in this case here, nuclear energy is more efficient than fossil fuels. It is much more usable and efficient electrical energy, and it produces no greenhouse gases. It does not contribute to climate change. It don't have any carbon emissions or anything like that. These are the 2 pros that you typically will go with. The cons of this, they might ask for 2 or 3. There's always a risk of nuclear meltdown. You have Chernobyl in Pripyat next to Ukraine. and you have Fukushima, Japan as two examples. Radioactive waste is difficult to dispose of. Yeah, create a fusion reactor, now you can solve plenty problems that we have today. Radioactive waste is difficult to dispose of because typically what they have to do, long time they used to just dump it in the ocean. They used to just throw the thing in the sea. But now, you know, they have to bury it in lead containers because gamma rays cannot fully penetrate lead. And so they bury it in lead containers. There's a lot of waste that's produced. It's expensive, difficult. If you had about third corners, that it's expensive. It don't really have anywhere in the Caribbean that could really, I wouldn't say afford it, but it's you know, we are a little behind with it. If you have a nuclear meltdown here, all you should know about Chernobyl, because you have all that strontium in the air and they have a half-life of a couple thousand years. People basically can't live there for like a couple thousand years. So yeah, man, that's how the thing does work. So this is the kind of big one here that a lot of people doesn't really understand. The formula for nuclear energy and calculating nuclear energy, right? This is how you have to do this here. Now typically you could also write this as delta E is equal to delta MC squared. So what's really going on here? Well, this is Einstein's formula here, and this basically says that is the relation between energy and mass, right? It says that energy, mass can be converted to energy. So mass loss, so the change in mass in a reaction can be converted into energy. And that there multiplied by the speed of light squared will give you the total amount of change of energy in a nuclear reaction. So how do you actually calculate this? Okay, so if you follow along here, we'll break this down real easy using a simple example here. I'll link a more complex one. I won't really go through it here, but I'll go through the simple example and the different principles you have to do, because this come for like all kind of 7-8 marks something if they bring it in full. If basically you're going through if you get. So here we have two isotopes of hydrogen. We have deuterium, which is hydrogen 2, and tritium, which is hydrogen 3. Two of these here, when combined, this is gonna give you helium or alpha particle, a neutron, and some energy. And the question here is calculate the energy release in the reaction above, and they'll give you a little table like this. This is how we do this. So we'll have the nuclide. This is like the isotope, and the atomic mass. Now the atomic mass U is not an actual SI unit. This is a relative unit. So you know when you're doing chemistry and you have relative atomic mass, relative molecular mass, and them kind of thing, those are relative units. It basically is telling you that if it have a relative mass of 2, it just means it's 2 times heavier than hydrogen. If it have a relative mass of 4, it means it's 4 times heavier than hydrogen. So that's all that means. It is not actually in grams or kilograms. So we would actually have to convert it using this, but we don't have to convert it yet. Now, so we have this here. So how are we going to calculate the energy? First, add the masses on the left. So this is the left side here, these two hydrogens. So if you look on the table, we have 2.014 and 3.016. So you add these on the left side first. So you take care of this side first. Now we're going to do this side here. So remember that this number here is the sum of the nuclides on the left side. So on the right side now, we have this. The helium, the neutron, and energy. So we're going to add the helium and the neutron, but we don't have a value for energy. So we're going to add 4.003, 1.009, add these two, you're going to get 5.012U. Now if you remember what we had the last time, it was 5.03. So be like, well, what happened here? Why is it, if I break a plate, I mash up a plate, right? I break it in half or break it in 3 pieces, I would probably still be able to put those 3 pieces or 2 pieces together. It should come back to the whole. So why is this less? Well, this is less because the change in mass between the two, the change in mass was converted to energy. So that's the key here. We need to find what is the difference in the masses. Now, subtract the difference. The change in mass 5.03, that would be the mass at this side, minus 5.012, that would be the mass at this side, and you get 0.018 U. That would be the mass that's going to then convert to energy. But remember that this here is a relative unit. So we need to convert it to kilograms. So to convert this unit U to kg, right? What we need to do is to take the difference in mass that we just had minus, right? So the change in mass was this. This is the difference in mass in the units U, and multiplied by this value here. Now, because this nuclear energy kind of segues into a field called quantum physics, which is the physics of the very small, typically, unless asked otherwise, typically you put all your decimal numbers. If you have 5, 6 decimals, this is the one exception where you'll put all of them. In other cases where they say put it to 2 sig fig or 3 sig fig or something, you do that. But otherwise, you put everything. Now, we get this as our mass in kilograms. So they say use Einstein's formula to calculate E. Delta E is equal to delta mc squared. So to calculate this, you have to remember C, and they'll give it this, is 3 by 10 to the power 8. So instead of squaring this whole thing in a calculator, you could just write was C squared, right? So the squared value of this 3 squared is 9. And 10 to the power 8 squared. So 10 to the power 8 squared is 10 to the power 16. So you don't need to like type out the whole thing and then square it. All you need to remember now is that C squared is this value here. 9 times 10 to the power 16. So 2.988 by 10 to the power negative 29 kilograms times 9 by 10 to the power 16. You get this here. And that's how it's calculate the energy. Now I say this slideshow is up in a video, so all you should be able to see the questions there as well. So as I said, I just taking my time and going through it here. Well, I'm gonna go through here. Typically, if you want to know what coming for exams, it's not all the time, of course. You go back about 5 years in your past papers, it have a kind of rotation of 5 years or so, 5 to 6 years, 4, 5, 6 years, and look at the topics that I see in there. So if we look at this here, this question, and remember, all you could work this out with me as I doing it. So a car tire is pumped to a pressure of, let me make this a little bigger. It's pumped to a pressure of 2 times 10 to the power 5 Newton per meter squared. This is pascals, right? Newton per meter squared is force over area. In the morning when the temperature is 23 degrees Celsius. Later in the day, the temperature rises to 34 degrees Celsius. Calculate the new pressure in the tire, and the volume is kept constant. Okay, let me explain some theory here for you first, just that you fully understand everything here. Or look at the simulation here. So here we have a container, right? And this container is currently empty. We have a thermometer, we have something to add heat, and we have this man here to adjust volume or the size of the container, right? So in terms of, when we talk about gas laws, we had these molecules bouncing around here, right? Look what's happening here. What is actually generating pressure or creating pressure inside this container here? What's happening here is when these molecules, not when they collide with each other, but when they bounce off the container here, when they bounce off the container, that there is going to impact a force, right? Impact a force against the sides of the container, the inner walls of the container, and that's going to create pressure. The higher the frequency of these collisions, and you can see this pressure gauge here, if I add more molecules, the higher the frequency of these collisions, basically the more often that they collide, the pressure is going to go up. So keep that in mind. The more collisions, the more pressure. So if you have a higher frequency of collisions, or if the molecules hit harder, so even if I have a small number of molecules and I was to add kinetic energy to those molecules, right? And also make that bounce around more and more and more and more, faster and faster, harder and harder, more and more force, that's going to raise the pressure of the container. So pressure and temperature have a directly proportional relationship. The more I increase the temperature is the more kinetic energy going to be in the molecules, and thus the more force they're going to impart on the walls. That's pretty simple. So the more I increase the energy of the molecules with it pop there, is the more pressure you're going to have. Once you understand the basics about it, the formulas just come in normal. So watch this next thing here. If I have, let me say that right now, let me say I was to adjust the length of this container, the volume, right? So right now, the volume is 6 by whatever, let me just say 6 meters cube, right? And I have a certain amount of gas molecules here. Now remember what I say, this constitutes pressure in terms of the gas pressure. This is where the molecules collide with the inner walls, right? The higher the frequency of those collisions and the higher the force of those collisions equals more pressure. Now, if I was to have less volume, but first I'm going to have more volume. If I was to have more volume, it have more space for the molecules to move around, so they're not going to hit the walls as often. So if I actually increase the volume, that is going to lower the pressure. But look at what's going to happen if I was to increase. So right now, the pressure is about, let me put a few more particles in here, so I can get up to 1 atmosphere. Right, so you're watching this gauge here, trying to get up to about 1 atmosphere, or close to that at least. The more molecules, of course, is the more collisions. So right now, it is 1 atmosphere at about 6 meters cube, right? So I'm going to halve this. I'm going to put this to 3. And what you're basically seeing is that the pressure has doubled, because it went from 1 atmosphere to 2. Well, it will fluctuate a little bit because there's a dynamic simulation. But what's happening here now is because now in a smaller volume, the frequency of collisions is going to be higher and higher. So if I was to even decrease the volume even more, the volume would increase. In fact, it might just pop. So those 3 interactions come into play when you're talking about gas laws: pressure, volume, and temperature. In the case here, yes, that's correct, Taco Shell. That there's Boyle's law. Once I keep the temperature constant. So an easy way to actually remember some of these, I just doing random questions. They're not really doing it by year. Any particular, but this one is June 2014. I just doing random questions just to explain the theory. I'm not really here to do past papers. So I just here to go through the theory to make sure that the theory sticks, because you can do plenty past papers and yeah, the question, if you understand the theory, you're going through it. So I find gas laws real easy, because even though it have 4 formulas associated with it at this level, you really only have to know one. So that one particular formula you have to know is called the combined gas law, and that is P1 V1 over T1. The name of the simulation is from a system called PHET simulation, PHET, simulations from the University of Colorado. Right. This is the only formula you really have to know for gas laws. One formula. The reason why I'm saying this is because the other 3 formulas involved in gas laws, which is P1 V1 is equal to P2 V2, that is Boyle's law. V1 over T1 is equal to V2 over T2, that is Charles' law. And then if I was to put the third one, studying if I run out of space there. Nah, it's not space. P1 over T1 is equal to P2 over T2, that is called Gay-Lussac's law, or the pressure law. I don't know why they just don't call it Gay-Lussac. I don't know if because the man's name is gay that they don't want to do it, but the name of the law is Gay-Lussac's law. But we just call it the pressure law here for some reason. I have his Jamaicans just do like, you know. Anyway, so in this particular case here, once we use the general gas, so the 3 formulas are in there. So in the case here, whatever is kept constant, if they say something is kept constant, right? All you have to do is cross off that value from it. So this here, we cross off V in this case, and we get the formula. It as easy as that. All we have to do is just cross off whatever is not part of the formula. So if they say temperature is constant, you cross off temperature on both sides, you get P1 V1 equals P2 V2, that's Boyle's law. If they say pressure is constant on both sides, cross off pressure, and you get V1 over T1 equals V2 over T. It's easy. So you just have to remember one formula. Of course, if they say nothing constant, that means that you're just leaving it just so and you're calculating it just so. Now, well, you can work this out as I go in here. So you're going to say P1 V1 over T1 is equal to P2 over T2, but since they say the volume is kept constant, we're going to rewrite this formula. Right, so you're going to rewrite this formula. Yeah, they could ask for a specific law, like you still have to know the wording of the laws. Right, P1, what sharpness I writing, but like I go, no matter what, P1 over T1 is equal to P2 over T2. Like I going crazy or what? Right, now since the volume is different on both sides, is constant on both sides across the top, so it's not part of the formula, it would cancel off anyway. Now, questions like this typically go for like 8 marks, 7, 8 marks. So this is because, and this is the most common mistake when it comes to doing this. These buggers right here. These Celsius buggers right here. This make you get the whole thing wrong, because when we relating pressure to temperature, the temperature has to be in a linear scale. Oh, sorry. Sorry. That's not there. So you had to put the thing in Kelvin. It had to be in the Kelvin unit. So what you do, you put on the side here, T1 is equal to this thing, T2 is equal to this thing. And that'll be 23 plus 273. And that'll be 296 Kelvin. It have to be in the Kelvin unit. They are 34 plus 273, and I say, well, I could work it out as I go in. And that's going to be equal to 307 Kelvin. If it's not in these units, you're going to lose almost all your marks, because they actually account for these two calculations. It could be 2 marks, or it could be 3 if they count the Kelvin unit as well. And you're just getting marks for the formula. You would get the marks for your N unit maybe, and that'll be it. So this kind of question here, this kind of screw over people. So going through this here now, make sure the thing in line, right? Okay. So you have P1 over T1 is equal to P2 over T2. What we're doing now, you cross multiply both of them. So the equivalent of that going to be P1 times T2 is equal to T1 times P2, or wherever you want to put it. So P1 in this case, 2 by 10 to the power 5, that's basically 2 with 5 zeros after it, 200,000 times T2, 307, that's going to be equal to T1, that's 296. Always make sure that your information is easy to see, especially when you're checking over, if you get time to check over. 296 times what we don't know, the final pressure. Now, using your common sense here now, the temperature increase. If you only remember the simulation that I did, temperature relates to increase in energy per molecule, average kinetic energy per molecule. So those molecules bouncing around faster and faster, they're hitting harder and harder, right? The walls, they're imparting more force. There's a higher rate of change of momentum as they're hitting. So, as we go in there now, multiply this, 200,000 times 307 is equal to 296 P2. So that's going to be equal to, we get some big numbers here. So you're going to get this number here, 614,000,000 is equal to this. So that means P2 is just going to be this divided by 296. And that will be your answer. 207,432.43 pascals or Newton per meter squared. You can also put this in standard form, 2.07 times 10 to the power 5 pascals. You don't necessarily have to, but sometimes they might ask. Easy. And this is how you get 8 marks here. So this is your typical pressure law or Charles law question. Yellow-Sachs law or Charles law question. The Boyle's law question, really easy. Now I wanted to show you one particular question here. And let me see if I can find it. I think it was, I know this question was kind of thunder for people who did come across the thing. Let's see if it's this here. Nah, that's nowhere. We'll see if it's this one. Alright, I'm gonna try one more. If it's not this one, Okay, look at this question here. This not the one, but this come a good bit of times, right? So for sure here, and also cheating. Describe how the graph of volume versus temperature in Celsius of a gas can be used to derive the Kelvin scale. So in this case here, this could also be pressure versus temperature, not just volume versus temperature, right? So in either case, the variations could come. And in this case here, what you want to do, although they never say draw the thing, all you have to remember this when you're writing CXC, right? Or CAPE or any exam. You think of what is the point of it. I know the exams is real bull, and the exams is real is real stress and thing. But basically, like when people watching a paper, what you're doing is you are proving to them that you know something. You are proving it. So if you have extra information, if you draw things, of course that's relevant and not stupidness. If you do that, that cannot do anything but help. You cannot lose marks for putting extra things unless they have a specific word limit like English. But you're doing this to prove that you know something, to prove that 2 years you went through this thing and I come out after 2 years and at least I know something. So even if they say describe something and you want to draw something and you have space, draw the thing. If you want to write a little extra about it, something that you probably read elsewhere and you know the thing correct, write the thing. The mark scheme is not something that is fixed, right? So sometimes that it might come across with things that they don't even know, and they will account for it, that they look it up and you know it, and they confirm it with a head marker and things like that. So like I might give you an example here. Vaping get introduced to the HSB syllabus, and vaping is something relatively new. People only start vaping like 10 years ago max, maybe a little more, but the long-term studies and things still coming out. So they ask about what is the impacts of vaping and all kind of thing. The typical things is that people just build up a fluid in the lungs. You have you have popcorn lung, you have destruction of the alveoli or deterioration of the alveoli. But only just the other day, it had a study come out that it actually could, because the nicotine could highly impact people who already have arrhythmias or abnormal heartbeats. Or, it could actually contribute to cholesterol buildup with atherosclerosis. So, even though that might not have been in the mark scheme, because they would have devised that mark scheme before the study, if you write it and you just write the things that you read about it on the proper parts of the internet, they will take it into account. The whole point of the exam is to prove that you know something. To prove that you know. Show them that you know something. Even if you had to guess the thing, don't leave the thing blank. Just write stupidness, waste the time. Prove that you know something. So in the case here where they say describe and you want to draw your thing, draw your thing. So back to the question. The volume of the gas. So in this case here, this is the volume versus temperature scale in degrees Celsius. Of course, well, all you would know that if you was to plot volume versus temperature, and it would be a directly proportional relationship in Kelvin, but in Celsius, what will happen here is that it will still hit 0, but that 0 here is not going to be 0 Celsius. It's going to be 0 Kelvin, because minus 273 degrees Celsius is equal to 0 Kelvin. You basically can never have a negative Kelvin number. And this here is equivalent to absolute 0. So the volume of the gas is 0, or the volume of the substance, you could say, is 0 when the temperature is equivalent to minus 273 Celsius. So since volume is directly proportional to temperature, it can be said that the volume of 0, right, when the temperature is equivalent to 0 Kelvin, when the pressure of gas is not changed. So this here shows that this, a lot of times when this comes, is very, very badly answered, because people don't think to draw the thing and then explain. They think to write and explain the graph. Of course, plenty of people in the Caribbean bad at English. So when they write, and it is being nonsensical. And from this here, this is usually segue into define the mathematical relationship between Kelvin and Celsius temperature scales, and that's easy. Basically, because when you plot this line here and you also extrapolate the line and it touches negative 273, this would also be equal to the 0 point in Kelvin. So the Kelvin value will be the Celsius value plus 273. So the example 0 Kelvin is minus 273 Celsius plus 273, right? That's the lowest possible temperature it could have. Now, so in terms of gas laws, that's the kind of things that you want to do. Now, something that could also come is the general gas law, right? And this here is where you bounce up a little mathematical dilemma because of the size of the numbers when we're talking about that. So with gas laws, if you was to take the combined gas law, right? And we was to take this example here, right? And all I could work this out as I working it out. Let me say that we have this question here. Alright. Let me say that we have this question here. And in this case here, we don't have anything that is constant. We don't have pressure is constant, volume is constant, temperature is constant or anything. So how are we going to work this out? Well, this is the case where we need to use the entire general gas law or combined gas law. So P1 V1 over T1, and all I could work it out as I doing it, is equal to P2 V2 over T2. We're not going to cross out anything because nothing here is the only thing that's constant is the mass of the gas before and after the initial and final. So how we do this? The ideal gas has a volume of 150 cm cubed, so that's going to be V1. At a temperature at 300 Kelvin, the thing already in Kelvin, so we do need to convert it. And the pressure is equivalent to 76 centimeters mercury. That's like, in a manometer, they use millimeters mercury. So none of these here have to convert, and the reason why I don't have to convert it is because the units are the same before and after. This centimeters cube, well, we have to find the volume there. This is also in Kelvin, the final, and this is also in centimeters mercury. If you have one thing in Kelvin and the next thing in Celsius, you have to convert it to the common SI unit, which is Kelvin. If you have one thing that is cm and the next thing is meters, you have to convert it, right? Typically, you don't get that though. So how are we doing this here? So how we doing this is that what we have to do is just work it out as we was working on a normal thing. It's just we have more numbers to deal with. So the pressure is going to be 76. The volume is going to be 150. And the temperature is going to be 300. This is the initial. The final pressure is going to be 70. The volume is going to be unknown. So that as V2. And the temperature is going to be 320. Now from this, it's a little hard to judge whether the volume will be more or less because we have an increase and decrease in some values there. So in this particular case here, we are doing everything. So how we doing this now is that we're going to cross multiply this part above with this part here. So this will be 76 times 150 times 320. And then we're going to cross multiply this part here above 70 times V2 with the 300. Multiply that there. So basically 76. And remember, always show everything in your working. Remember, say what is the point of the exam? The point of the exam is to prove that you know. Prove that you're not stupid. They think you're stupid. You're going to prove that you know something. You're going to prove to everybody. You're going to prove to them. You're going to prove it to yourself. You're going to prove it to your parents. You're going to prove to everybody who's hate you and bring you down. You're going to prove that you know something in this thing. That you didn't waste nobody's time. So this is going to be equal to 300 times 70 times V2. So you multiply this, 76 times 150 times 320. And big number here, 364,800. And that's equal to, well, 300 times 70 is, me and a calculator for that, that's 21,000. And this will just be this number here divided by this. The 364,800 divided by 21,000. And yeah, we see XC SPY correct there, 173.71. And make sure you put your unit. Remember, your unit here is going to be meters cubed. No, not meters. Centimeters. Hold on there. Centimeters cubed. This is pretty much the hardest the thing could come. It can't come harder than this. The other things that they could ask is for ratios, and ratios easy. Ratios is just like they might ask, what's the ratio of V2 over V1? So if I was to calculate this here, again, that's easy. All you have to do is put the volume, the final, the 173. It is 3171, sorry, and divide that by the initial volume, which is 150. And when you divide that, the ratio is 1.16. So that's like the only other thing that is really asked about it. What does this ratio mean? This means that the volume, the final volume, was 1.16 times bigger or had a 1.16 times increase compared to the initial. That's basically what it means. It's kind of like relative density. So I'm still looking for this particular question, you know, just now. Let me see if I can find it there. This to do with gas laws, because I know when I was reading the little examiner thing for it, like it had real people who, you know, that they get, oh look at here, they didn't get through with it. Real ginger beer for real boy. Only play the game good. Alright. This is Jan 2016. So, if we look at this question here. Figure 2 shows a sealed flask which contains a fixed mass of gas held at constant volume. The question itself not hard, but I think it's the way in which they phrased it, all people got it wrong. So here you have a pressure gauge, a thermometer, a gas. In here we have a fluid being contained in, and that the heat is being absorbed by the fluid, which is then absorbed by the gas, causing it to increase. All that's just extra information. You need to know what the hell going on. You just look at the numbers. Right. So the question was this. Let's see if I could put that there. The question was this. They say when heated, the pressure, the temperature and pressure of the gas, my bad. The temperature and pressure of the gas increase is shown in table 3. So here you have the pressures, 1.1 by 10 to the power 5, 1.2, 1.3 and so on, and we have the Celsius temperatures. They wanted it to convert the things to Kelvin, which is simple enough. 3 marks, you just add, remember you add 273 to each one. That's easy. The next question is, what was the kind of chain up? They say, is the pressure law supported by this set of data? And to explain. So, let me explain here. So let me work it out and you all can work it out with me. Is the pressure law supported by this data? So I'm going to put the table here. Right, and remember the question here is the pressure law supported by this data? And this is 5 marks. Now, all you remember, say you could write the pressure law formula as P1 over T1 is equal to P2 over T2. Right? Basically, it means pressure and temperature are directly proportional to each other because the more heat they add to the molecules, the faster they move, the harder they hit, and the pressure goes up. But and the volume has to remain constant for this law to work, because basically it means that the whatever container it's in cannot expand, like how a balloon is expand. So how are we doing this? So a lot of people start off first by stating what the pressure law is, right? But how are you going to support the data? So the pressure law states that at constant volume, pressure and temperature of a fixed mass of gas is directly proportional. So that there will give you like 2 marks, right? But how do we support, how is it supported by data? Now remember, you could actually write this formula. This P1 over T1 is equal to P2 over T2. You could also write this formula like this. P over T, once they are complementary to each other, once you divide those two, that is going to be equal to a constant K. And this is where a lot of people forget that you can actually rewrite this formula like this to have a constant. So what you're going to do is you're going to divide the Kelvin temperature, the pressure, by the Kelvin temperature for each one. I see somebody done get through it there. We main man there. So 1.1 times 10 to the power 5. So that's 110,000. And divided by 308. So you're gonna get 357.14. Right? So when you divide that there. So remember that? So this is the constant, 357.14. Now you have to remember now that this here relates to the ratio of the pressure to the temperature, right? Now if this gas obeyed the pressure law, right? If it was a gas that supported that means that all these other parts here should also give you the same constant. So if you was to do it for this, for example, 1.2 by 10 to the power 5 divided by 3 to the 6, you're supposed to get the same thing, which will be 357.14. And our last set of data here, same thing. I say it's not a hard question, but a lot of people get stumped by it because you usually don't go through it. You might go through like one example in school and you slip away and you forget about it. But if you was to divide 130,000, 1.3 by 10 to the power 5 divided by 364, you'll get the same thing, 357.14. So what does this say? This is the evidence that you're going to use to support this data. So let me show you here what the answer would look like for this. So the answer would look like this. So if you want to get your full 5 marks for it, the pressure law formula, so you could write it in words. The pressure law formula states that, as somebody put in the chat there, the constant volume, the pressure and temperature are directly proportional to each other in a fixed mass of gas. Right? The mass had to be fixed too. And this is going to give you, if you write the formula, P over T is equal to K, a constant K. So using P over T for the 3 data sets, 1.1, right? And you get 357.14, 357.14. You need to know how to write so good. You just provide the numbers, provide the evidence, do like you're doing in court, and you're going to lose a case and be like, there's the evidence right here. We get through. And then you just say, since the K value is equal in all 3 sets, that means that it is constant. That means that it obeys the pressure law. The pressure law is supported. And that's basically what happened in there. Easy. So that's the pressure law. Now, you have anything in particular they would want to go through? Because I think from these, honestly, I find from these broad topics, all they kind of get away. All they have no specific heat capacity, or they have no, I mean, all they have circuits and things, but they have no magnetism and transformers. Or they have no refraction and refractive index. The other things like sound and I mean, those things kind of basic, I find, but if all you have anything in particular, I could go through it. So lenses. Well, lenses radiation is not two things, you know. Let me start with lenses. Alright, let me start with that. And what they're going to do after CXC, or they're going to play some games. Because if all they're playing some games, all they know which one all they have to start with. Raid Shadow Legends, one of the biggest mobile role-playing games of 2022. It's totally free. Almost 20 million users, 10 million enjoying Raid over the last 6 months, and it's one of the most detailed models and environments. Silky, smooth, 60 FPS, animations, all the champions, you change your strategy and your buff and your debuff and your abilities, dungeon bosses, all them nice things, man. When all they done in exam, all they go play some Raid Shadow Legends.
God, Steve.
Only take 5 minutes. When we come back, we'll start circuits and then we'll do lenses. Well, I get a little fright yet. Oh, let's probably look at this. Which one would have been the worst? It's really the worst. Fail maths, you go on through it. You can't get nothing with this. Alright. Let me start with them. Let me start with them circuits there. Alright, just now, Alright. Let me go through some basics there. Let me go through some basics with these circuits, right? Let me start over. Let me go through some basics there. Let me say. Let me have normal circuit, normal series circuit here, right? Let me go through the theory with all it. We have normal series circuit here, right? So we starting back with, wait now, let's make sure everything, music too loud, everything good? Let me know if it's too loud or go low it. Alright, so you start there. Alright, that's now, I think we're okay. Alright. So let me say that here we have a group of batteries. Right? And we just doing like a typical series circuit. So we have a bulb here, a bulb there, right? We have switch there, there the bulb, right? That's the bulb. And there's a series circuit. Let me put our next bulb and done, yes? Right. We have a next bulb there. If we label these bulbs A, B, and C, right? So just going through this normal again. Let me say that this group of batteries here, this is 12 volts, right? And hold on, let's double checking something. Yeah, everything look good, right? And let me say that this here is a power resistance to each one. This is 2 ohms, this is 3 ohms, and this is 1 ohm, right? A is 2 ohms, B is 3 ohms, C is 1 ohm. We have an ammeter here, and we have a voltmeter connected here. The voltmeter like this there. So I'm going to slide this here. Now, here we have your typical series circuit question. Not hard at all, so we're starting out simple and we are going increase in complexity, right? Now, what if we had to find the total resistance? Well, that's easy. You just have to say the total resistance, the total resistance going to be the sum of all three. So it'll be R1 plus R2 plus R3. Shucks, just now. The chat kind of again anyway. The chat pop out and it kind of just the right R3. So the total resistance is going to be R1. We're going to say that's A, so that'll be 2 plus 3 plus 1, and that's easy. That'll just be 6 ohms. Easy, yeah? So the total resistance, not counting the wires, because the wires actually have resistance, but at this level we don't count them. So I'm just going to put here the total resistance in series is going to be 6 ohms, right? Just for the sake of keeping the thing a little clean. Now, so everybody know how to do that. You just add the thing if it's in series, these 3 things in series. Now imagine now if I was to remove this bulb, that basically breaks the circuit, which means that the other 2 bulbs would not receive any current and thus would not light. Everybody know that. Now, you have to remember now that this is the positive end of the batteries and this is the negative end. Conventional current, if we're going by conventional current, which we usually go with, I explain that. Conventional current shows that positive charges flow from positive to negative terminals in a circuit, and this is under current electricity. Electron flow is the opposite. Electron flow shows that negative charges flow from negative to positive in a circuit. But I explained before, because electrons were discovered so late, only in 1897, and electricity was discovered in the 1700s by Benjamin Franklin, he say it was positive. He just say it was positive without knowing anything. But they find it was negative a little too late, so we use positive to negative. Now, in reality, it's really electrons that flow from negative to positive, right? But we don't use that. And it can get confusing, but that's the thing there. Now, what if we had to calculate here the reading on the ammeter, right? What if we had to calculate the reading on the ammeter? Well, remember, ammeter measures current. You might argue and you're wondering why I didn't count the resistance of the ammeter. Is because it's negligible, is basically 0, right? So we don't count that because it don't really add on anything, and that's useful because it doesn't impact the voltage and the resistance of the circuit. Now we say, and remember I say how to do this, write the full formula first. There's the Ohm's law formula, write that first and then transpose it. So you just parallel therefore symbol, V equal IR, so I is equal to V over R. So the total voltage is going to be 12 and the total resistance is going to be 6, 2 plus 3 plus 1. So that means the current is going to be 2 amperes. That's easy. So what does that mean? What does 2 amperes mean? What does that mean? Because if all you think about it, or you think about volts and amps and all kind of thing, what does that mean? So 2 amperes, let me explain what that means, right? So let me write down here that the current is 2 amperes. So 2 amperes means that this shifts, or this battery lets out or emits 2 charges per second, or 2 coulombs per second. What exactly is a coulomb? Well, if I had 1 electron, right? If I had 1 electron and there's an electron, and I had a huge bag of electrons, I had a whole set of them, basically 6.25 times 10 to the power 18 or something, or somebody could tell me, but it's a huge number. If I had a whole big bag full of electrons with basically billions and billions of electrons, right? Those electrons group together to form a single unit called a coulomb, right? And a coulomb is spelled like this, right? So it's called a coulomb. And the coulomb now is a bundle of electrons that we count them as 1 unit passing through the circuit, right? So 2 amperes means that 2 coulombs pass per second. So if you're charging your phone, for example, if you're charging your phone and you have a 2 ampere charger, or you have a 1 ampere charger, for example, that's not it. That means that 2 amperes could, go, 2 coulombs could go into your phone per second. So if you had a 9,000 coulomb battery, right? If you had a 9,000 coulomb battery, 2 coulombs per second would go into this phone, and it would take 4,500 seconds to charge 9,000 over 2. So that's why the formula for charge is Q is equal to IT. Because if you really think about it, the two things you need to charge your phone is current and time. Q is equal to IT. So coming back to the circuit now, we'll get to that in our timing. Coming back to the circuit, we just calculate that the current is equal to 2 amps, right? And we get that by saying V over R, which is 12 volts over 6 ohms. And the 6 ohms was 2 plus 3 plus 1. Now, what if now that they ask us what is the voltage, right? What is the voltage reading on the voltmeter? Now, the voltmeter is connected in parallel to whatever it is measuring. Now, this is because as opposed to the ammeter, remember the ammeter had a very small resistance, but the resistance of the voltmeter is very high. This is because the voltmeter needs only to take minimal amount of coulombs or minimal amount of current into this little pathway here. If it takes too much, imagine this, if too much electrons pass here instead of passing here, those bulbs won't light as brightly. It's kind of like if more cars come here than here, you understand? So it's kind of like if more energy come down here than go here, they wouldn't light as brightly. So the voltmeter is hooked up in parallel on a whole separate wire so that it doesn't disrupt the rest of the circuit. There's like, hey, all you fellas are just doing my job, you know. It's kind of like the man who come to, you know, the person who come to clean and hey, I'm just doing my job, you know. Don't study me. I hanging out in my own wire here. My resistance real high. I want to bother all the fellas there. I just recorded some voltage. That's why the voltmeter on its own wire hooked up parallel, because it doesn't actually it actually, if it was to hook up in series, it would draw way too much energy. Now, coming back here now. Is it stuck? Okay, so what if we had to calculate the voltage here? Well, we're going to say V is equal to IR, right? And the current, so this current here, 2 amperes, in a series circuit, or if the components are hooked up in series, the current is going to be the same throughout each component. So here is going to be 2 amperes, here is going to be 2 amperes, here is going to be 2 amperes once it's part of the series. Here going to be 2, here going to be 2, here going to be 2, and so on, right? Now remember, this wire down here with the voltmeter, minimal electrons go in here, so we're going to ignore this for now, right? We're going to ignore this one. Now, this voltmeter now is measuring these 2 bulbs here, right? So that's measuring those 2 bulbs, these 2. I'm marking it in green because that's the only things I connected to, and then connected to this particular wire here, right here. Now, so the current is going to be the same going into a component as it is coming out. That doesn't change because that relates to the flow of the coulomb, which is the flow of the electrons, because a coulomb is a bundle of electrons. Just think of it as a big bundle, a big ball of electrons passing through as a single unit. So this will be 2 amperes times the total resistance, not 6, but the total resistance of these 2 here, because you're only counting these 2. So the total resistance of those are going to be 5. So 2 times 5 is going to be 10 volts. Now, if these 2 combined are 10 volts, how much is this one here? Well, you could guess, because if this is 2 volts, if this is 12 volts, and these two is 10 volts, of course this one here is going to be 2 volts. It's going to be the equivalent of the total. So if I was to add the voltage of each bulb, it would amount to 12 volts. So I know this looking like a colorful vomit mess here, but that's basically how that works. So the voltage, basically, if you was to add all of it, the total voltage, right, will be the voltage of each component, the voltage of A plus the voltage of B plus the voltage of C, and so on. Whereas the current right? The current in a series circuit is going to be through each component. So the current IA is going to be equal to the current IB is going to be equal to the current IC is going to be to the current ID, and so on. So the current is not going to change, right? Once the components are hooked up in series. So that is not that's of course, if they hooked up in parallel, that is a whole different story. Now, let me try one that is a little different now. So let me say that we have this here, right? So here we have a typical resistor, a variable resistor, and that's it there. Here we have an ammeter, and they have a voltmeter connected only to this one here, and the current, sorry, not the current, the voltage we don't know, but let's say that the current here is 5 amperes. This resistor here is 3 ohms, and this resistance here, sorry, I'll put it as this. This resistance here is 1 kilo ohm, and this here is 2 kilo ohms. So how are we gonna work that out there? So what would be, well, this would be like a normal battery, nah? But let me just say that that's the thing, how much voltage would be in this particular power source here. So we find the total resistance. So the total resistance is going to be 1 plus 2 kilo ohms, and that they are going to be, we need to convert that to ohms. So you know, kilo means 1000. So the total resistance is 3000 ohms, right? And what now will be the voltage? Well, the voltage would actually be really high on this. So this wouldn't be a battery at all. So the voltage would be, use Ohm's law, V is equal to IR, which will be, the current is 5 and the resistance is 3000, and that will give us 15,000 volts. So I say this wouldn't be any type of battery. Probably Elon Musk probably invent something like that, you know. But this wouldn't be the typical kind of battery that we know. But this would be 15,000 volts or 15 kilovolts, right? Now, alright, that's a little better. Now you might be like, well, now I'm using this here as an example to explain why the voltage would be so high for such a high resistance. I want you to think of it like a car, and you have a car driving on a very rough road, right? So it's to understand what voltage means, what current means, and what resistance means. Imagine that you have a car. So there's your car is a little beat up. Oh shucks, just now. It's a little beat up little car there. Forgive me, I'm using paint. There's your car, and the road real rough, right? Rough road, right? So the road real rough, and basically this means that it has a high resistance to it. So think of it like this, right? If the road real bad, even if and especially if the road now start to go uphill and it real bad, think of how much energy you actually gonna need to actually overcome this rough road. In the case here, a high resistance. So typically a high resistance means that you need more energy to overcome that high resistance. So you need a higher voltage. So high resistance, typically, if you wanted to go the same speed, the speed in this case being current, so you could think of it like this, right? The strength is the voltage. The strength and powers is the voltage. The speed is the current. And easy way to think like that. Plenty friction, plenty thing to overcome. Nah, man. Right? So think of it like that. So what exactly is voltage? Well, voltage is this. If we have a coulomb, right? If we have a coulomb there, that's a coulomb, and we need a certain amount of energy to push that coulomb, right? So there's the push. We need a certain amount of energy to push that coulomb. And if that amount of energy pushes that coulomb, that will be the voltage. So we say that 1 volt is equivalent to 1 joule per coulomb. 1 joule per coulomb. So you could also write this as V, right? You could also write it like this formula here. V is equal, and remember, joules is a measurement of energy, and coulombs is a measurement of charge. So you could write it as V is equal to E over Q, or E is equal to V times Q. So that's basically how to derive that formula there. The more voltage is the more push that this thing going to have. So you could think of it like this. More voltage means more the coulombs are pushed with more strength and energy. Right? And this is why if you have push harder, the thing go faster. So typically we say that voltage and current are directly proportional, which means you raise the voltage, you raise the current, typically. So that's how we have that relationship there. Because, coming back here now, 1 ampere is 1 coulomb per second. 1 volt is 1 joule per coulomb, right? And if we was to combine those two, 1 coulomb per second times 1 joule per coulomb, which basically means current multiplied by voltage, and we was to cross off. Well, basically we'll cross off C here and C here when we multiplying. So this will be 1 joule per second. And if all you know anything about physics, 1 joule per second is equal to 1 watt. So this is why current times voltage is equal to powers. So voltage is strength, current is speed, and two of them combined, you get power, right? You catch powers. So that's why we get the formula here now. P, so the typical formulas you have to remember is V is equal to IR, P is equal to IV, right? Because power is going to be current times voltage, speed by strength, basically. And we could also derive this like E is equal to power by time, but since power is equal to IV, we could also say energy is IVT. Right? So those three particular formulas is what you have to know when calculating voltage, power, current, and energy in a circuit. So they're not hard to they're not hard to memorize, honestly, but is to understand what each thing means, is to understand what each quantity means. So as I say, imagine you have a question like this. Right? So imagine you have a question like this. You have a 9,000 coulomb battery for your phone, and them company give you a 3 amp charger. That's plenty. how long it will take you to charge your phone if it dead. I hear like a rumbling happening there, you know what happening there? Alright, so how long that'll take you? So that's why you're working it out here. So you're gonna say Q is equal to IT. Now actually remember now this 3 amps. 3 amps means 3 coulombs per second. And I'm sure if you just do, you need to use no blasted formula to work it out. If you know 3 amps means that the thing could put 3 coulombs every second in the battery. So we're gonna say Q is equal to IT, right? So T, remember we want to find for time how long it will take you. T is Q over I. So how long it will take you? It will be 9,000 coulombs over 3. And that's going to be 3,000 seconds. That thing going to take you. So you see there. And that'll basically be 1,000 minutes. So that's charge. As I say, charge is as easy as that. The rest of it is just common sense. You just need to understand what each particular quantity means, right? So let me look at parallel circuits now. So parallel circuits would be, I'm gonna draw like a simple one first, and then we'll go through this. So let me say we have a battery here, right? There's a battery, and we have one bulb here, and we have a next bulb here. And this is our, and of course you have a switch somewhere here, right? And let me say that this here is 10 ohms. This is 10 ohms and there's 100 ohms. Right? And the current for this is going to be, not the current, sorry, let me say the voltage here is, let me just say 60 volts. Right? 60 volts. So what would be, let me say we was to find what is the total resistance of the circuit and what would be the current in this pathway here. So I'm going to call this pathway A, and I'm going to call this pathway B. What is the current through each individual pathway, and what is the total current in the entire circuit? That's IT total current, right? So first of all, to work out parallel, you can't just add it like 100 plus 10 is 110. All you know that already, of course. If you know that, you're in trouble. So if you don't know it, best to pay attention now so we could see what's going on. So what we have to do is do the inverse of each resistance. And yeah, me and man correct there. P is equal to V squared over R. So we have 1 over RP is going to be equal to 1 over R1 plus 1 over R2 going down the road if you have more. You could also do it a next way. So we have 1 over 10 plus 1 over 100. And there's where your maths go come into play here. What you need to do is, let me have this a little smaller there. So I got a little room. 1 over 10 plus 1 over 100. And the LCM of 10 and 100 is going to be on the way, right? Oh man, this happening here, right? It's 100. Not the highest common factor, the lowest common multiple. All they who fail maths. 10 into 100 is 10. And 100 into 100 is 1. Right? So 10 plus 1 is going to be 11 over 100. So I wish I did use something that I didn't have to use the decimals with, but if you had to get the total resistance now, the total resistance is going to be the inverse of this. So total resistance is going to be 100 over 11. So when you worked out, well, that'll be 9 point something. 9.09. I'll put 9.09, yes. 9.09 ohms. So that'll be the total resistance of this. 9.09 ohms. So now, do you write that here now? So this is how you do this. Now, because we don't have any resistors over here, we're not counting anything that connected to the main power source, we could just keep it as that. So the total, the resistance in parallel is going to be 9.09 ohms. Now, what is the current? Well, the current now through A and B. So we're going through the theory here with this. Let me start here first with the current through A. So I'm not going to use the total resistance for this yet, right? So I'm going to go through this with the total current in A. So the total current in A, I am just going to use this one component here. And I'm just going to use 60 is the total voltage over 10, because that is the resistance of this pathway here. So the total current of that is 6 amps. And using this now, the total current of B, this pathway B. So what does B have in it? B has this bulb that has 100 ohm resistance. So I'm going to say 60 over 100, because it's I is V over R, voltage over resistance, right? And that's going to be 0.6 amperes. So if I wanted to find the total current, all I have to do is add each individual pathway. That's one way I could do it. So in the case here, I can, I'll make this a little smaller now. So I can simply add these two. The total current, this plus this, is going to be 6.6 amperes. All the loss, you do it for each individual pathway. So this is one way you could do it. This is one way. So if I was tasked to find the current through A and then the current through B, I can find it individually, and then I could simply add those two, and I can simply get the total 6.6. So how another way I could do it, since I already found the total resistance, I could do it like this too. I can say the total current is equal to the total voltage divided by the total resistance. So this is just the alternate way of doing it. So the voltage is going to be 60. That's the total, that's the voltage of this battery here. The total resistance is going to be what we calculate, 9.09. And if all it worked out in the calculators, 60 divided by 9.09, you're going to get 6.600 something. So 6.6 ohms. You get the same thing. So you could find the total current through each individual pathway, or you could simply just divide, you could use the same formula, Ohm's law formula, but use the totals. And so I'm just showing you two things you could do, because that's the theory behind it. So you could use the totals, or you could just find it through each individual pathway, and you're good to go with that there. So what if we had a question like this? So I'm going to show you a next voltage question here. A next circuit question, sorry. Alright. Let's now, let me just find the thing. Alright, give me that. Alright, let me just draw one and done, yes? let me say you have this here. So we go in, we're taking it up a notch here. Let me say that this is we circuit. Right. I'm gonna just put 1 day. I don't make it too difficult for people to give up on the feel that they go feel the whole thing. Alright, let me say that we have this circuit here. And just to simplify things, let me say that each one there has the same, let me say that each one has the same value, right? So all resistors here is, let me say 10 ohms, right? All resistors is 10 ohms. So we have 4 here, R1, R2, R3, R4, and we have this battery here. Let me say that this is, let me just say it's a series of batteries, and this is 120 volts, right? We have an ammeter here, and I won't put an next ammeter. Let me just say we have this ammeter here. Yeah, so you might watch this and you might get a little frightened, but what we have to do, as I say, when you get any circuit diagram, is to simplify the thing. So let me think about how much different pathways we have, right, in the circuit. So I'll color them in. So first we have this pathway here. We have this pathway that I color in pink, and I'm gonna call this pathway A, right? I'll put another common A, right? So you're gonna call that pathway A. We're gonna have a next pathway here that I'm gonna color in blue, and this pathway here we're gonna call this pathway B, right? So that's pathway B. Now R1 is on the same pathway, right? This is on the same pathway as the power source. So let me keep that in mind. This is in the same pathway with that. So we're not going to include R1 with these other 3 here, R2, R3, and R4. So R2 is on its own pathway, pathway A, and R3 and R4 are on the same pathway. Think of it like a road, right? There's a road. R3 and R4 are on this pathway here. So if we have to calculate the total resistance of this circuit here, how are we doing this? Well, we need to work it out not by resistor, but we need to work it out by pathway. So the total resistance of this pathway here, pathway A, and I'll put it in pink, this is 10 ohms. So because R3 and R4 are on the same pathway, these on the same pathway, these are connected in series. So I'll just put in a little S here to show that it's in series. So this here is in series. So the total resistance of pathway B, and I'll put it in blue here, the total resistance is going to be 10 plus 10. So the total resistance here is going to be 20. Total resistance here is going to be 20 ohms. I'll write that a little better. So it's to simplify the thing. So now we have fused this R3 and R4 into one value, right? 10 plus 10 is 20, and this one here is 10. So we're gonna find the total resistance of these 3 here alone, and then we're gonna add R1 to it separately because R1 is in series with the power source. R1 is not on a parallel pathway. So let me type that here. So R1 is not on a parallel path. He not on a parallel path, right? He not there. So he going to get counted separately because he in series to the 120 volts. Now, to work this out, I'm gonna choose a color there, and we're gonna calculate the total resistance of the parallel paths, the parallel paths, right? So this will be 1 over 10 plus 1 over 20 Alright, I know I kinda off base here. Alright, make sure everything fits in the one thing. So the LCM at 10 and 20 is 20. 10 into 20 is 2. 20 into 20 is 1. So 2 plus 1 is 3 over 20. Flip that, RP is 20 over 3. And the answer for that there is going to be, well, 6 and 2/3, I believe, but sometimes the maths just fail, right? So 6.67 ohms. So this 6.67 ohms is everything here that are circling. Everything there. That's the total of that there. So how we get the total resistance now is we just need to add this one here separately. So we don't count this as the parallel path because this one here is connected to the power source, as I said. So the total resistance, the total overall resistance is going to be 6.67 plus this here, 10. 16.67 ohms. I'm telling you, the thing does look scary. It does look scary, but you just have to know how to break it down. Think of it like, again, think of it like a puzzle that you have to solve. You just have to figure out the puzzle. Don't think of it like work. Don't think of it like an exam. It's a thing that they give you. Solve this thing. Show me you could solve this thing. Each little circuit is like a little puzzle that you have to do. And, well, what I give you there, that was like a hard, I mean, for CXC, that was a hard one. But all you might be fortunate to get something that is, you know, a little easier than that. So let me go through an example here. Let me go through one more example from a past paper, and hopefully we could get through good with this here. So I'm gonna give all you this. Let me show you this example here. This is from Jan 2016. And you all could work it out as I working it out. And they say calculate the following. Calculate total resistance, total current, voltage through the 3 ohm resistor, right? So I'm gonna label here, so I could work it out as I doing it. So again, the paper, you could label up anything that you want on this paper. You could draw anything that you want to help you figure out the question, because you're going to go into the exam room. You're going to go into the exam room, you're going to prove that you know how to do the thing. That is what they want from you. You're going to prove that you know, you're going to prove you know something, you're going to prove it to yourself, you're going to prove to everybody who didn't believe in you. Prove to everybody who say them going to fail, them is a failure, they're going to be a vagrant. You're going to prove to them that you know this thing. So, let me say that this is R1, this is R2, and this is R3. R1 and R2 are on their own parallel pathway. R3 is series. So these two, these are parallel to each other. And this one here, this is series. So if it is series, you don't count it as part of the parallel system. Of course, you add it as if it's in series. So you could think of it as this whole thing combined. This part here combined, this part here between B and C. That is one component. You could think of it as like one big component. So let me work out here the total resistance for R1 and R2. So this here is going to be 1 over Rp, so this for the parallel part, is equal to, of course, 1 over 1 plus 1 over 2. So this is not hard at all, right? LCM is 2. Still show you working. 1 into 2 is 2. 2 into 2 is 1. So 2 plus 1 is 3, right? And so that means that the total resistance in parallel for the parallel parts is going to be 2 over 3 ohms, which is 0.67 ohms. Take a look at it again before I move on. These two here in parallel, these two here in parallel, 1 over 1 plus 1 over 2. LCM is 2. 1 into 2 is 2. 2 into 2 is 1. 2 plus 1 is 3. Right? Over 2. But remember here we have to flip this. 3 over 2 represents 1 over Rp. So Rp will be 2 over 3. Right? So remember you have to flip it in the end. So what we have to do now to get the total resistance, the total resistance is going to be 3 plus what we got here, 0.67, which is going to be equal to 3.67 ohms, or 3.7 if you want to round off to 1. Why did I flip it? I flip it because when we work out for parallel resistance, we're working out for 1 over R. So to get for R, we invert it. So you have to remember now that 1 over Rp is equal to 3 over 2. So Rp will be 2 over 3 because this is 1 over R, this is the inverse. So summarize this day. The total resistance would be, so remember this was 0.67 and this was 3, right? So the total resistance was 3.67 ohms, right? So the parallel parts was 0.67, 3 is the series. Now what is the total current? Well, from here to easy. So what we're gonna do is V is equal to IR. I is V over R. So the total current is gonna be the total voltage. If you look at the diagram here, total voltage is 12. And the total resistance, which is what we just calculate, 3.67. So 12 divided by 3.67 right, and you're going to get 3.27. Well, they say if the switch was closed, if this switch was closed, so this will be 3.27. The question did say if the switch was closed. Sorry, I forgot to put that part. Right. So now what we want to calculate for now is the voltage through the 3 ohm resistor. Now, remember what I say, that the total voltage going into a component in series is equal to the total voltage coming out. So the total voltage through this thing here, this part here, there's all we have to do. V is equal to IR. The current is 3.27. And the resistance is 3. So that is going to be 3.27, shucks, I'm shipping this, times 3, and that'll be 9.81 volts. That is all it is to it. So if this is 9.81 volts, the remainder of the voltage is going into this parallel component here. But they didn't ask that, because the total is 12. So 12 minus this number, 9.81, that will give you the voltage in this parallel component here. And remember, in parallel, they share the voltage is the same per pathway. Not the current, but the voltage. That was a kind of tough one. Only one next one, or you want to move on to something else? Well, I mean, after this physics thing here all you have IT there. You know, all you could use all your IT skills in the future to, you know, to do a number of things. You have data security, you have website building, and of course, if you want to build a website, let me tell you where to go. Squarespace is the absolute easiest way to make a website. I use them for a few different sites myself. I basically buy that domain to be sure nobody else could. I didn't really have the time or need to create a fancy website. I just take about 15 minutes to throw together a landing page. It was incredibly easy with the Squarespace template, and in my opinion, at least, it looked great. Squarespace. Back to the session earlier. Alright, let me find one more day for you. Alright, I know it had a nice one here. I had a nice one here trying to find. Alright, that's not it. Thing is the 20th. Thing is the June. I should write down I should write down. I feel I should write down which which questions is what, Alright, that's let me check two more day and see. The stupid thing. I feel it's just for me to draw more and Oh, look at it. So this question here say let me switch to this thing. Right. So the question here say, and this is, I'm going to tell you the year, this is June 2015. I tell you, best places to dig up. Best places to dig up is about 5-6 years ago. And yeah, so typically you just see a pattern, you just see something, but you can't depend on that, you know what I mean? Alright, so the question here is calculate the reading of the meters shown in the circuit in figure 2. The meters meaning the ammeters, right? So the meters meaning this fella here, P, A1 and A2. When the switch is closed. I'm going to just take a peep fast to see how much marks this is. This is 8 marks. to calculate this is 8 marks. To calculate the readings on each meter. So again, when you look at a question like this, simplify the thing and do it by part. Don't do it by resistor, do it by pathway, right? So in this case here, we have a main pathway, which I'll mark in red, right? So this is the main pathway. So when I say main, this is like where the live wire would be. This is like connected and switch closed, right? This is where it connected to the power source. This is the main pathway. This is the mains. So then we have, it will divide. Now that's the main road that we're working with. So now we have this pathway here, which I'm marking in blue. There's a pathway. I'm calling this pathway A. And then we have this pathway here, which I'm marking in green. Music too loud. Right. So we have this pathway here in green. And this pathway here, we call it B. So what is A1 measuring? So A1 is measuring, I'm going to type it here. A1 is measuring the total current in the circuit. This is because it is connected to the mains. So this would be part A plus part B. A2 is measuring the current in only part A. Right? So, right, this is A2 here, by the way. This is A2. And this is A1. Now, so what we're going to do is we're going to work out first the total current of each pathway, right? So we're going to work out first what is the current through A and then what is the current through B. So we're going to start with A. So the current through A, let's say IA, is going to be equal to V over R. But that'll be the voltage of the circuit, so the voltage is 12. So that'll be 12 over the resistance of whoever is in pathway A. So that's 2 in this case. So 12 over 2 is equal to 6 ohms. Right? So this is reading, not 6 ohms, what shipping is that talking about? 6 amps. Right? So this is 6 amps. Now, pathway B is basically this resistor here and this resistor here. So the total of these is going to be, and I'll just type it here. So the total resistance is going to be 2 plus 4 because they're in series. And that's going to be 6 ohms. So the total resistance here is going to be 6 ohms. So that means the total current of B V over R, same thing. So this is going to be 12 because it's the same 12 volts because the parallel circuit receives the same voltage per pathway. So this is 12 over 6. And this here is going to give you 2 amperes. So the total here is going to be 2 amperes. So that means that the total current A1, so A2 is going to read 6 amperes and A1 is going to read 6 amperes plus 2 amperes is equal to 8 amperes. And as I said, I find that's the easy way to do it. It have that way, and then it have the hard way, which is determining the total resistance. Which way the current is flowing like this, positive to negative. So the current, I'll draw some arrows. The current is flowing like this. Positive from the positive end to the negative if we counting it as conventional. That's how the current is flowing. So, what if we were to do this the longer way? What if we had to calculate the total, right? The total current, but finding the total resistance first. Now remember again, this here is 2 ohms, this pathway, and this pathway here is 6 ohms. So if all you remember the answer that we got, it was, what it was? I forget, yes? It was 8? It was 12 over 2 is 6, 12, yeah, it was 8, right? So what we got before was 8 amps. Mine like it's slipping, right? So that was the total that we got. So if we was to work out the total resistance here, 1 over Rp is equal to 1 over 2 plus 1 over 6. Find the LCM of that, which is 6. 2 into 6 is 4, 4. 2 into 6 is 3. 6 into 6 is 1. So that is equal to 4 over 6. So 1 over R is 4 over 6. So that means Rp is going to be 6 over 4. And that's going to be 1.5 ohms. That's the total. And if we was to work it out using the total current, using I is V over R, right? I is V over R, which is the totals for each one. The voltage is 12. The resistance is 1.5, which is what we work out here. And that would also give you 8 amps. So, let's see, it had 2 different ways you could do it, which is using the total, right? Using the total resistance divided by the total current. Or you could just find the current in each individual pathway and then add it up. Depends on the circuit. But if you have time, what you could do is simply rework it 2 times and see if you get the same thing. But you might not time. Who knows? It's 2.5 hours to do all kind of thing. And that's pretty much it for circuits, but there's a few other things I would like to go through with you all with this. Just some theory things that didn't come in a little while, but let me go through it here with all you, just in case. And where are they? It have a few things that your teachers might have just skimmed through without you just kind of learn it and you just kind of forget it. It's nobody's fault, but sometimes it just pop up and people be like, "Well, I never learned that in school," but you did learn it. You probably just learn it for like 5 minutes. So, of course, you have to differentiate between, so current electricity means that you have to differentiate between direct and alternating current, right? And it's pretty easy. If you have to draw a graph for direct current, it just looks like a straight line, and this is because you have to remember up here is the positive part of the graph. So it's typically, a positive charge flowing, because conventional current is unidirectional, which means it only flows one way, positive to negative, and it has a mostly fixed value. And examples of DC sources would be like AA batteries, for example. AC is bidirectional, so this means that it alternates between positive and negative. So the values fluctuate as time goes by. And, this kind of segues back to waves here because it forms a transverse wave. I might go through that, I sure, but I find that easy. But alternating current results in like less heat losses because the values could actually go pretty high. In fact, when Nikola Tesla, he's kind of the one who, he didn't invent AC, but he popularized it. And when he competed with Thomas Edison, because they wired everything in DC, but then they switched, because DC now, the voltage is really low. But alternating current, you could, with the help of magnets and coils, you could actually raise the voltage really, really high. That's why now electrical wires could have like 100,000 volts and things like that, with the help of transformers and things. So alternating currents could have a range of values with very few losses. The other things here is rectification. Let me say my laptop or your phone, for example, right? Well, that has a DC battery in it, a direct current battery, which is a lithium-ion battery, right? But usually when you plug it into charge, it has to charge in an outlet, like a wall outlet. Wall outlets are alternating current. So what you would need is a diode, right? You would need a diode to convert alternating current, right? So this would be like an AC input here, alternating current into direct current, so that you could the phone could charge, because in order to charge something, the current has to flow forward and reverse. So a diode, what the diode does, the diode enables the current to flow one way but not the other. So in this case here, this is what you call forward bias, which means that it could flow this way in the direction where the arrow is pointing, but the current could flow this way, for example, but it cannot flow this way, right? So it cannot flow in reverse. Think of it like it have a little barrier that blocking the electrons. That's not really happening, but think of it like that. So a semiconductor diode allows flow of electrons one way, but not the other way. So if you was to graph it, your typical AC voltage, which looks like this, you have to remember one way is a positive and then the next one is negative. Instead, what happens is that the troughs get cut off, right? The troughs get cut off here, and you end up with just the crests of the wave. So this is what you call half-wave rectification, or just rectification you might see in physics. But this is when you use a diode. So this here, this is an alternating current here. This is an AC. And this here is a DC. But what you call it a rectified DC. Sometimes you get that, you don't know. And I say if the diode is reversed, no current will flow because it only allows one-way flow of a current. Think of a diode as a one-way street sign. Or it could go this way, but not this way. Right, there's a next thing that potentially could pop up, and you might have forgotten it, or you might have skipped it over when you was revising, but this actually falls under current electricity. A lot of people forget about this. The difference between primary and secondary cells. Main band as a good example here is like a valve. It allows flow one way but not the next way. That's a really good way to put it. Primary and secondary cells. Primary cells is like your AA batteries that you have in your remote control. They're not rechargeable. So they cannot be recharged. They typically have a lower voltage, like a AA battery, for example, has a voltage of 1.5. It has a higher internal resistance and charges flow from positive to negative. You should also know how to label the diagram. There's 3 things in particular you should know how to label, and I'll point them out here to you. Alright, that's now I'll point them out here. You should know to label the carbon rod in the middle, the zinc casing or the zinc can, and the electrolyte, which is different according to the battery. So the electrolyte is usually like a mixture of different like kinds of manganese or cadmium. It depends on the battery. But this, you have to know how to label those 3 things. A lot of people forget that they have to learn this. And when it does come, it'll be like, well, what the hell going on with this boy? But yeah, you have to learn it. So secondary cells, on the other hand, examples of this would be like a car battery, your phone battery, laptop battery, lithium-ion batteries, lead-acid batteries, and so on. These can be recharged, right? They have a higher terminal voltage. So, for example, a car battery would have about 12 volts, for example. Thus, it's basically the opposite, a lower resistance. And both positive and negative charges could flow. It's kind of like electrolysis in chem. I know we are doing no chem here, but it's kind of like that, where you have an anode and a cathode, and you have both different charges could flow, positive and negative. Whereas in a primary cell is really only one type of charges flow. In the case here, electrons. This one here, you have cations and anions. You don't have to know all the different things about it. You just have to know the differences between a primary and a secondary cell, be able to differentiate between them, and be able to label a primary cell. Be able to label the carbon rod in the middle, the zinc can or the zinc casing on the outside next to the anode, and the electrolyte that basically allows charges to flow between that carbon rod and that zinc casing there. The anode and the cathode and the anode basically. So I just, as I say, you never know. I have a feeling they'll come, but my feelings don't really mean nothing. So yeah. And let me see if it have anything else here. Right, these things here, these 4 current type graph, well, not really so much the electrolyte, not really so much that one, but the conductor, the lamp, and the semiconductor diode. You all should know how to draw these, how to explain why exactly the shape like that. You could find that in any textbook. I don't really need to go through it here. I'm not too sure if in my 2-hour-long video, which I covered the whole syllabus, if I went through there. I'm sure you can find it in your textbook or your notes. So yeah, these 3 in particular, the ohmic conductor, the filament lamp, and the semiconductor diode. You don't have to know logic gate, at least what they say in the broad topics, you don't have to know logic gates for your paper 2 at least. So, well, we'll take a 5 again before we start lenses. Okay, 5-minute break. All you decide which topic all you want to do after lenses. Let me know. Let me know topics and them easy. Yeah, I kind of went through radioactive decay. I mean, that I had. But I could go through our next example. Waves. Nuclear physics. I kind of went through that, but I'll go through our next example. What parts of mechanics come in? The only parts of mechanics come in I seen as forces. I don't know if I really had to review Newton's laws and thing. Alright. I'll do waves after lenses, and then we'll just kind of go through oh yeah, hydrostatics, that was something. Probably one of those. I'll go through our vectors example and you see. Alright. Let me start here with this lenses thing. Let me start here with convex lenses first and then concave lenses, right? Alright. Convex lenses, as I said, are thicker in the middle and thin on the edges. So if I had to draw a light beam, which is just a set of light rays propagating through each one, is very simple. First, so we can have it both ways. You can have it like this, which is a light ray that is parallel to the principal axis. The principal axis is a horizontal line cutting across the optical center of the lens. So if I have some light rays like this, and they refract in the middle here, the point at which those meet, this is called the this is called the principal focus of the lens, right? So for a convex lens, it's easy. It's just the points where they meet like that. Now, I saw a question that came about 2 or 3 years ago where they had the light rays like this. They had 3 light rays like this, and they wanted you to draw how and they had the principal focus being labeled, which was here, I think. And they wanted you to draw what the rays would look like after they pass through, the convex lens. Well, this one here that passing through the optical center, this remains undeviated. So this keeps going straight like this, right? That'll change. And I'm gonna shift this focal point a little bit here, because it might be more here, right? I'm gonna leave it there. This one here now, this is gonna go through the focal point. Actually, I'm gonna shift it back to where it was. Just to make the diagram look a little easier. So these rays always had to pass. This one will pass through the focal point here. So kind of like this, right? So I know maybe just pretend that they're touching here, just to make things easier. So the last one now, what will happen here is that, actually let me just find the question undone, because I feel I do it a little inaccurate here. So just give me a second here. I'm gonna find the actual question so I could show you. I think is either 2018 or 2019. I'm gonna find it there, and I could draw it in for you. It's not 2019, huh? Let me see if it's 18. Yeah. So we'll find the it's showing up some people's head. There's what it look like there. And there's how you have to draw it here. Now, here we have the focal point, and I draw it wrong there. It's not supposed to pass through the focal point, so it will pass through it will reach the focal plane below the focal point, right? And this first one here that coming down like this, this is going to pass through the center of the lens, undeviated. This one here will come like this. And this will pass through where the focal plane will be. The focal plane is a vertical line where the focal point is. So you see where the focal point is here? This will be a vertical line as the focal plane. So all of them will meet up at the focal plane. Hopefully this I come for you, but so this will meet up below where the focal point is, and this last one here will converge with these three. The butts reach, yes. Well, I could set as a mod in here to get rid of the butts. Last time we had a few butts. As main man up in here as a mod. And spy. These butts just come out, but is just reach. Up in all as moderator. Just get rid of anything that's be real annoying. Somebody to send them butts, and I just that's not me, eh? That's not me. Alright. So coming back to my example I was using here. So this will meet up with what we call the focal plane. Right? So the focal plane is a vertical line cutting across there. And then all we have to do is continue this ray. Let this one meet up there. And this one will meet there. And that's basically how they would converge. And as I say, is a type of question that has come. Sometimes it will be like just the straight thing that I draw before. So sometimes it will be like this. Hopefully it'll be like this if it come. Where you just have to draw the three converging rays meeting up at the focal point. Or the principal focus, same thing. And sometimes it's asked you to label the focal length here as well. So this would be the distance between the focal point, which is along the focal plane here, and the optical center. And this here is your focal length, and you typically write this as a common F. So if you have to draw it now for a concave lens, and if we say for the concave lens, we have this here as the focal point, and we have this here as the focal point. This is basically how this is done. What you are doing is you are imagining that the rays are coming out from this point going outwards like this. So let me say we have three rays. The first ray is undeviated, of course. The second ray is like this. And let me say the third ray is like this. So how do we draw a divergent? How do we draw it properly? Being that is usually asked you to draw it, but not really anything else. So how you draw it propagating outward, or basically diverging, is you do it like this. You start from the focal point and you extend it to go outwards like this, meeting with this ray. But this would typically be a dotted line because it's imaginary. So it'll be like this. And that's how it's drawn. In a hand, I mean, it has come for a lot of marks. Sometimes it has come for like 6 marks and thing. So hopefully it come because it's easy. But yeah. And of course you put little arrowheads to show what direction the ray is going. Same thing here. And that's how you draw it. It's as simple as that. I think everybody should know how to do that. The things that you should know how to label is the principal axis, I'll label in the TSPA, which is a horizontal line cutting across the optical center, focal point, focal length, and focal plane. And the focal plane is a vertical line perpendicular to the principal axis that cuts across the focal point. And those are the 4 things you really have to label. And I guess optical center, which is the center of the lens. So, easy. And how exactly do these lens questions work out? Now, we have real images and we have virtual images. But type there. Yeah, I'm gonna do the formula just now. But first, let me just do a basic diagram. And I say it's really just through convex lenses that is bring this for, right? So just now, let me get back this image here. Oh, shucks. And then I'll go through some lens formula questions. Right. So I'm not going to do it for the concave because that is barely common. But let me do it for the convex here. And we will work out here how these images look, what's the difference between real and virtual, and how to solve for focal length and image distance and things like that. Alright, we have our next bud there. Shut it down. There's a wholesome stream. Alright, so I'm gonna draw this a little longer. Okay. So let me say that this is our focal point here. There's the focal point. And there's the focal point here, which will be the same distance from the optical center of the lens, right? And we have different positions where our object could be. So we are going to represent our object as an arrow. So let me say that our object is here, which would be between F and 2F. 2F is just double the focal point. I wanted to draw that in. What would the image look like? Well, this is how you would draw it. So first, your first ray would go through the optical center of the lens. So let me say here's the optical center. And I'm going to draw a line coming down just to show this is where the ray be thinking. And the first ray would come through like this, come through the optical center. You don't really have to know how to draw it though, but I'm just showing you like what it means to be real and virtual. The second ray passes through the focal point like this, and basically where they converge you could do this, or you could even do a third one which is through this focal point, and then this here meets with this, but I ain't about to do that part. Now, see here where these two converge? Look at what's gonna happen here. So this in case you can't memorize the whole table with real and inverted and magnified and thing. This is where the image is gonna be. So you could actually just sketch it if you want. And this image, we could describe it as inverted because it's upside down. It looks a little bigger, so I'm gonna say magnified and not I measure it, and real. So what exactly real means in this case? So real means that the image is projected on the other side of the lens, basically opposite to the object. And how you know, how you can determine that you have a real image. In the case, remember this is the object, this is the image. How you know you have a real image is this. If the object distance is greater than the focal length, you're going to get a real image. Right? So remember, the focal length is this. The focal length is the distance between the focal point and the optical center. That's the focal length. And the object distance is going to be the distance between where the object is and the optical center of the lens. And typically you could write this object distance as U, or you could write it as a D with a small o. Both of them mean object distance. Typically you'll see U and V for image distance. So the image distance will be the distance between the image and the optical center, of course, right? But if it's projected on the other side of the lens, the opposite side to where the object is, that is called a real image. So let me show you an example of a virtual image. So what I'm going to do is I'm going to shift my object to be closer to the lens. So the object is going to come here. I'm going to put it here. So in this case now, what you're seeing that the object distance is less than the focal length. So that's going to give you a virtual image. So what's a virtual image? So a virtual image is like this. So first, let me draw here what this is going to look like. This is going to come, remember the ray will touch this plane here by the optical point, the optical center, pass through the focal point here. Now, what would happen to the other one? Remember, this one here passes through the optical center. These two rays here would never meet on the opposite sides of the lens. These two would never meet. So what we'd have to do instead now is that we would have to continue these rays but on the same side as the object. So we're going to continue them like this. So you're going to continue this one like this and this one like this. And because, you know, this is virtual, we would have to make it dotted. And where those two meet on top there, right here, this is where your image is going to look like. So your image is going to look like this here, and this is going to be an image, and this is going to be an object. Now, notice something here. This is not projected on the other side of the lens, right? So image is not projected on opposite end of lens. So this means the thing virtual. So you could describe this as, this would be like a magnifying glass. Magnified, virtual, and it's not inverted. So not inverted, you could say upright. So that's how, you know, that's basically how you just draw it. Now the last example here, coming back here, is what if I take my object and put it here over the focal point, and I was to draw what the rays look like. First ray goes through the center of the lens. Second ray goes through the focal point. Well, again, you're seeing what happening here. These two rays here, these two rays are parallel. So I don't know if anybody know what is called it when we have these two parallel rays, they would never meet. So in this case here, we say that the object is formed at sorry, not the object, the image is formed at infinity. And basically what that means is that the image will never form, but in physics and maths is never really say never. It basically means that the two rays will have to travel an infinite distance before forming an image, or the two rays would have to travel for an infinite amount of time before they ever meet or form an image. So it formed at infinity. That's basically what it means. And let me just do some examples here with working out for focal, like using the lens formula. But again, a lot of this is not tough at all. Let me see if I could dig up. Let me see if I could dig up a little past paper there. Alright, that's now. I think this come in the same paper I was looking at. Okay, let me look at this one here. And you all can work it out with me as we go. I'm gonna paste it now. And let us type out the rest. The next part says calculate the image distance if the object distance is 20 cm, and the third part is calculate the focal length. Okay, so this is how we're doing it here. Let's type out the 3S and done. So I need to have that thing hovering there. Calculate the magnification where a lens produces an image of height 3.6 millimeters for a 2.5 millimeter high object. Okay. Right. So this is how you do it. So to calculate this, the first one, we are gonna say, so for part 1, M is gonna be the image distance. No, sorry, that's not distance. The image height. So HI over HO, or you could say V over U. And this is going to be 3.6 over 2.4. And that's going to be equal to, if you work it out with me, the magnification of the image is going to be 1.5. All that means, and remember there's no unit for magnification. If you put a unit, you actually lose a mark. So the magnification is 1.5, which just means that the image is 1.5 times larger. So in the case here, I'm just going to write that here. M is equal to 1.5. Now, coming back here, calculate the image distance if the object distance is 20 centimeters. So how are we going to work that out? Well, there's two aspects to the magnification formula. So we're going to say, so remember I said M could be equal to HI over HO, but this could also be equal to DI over DO, which could also be written as V over U. And that just means image distance over object distance. So let's use for the distances now. M is DI over DO. So we want to find for DI. So this will be DI is equal to M times DO. And that's going to be equal to, the magnification is 1.5, right? So 1.5 times 20, if you're working that out with me, 30, 6 o'clock, 6 o'clock we're taking a break. We'll take our 1 hour break at 6 o'clock. So the image distance here is equal to 30 centimeters. So how do you calculate the focal length? Alright, so how do we calculate this should have an E here, the focal length? Well, we use this formula here. 1 over F is equal to 1 over U plus 1 over V. Right? So this is the formula here. Sometimes you have to rearrange it to find for V. In this case here, that asks focal length. So we're just using that. So this will be 1 over, remember the object distance. The object distance is what we calculated. Oh shucks, this will be, no, sorry, the object distance was here, 20 centimeters. The image distance is what we calculated. And what is the LCM of these, of 20 and 30? So the LCM of this is going to be 60. Think of the lowest number that both of the highest, the lowest number that both of these could go into. 20 into 60 is 3. 30 into 60 is 2. 3 plus 2 is 5 over 60. So F is going to be equal to 60 over 5. Same way we was doing with resistance. And that's going to be equal to 12 centimeters. And that's how that's basically how it's calculated focal length. So let me give one more example on how to do this. So I'm going to just do one with just using the formula alone, and after that we'll take a little break. Calculate the image distance for a convex lens of focal length 8 centimeters if the object distance is 12 centimeters. Again, it's the same thing over and over. So this is how we'll do it here. Same formula. 1 over F is equal to 1 over U plus 1 over V. But we're going to transpose for V. So remember, this will stay here. This will stay here, 1 over V. 1 over U going next door. We're going to get subtracted because it added on the side, so it's subtracted. So 1 over V is going to be equal to 1 over F minus 1 over U, FU. Alright, so 1 over F is basically 1 over 8. sorry, not plus, minus 1 over, and the object distance is, remember object distance is u, 12. That curve not real, boy. I don't know who tell all about that curve. That curve is not real. I telling you for a fact it is not real, because CXC is a criterion-based exam. It's not there to say this one better than that one, right? It's there to say that you didn't know this or you didn't know this. So it's not real. A grade 1 means you had outstanding performance in the exam. A grade 3 means you had a moderate performance. A grade 5 means you have a very limited performance. For example, if everybody do bad in maths, for example, right, and everybody get 50 out of 100, how you could give them a 1 and say, oh, they had an outstanding performance? It's not real. So hard luck day. Anyway, LCM at 8 and 12, 24. 8 to the 24, 3. 12 into 24, 2. That'll give you 1 over 24. So if 1 over V is 1 over 24, that means V is 24 over 1, which is of course 24 cm. And that is a day, really. So, let me take a break. We're taking a hour-long break. Or they go and eat and thing. Are you hungry too? So we'll come back here. We'll come back here 6:45 Trinidad time.
Geddes Grant Office World presents the award-winning Lanier copiers. Low in cost, high in performance, Lanier matches the copying needs of any size business. Call or visit Geddes Grant Office World for special introductory offers.
Rough play. Tough turf. This shoe will leather it through. Lakers leathers. Tough enough for the games people play.
Happy days when you shop at Cram Book Center, Tunapuna. Get 12 copybooks for $10, 16-inch flats for Toko Composite, Sanwa Junior and Senior Secondary, Eldorado Junior and Curep Junior Secondary. Cram Book Center, Eastern Main Road, Tunapuna, where good education begins.
It's the once-in-a-blue-moon clearance sale at Lim Choice. Get plastic toilet seats at $55, 10% off factory prices on paints. Cabinet knobs and hinges at 50 cents. Everything is on sale at Lim Choice. Once-in-a-blue-moon clearance sale. Western Main Road Center.
Barbecue, pit and pop on Charlotte Street. There we'll meet. The pit is hot, the pub is new. All kinds of food, barbecued. Smells good from the outside. It's the only one of its kind. Let's go inside. Barbecue pit and pub.
Opposite the old market, 33 Charlotte Street.
So there goes another satisfied customer. You've just got 3 days to get that car you've dreamed of at SP Motors' big used car flea market. Sale starts 10 a.m. daily on June 26, 27, and 28. Hurry to SP Motors. Fly over Chaguanas now.
It's bad guys versus good guys in giant-sized puppy sticker 6-packs from Sunshine Snacks. Get them for less than half the price with any 4 wrappers from these Sunshine Snacks or Lolita, plus $2 at any Batter store.
In my profession, staying in shape is very important. Regular exercise, good diet, and of course, stay fresh. That's how I do it. Stay fresh, low fat. My choice for staying in shape.
My answer to skin protection for the whole family, new Protex Skin Health Soap. Protex helps guard my baby against diaper rash and our son against cuts and bruises. Don't talk about my teenage daughter. Yes? She swears by Protex for skin blemishes. My husband, now he likes Protex because it takes away bacteria and the odor they cause. Of course, I love Protex too. It really helps against those little skin infections, leaving my skin the way I want it. Protex protects my family every day.
Out from the dark comes a strength that goes beyond expectations. Special old cask rum, smooth, mellow, blended in the tradition of Trinidad's finest old rums. Special old cask, the dark strength you won't take lightly.
Carpenters, come, come, come. Tonight you be licensed, electricians, run, run, run. Tonight you be licensed, nails and accessories by the store. Bulbs and light fixtures evermore. Paints and brushes just for you. Paint up your house, have it looking new. Tonight you be liars, working a lumber. Staff well, helpful, service much better. Hardware for support and get too. Tonight you be liars, is the place for you.
For great taste in sandwiches, start with a freshly baked Linda loaf, hamburger bread, hops or even bagel. And for quality cakes and pastries, Linda's are the best. Order beautifully decorated cakes for those special occasions, weddings, birthdays or graduations. And if you want that extra special, personalized touch, their friendly staff will decorate while you wait. Visit Linda's at 55 Western Main Road, St. James, or any of their 5 locations. Linda's Bakery, coming soon to Excellence City Centre in Port of Spain.
This is the season to be happy. Open up your eyes. Get great big savings on gift items when you shop at Pennywise. Get great prices and hair and skincare. It's for every size. Save on toiletries, lotions, and Christmas items when you shop at Pennywise.
Experience the grandeur of the cinema in the comfort of your home and watch the big screen come to life with sharp 25 and 27-inch remote control color TVs. These cable-ready, brand new sharp design sets will fill your living room with stereo sound, complete with closed caption, sleep timer, child view limiter, and more. Each TV set comes with the famous CTC Electronics 3-year warranty, so look sharp.
Clear for takeoff.
Aye, aye! A few days before Christmas, Casey brought for me Christmas gift packages, delightful party bags, ooh, and candies, and cosmic gum bulbs to decorate your trees. Casey Candy, you make life sweet for me.
First citizens, bankers in action. People like you and me share one vision. From the start, from the heart, to make a brighter day. It's the way we bring banking to life. First citizens, building a nation. People like you and me, we're first citizens.
Ready, get set, go! It's the ultimate driving machine, the KFC Bunny Buggy. Fast, fun, and only $3.99 with the purchase of a KFC Kids Pack and $1 Hop Dollar. Hurry, get yours today. Stocks are limited.
Come now, can you buy a real nice lady? What you say to say Say, senorita, I bring a cow. We can have milk for soul from now.
Who tell you I want a cow? If you know what's the fear, move a cow.
But darling, I was only trying to be helpful. Think about the convenience.
Convenience? Mister, this is convenience. Nicer milk powder coming straight from Holland. And you'll believe it straight from the cow. This is all that is used now.
These days you're really looking nicer and nicer.
Get yourself. Besides, take that cow back where you find it.
You can't please nobody, no. You self couldn't tell me nice to have milk powder?
Where is that mumbling there?
I said I didn't know nice to have milk powder.
Well, nicer have everything. This is nicer country.
Nicer is nicer.
For Mother's Day, give Mom a gift for good health and longer life from Modern Caribbean. Strong Magnetic Cup cures and prevents kidney and bladder stones, obesity and other diseases. Slimmer Belts relieves back and menstrual pains and slims the waistline. Massage sandals and shoes relieves arthritis, tiredness and improves health. Necklaces and bracelets relieves pain in neck, shoulders, wrists and more. Available at Modern Caribbean, Roundabout Plaza, Gulf City Mall and Mon Repo, San Fernando. Phone 653-0011 or 638-2682.
If you can dance, how long can you do it?
Yeah, the biggest dance-a-thon is on, so check the funky prizes to be won. Have some fun as you compete, but remember it's the clock you've gotta be.
Dance-a-thon 93 from Radio 95.
Caribbean Sound Basin, May 30th, 2 to 10.
Puff and Stuff for the freshest bread, the tastiest cakes and pastries, and delicious desserts. Kids love the delightful lunches. Check us for children's parties, meetings, and seminars. With a friendly and knowledgeable staff, Puff and Stuff is there for you. Say Puff and Stuff.
1993, dimensional, and life today ain't that conventional. So what we've got is quite intentional at Cole's Powerhouse. Our electrical range is sixth sensational. It's new, it's oh so conversational, and all our prices inspirational at Court's Powerhouse. Up to date and always fashionable, Court's top brands are international, and your choice is always rational at Court's Powerhouse.
Kids, here's great news from Royal Castle. Get a delicious Canning's Lolly absolutely free when you purchase Royal Kids Castle now. Better all over with your Canning's Lolly.
Are you serious about your investment? Let the Trinidad Cooperative Bank work for you. Your investment yields higher earnings with our fixed deposit. Rates are negotiable according to your deposit. Call us. We'll come to you to discuss and advise on your investment. The Trinidad Cooperative Bank.
Change your oil and you can be all in smiles, 'cause you can win 70,000 free miles. If you want a chance to win all this free gas, count on NP now and change your oil fast.
You know, Amanda's feel proud when you reach home and you have a nice door to open. A nice young sing door. Solid, secure, quality wood, beautiful young sing designs, carved doors, flush doors, doors with glass, solid panel doors, secure doors, and at prices everybody could afford. Yes, man, with a young sing door behind you and a young sing door in front of you, you and the whole family could.
Yes, it's open house and free stickers for all kids this Sunday at Carnival Expo. Bring the kids for Fun-Filled Day. There's Magic Fantasyland and Calypso Matinee at 4 o'clock. Open house, free stickers for all kids this Sunday at Carnival Expo. Admission free until 1 o'clock.
Want to know how to cross that bridge that separates you from the house of your dreams? Check with the Trinidad Cooperative Bank, now offering bridging finance for first-time builders. The Cooperative Bank at Charlotte and Duke Streets, Barataria, and Point Fortin.
The National Commercial Bank, we aim to give you quality service. Convenient locations to service your banking needs. Working specially to satisfy each customer, your affairs are handled confidentially and with empathy. NCB offers security, competitive interest rates, and added value for your money. Our wide range of banking products includes the unique Life Insured Savings Plan. The National provides state-of-the-art banking technology, including our 24-hour self-service automatic banking machines. All this and more at the National Commercial Bank, the bank to help build the country.
violet, tender juicy chicken. Miss Violet. Each and every bite is a shared delight of the zesty chicken. Miss Violet.
The National Gas Company transports natural gas, a vital resource for our nation's industrial development. Trinidad and Tobago's economic turnaround is in our pipelines. See the light.
There are some things that neither time nor distance can change. With Illusion, there's no time or distance.
Because a man never forgets a woman whose fragrance he remembers.
With Illusion, there's reality. Illusion, the sensational new perfume and deodorant for today's woman. When you need to keep an important appointment, when you need to keep your cool all day long, make your day one of long-lasting confidence with Rage. With Rage, you're silently ready for any situation. Rage, the deodorant cologne for men. She'll never forget you for it.
When your job calls for a lot of brawn and plenty brain,
Go for a gold, go for a gold, go for a Nutriment. Gold!
Nutriment Gold, it nourishes all the parts of your body.
When you need to lose weight, you exercise. When you need a garden, you plant. You need your telephone, so pay your phone bill. When you pay your phone bill on time, you're doing what you have to keep your telephone. So pay it, and don't cut your lifeline.
Serving people.
Telco.
In the offices, on the streets, in the shops, and in the factories, the wheels of enterprise begin to turn as the country gears for yet another day of productive effort.
Well, you know me ain't no housewife, but I know a good product when I see one. Well, all you don't know that a breeze box holding more detergent than some of them other detergent box. But what I really want you to know and understand is that Breeze is unsurpassed in cleaning clothes and making them smell good too. So don't get tired. With Breeze, you could see it clean and smell it clean all through. Still good economic sense. Don't doubt me.
I love the way you look in that blouse.
That's because I wore it when we met.
Really? But it looks so new.
Because I wash it in Softland.
What's Softland, Mommy?
Softland's a gentle detergent and I use it on all our delicate clothes.
Will you wash my nightie in Softland too?
I did it with my very own hands.
And it smells nice, too.
Softland. Tender loving care for clothes you care about.
Never before so much to see. Never before so much to do. Everybody will be at Caribbean Expo 88. See you at Expo 88.
Black in the raw, gold when refined. NP Super Lube, black gold. A supreme quality, high performance motor oil. Super Lube, only NP has it, so demand it. NP Super Lube guarantees protection for your engine. NP Super Lube, quality you can depend on at all service stations.
Now in Trinidad, an executive limousine service from Henry's Taxi Service and Car Rentals, 3 Damien Street. Just take the Roxy roundabout by Hamilton Street, telephone 23716 for Henry's executive limousine service. Chevys and Cadillacs, and over 30 years experience of driving top businessmen and politicians in total air-conditioned comfort. Get yourself ready for your next meeting or flight in a limousine from Henry's Taxi Service. 24 hours. Telephone 23716.
Anybody could paint if they use kaleidoscope. It's tough and durable like you, and top quality like you, and long-lasting and colorful like me. With kaleidoscope, anybody's a painter. You and all. Color your home, kaleidoscope.
Think of what you can do when there's a lion in you. Royal Extra Stout. Look for the lion on the label.
Drink something solid, solid. Drink Royal Extra Stout. Drink Royal Extra, solid, solid. Hey!
Get a fresh new deal. Now it's any Coca-Cola Premium of your choice with any marked crowns plus cash. Get basketballs, wraparound darkers, head and sweatbands, Coca-Cola t-shirts. Get your choice now. In exchange for crowns with any premium marked inside plus cash at any Delimas, all banner stores and Almondos Tobago.
It's a hit, it's a pop. Coca-Cola music.
Nestle sweetened condensed milk.
It's a taste that you never outgrow.
There's a toasted bun.
With a Mario's burger.
That's no secret.
There's lean beef. In a Mario's burger.
That's no secret.
There's fresh salad in a Mario's burger. That's no secret, no.
The secret is the sauce.
It's made with care.
That Mario's burger.
That's no secret. It's a short wait.
For a Mario's burger.
That's no secret.
It's a perfect meal. It's a Mario's burger. That's no secret, no.
Secret is the sauce.
Mario's?
Brilliant.
Dixie Cola now. Dixie Cola now. Dixie Cola now. Dixie Cola. Dixie Cola brings you cola in 16-ounce bottles. Cola you can use and use again. The plastic cap keeps it from going flat. Get with it, cause this is as good as it gets. Dixie Cola, now in 16-ounce bottles.
The grand finale of On Track, the most happening television program on air, videotaped on location at Club Platinum West Mall. On Track brings a countdown of the 5 hottest songs played in clubs throughout Trinidad and Tobago. This week we feature Kindred.
It's just a Trini vibration to African rhythm. You're begging for the music, so I reach to get you some.
Sister Run.
I'm a sister who can sing into a song, get down. Like a funky James Brown, my song. There's not one you can sweep to, so get a stand up and rock so you know what I can.
General Grant.
In the dance on the shot, boyaka, boyaka, they shut down, cause they shut car. Yes. In the dance on the back, boyaka, boyaka, holy papa, body part.
And Victorian.
Look, kick it up, nothing what I'ma do. I'ma take a mic and I'ma tell it to you. Be true, I'ma tell it to you. Get us every day, we have a brand new crew. And every time it come and top it from. Come on, come on, jump it down and round.
The grand finale of On Track this Saturday at 12 right here on AVM channels 4 and 16.
Come down and see for yourself just how we are beating high prices at Quartz. It's amazing what it does to people. You've never seen anything like it. Guaranteed low prices, easy credit, low deposit.
With the down payments cut down and low, plus the chance to be a Quartz Cash Accumulator winner.
So come on down to Quartz now. You'd be amazed. It's time to shop at Quartz.
To all them Magabottle boys, come out to the play scene. You see, don't you have one original 16 in the land? Drink up, drink up, drink up, drink up. All them youths them. Drink up, drink up. All them pussy them. Drink up, drink up. All them massive them. Drink up, drink up. When you put the massive on it up, your massive knob, massive 16 in the air, you just drink up, drink up. Drink up, drink up. With your massive flavor. Drink up, drink up. Original power. Cannons rule the scene, original massive 16. Drink up, drink up.
If you walk downtown, wouldn't it be nice if you could shop downtown? Some place where you could walk around, up and down, for everything conceivable under the sun. If you walk downtown, it's easier to shop downtown. We're right here at the Cool Salt Mall, the only place.
It have a smile out there, coming from right in here, coming from the soul of our shores, and you know that smile is truly yours. That smile come from you, and it come from me too. Keep it flying forever, because that smile is truly yours. We gon' fly that smile, with pride and style, with an engine that roars like a lion for a cause. Pee-wee, truly yours.
The fete is grand, with products from Angostura. Get your glass in hand and be part of this fiesta. Everybody drinking White Oak and tonic water, Angostura rum punch with hammers and appetizer.
Drink a rum and a punch a creamer, drink a rum.
Old Oak is the pleaser.
Drink a rum and a punch a creamer, drink a rum.
Royal Oak is the master.
Drink a rum and a punch a creamer, drink a rum.
Well, to get all your flavors,
drink a rum and a punch a creamer, drink a rum.
Angostura bitters.
Drink a
Merry Christmas, everybody from Angostura.
Drink a rum and a punch a creamer, drink a rum.
Geddes Grant Office World presents the award-winning Lanier copiers. Low in cost, high in performance, Lanier matches the copying needs of any size business. Call or visit Geddes Grant Office World for special introductory offers.
Rough play. Tough turf. This shoe will leather through. Lakers leathers. Tough enough for the games people play.
Happy days when you shop at Cram Book Center, Tunapuna. Get 12 copybooks for $10, 16-inch plats for Toko Composite, Sanwa Junior and Senior Secondary, Eldorado Junior and Curab Junior Secondary. Cram Book Center, Eastern Main Road, Tunapuna, where good education begins.
It's the once in a blue moon clearance sale at Lim Choice. Get plastic toilet seats at $55, 10% off factory prices on paints. Cabinet knobs and hinges are 50 cents. Everything is on sale at Lim Choice. Once in a blue moon clearance sale. Western Main Road, St. James.
Barbecue, pit and pub on Charlotte Street. There we'll meet. The pit is hot, the pub is new. All kinds of food, barbecued. Smells good from the outside. It's the only one of its kind. Let's go inside. Barbecue, pit and pub.
Opposite the old market, 33 Charlotte Street.
So there goes another satisfied customer. You've just got 3 days to get that car you've dreamed of at SP Motors' big used car flea market. Sale starts 10 a.m. daily on June 26, 27 and 28. Hurry to SP Motors, Flyover Chaguanas, now.
It's bad guys versus good guys in giant-sized puppy sticker 6-packs from Sunshine Snacks. Get them for less than half the price with any 4 wrappers from these Sunshine Snacks or Lolita, plus $2 at any Batter store.
In my profession, staying in shape is very important. Regular exercise, good diet, and of course, stay fresh. That's how I do it. Stay fresh, low fat. My choice for staying in shape.
My answer to skin protection for the whole family, new Protex Skin Health Soap. Protex helps guard my baby against diaper rash and our son against cuts and bruises. Don't talk about my teenage daughter. Yes? She swears by Protex for skin blemishes. My husband, now he likes Protex because it takes away bacteria and the odor they cause. Of course, I love Protex too. It really helps against those little skin infections, leaving my skin the way I want it. Protex protects my family every day.
Out from the dark comes a strength that goes beyond expectations. Special old cask rum, smooth, mellow, blended in the tradition of Trinidad's finest old rums. Special old cask, the dark strength you won't take lightly.
Carpenters, come, come, come. Tonight you be like your Simpsons. Electricians, run, run, run. Tonight you be like your Simpsons. Nails and accessories by the store. Bulbs and light fixtures evermore. Paints and brushes just for you. Paint up your house, have it looking new. Tonight you be like your smoking a lumber. Staff will help for service much better. Hardware for support and get too. Tonight you be like a city place for you.
For great taste in sandwiches, start with a freshly baked Linda loaf, hamburger bread, hops or even bagel. And for quality cakes and pastries, Linda's are the best. Order beautifully decorated cakes for those special occasions, weddings, birthdays or graduations. And if you want that extra special, personalized touch, their friendly staff will decorate while you wait. Visit Linda's at 55 Western Main Road, St. James, or any of their 5 locations. Linda's Bakery, coming soon to Excellent City Centre in Port of Spain.
This is the season to be happy. Open up your eyes. Get great big savings on gift items when you shop at Pennywise. Get fragrances and hair and skincare. It's for every size. Save on toiletries, lotions, and Christmas items when you shop at Pennywise.
Experience the grandeur of the cinema in the comfort of your home and watch the big screen come to life with Sharp 25 and 27-inch remote-controlled color TVs. These cable-ready, brand-new Sharp design sets will fill your living room with stereo sound, complete with closed caption, sleep timer, child view limiter, and more. Each TV set comes with the famous CTC Electronics 3-year warranty, so look sharp.
Clear for takeoff.
Aye, aye!
me! A few days before Christmas, Casey brought for me Christmas gift packages, delightful party bags, ooh, and candies, and cosmic gumbulbs to decorate your trees. Casey Candy, you make life sweet for me.
First citizens, bankers in action, people like you and me, share one vision. From the start, from the heart, to make a brighter day. It's the way we bring banking to life. First citizens, building a nation. People like you and me, we're first citizens.
Ready, get set, go! It's the ultimate driving machine, the KFC Bunny Buggy. Fast, fun, and only $3.99 with the purchase of a KFC Kids Pack and $1 Hop Dollar. Hurry, get yours today. Stocks are limited.
Come now, can you buy a real nice lady?
What can you say on Friday?
Say, senorita, I bring a cow. We can have milk for soul from now.
Who tell you I want a cow? If you know what's the fear, move a cow.
But darling, I was only trying to be helpful. Think about the convenience.
Convenience? Mister, this is convenience. Nicer milk powder coming straight from Holland. And you'll believe it straight from the cow. This is all that is used now.
These days you're really looking nicer and nicer.
Catch yourself. Besides, take that cow back where you find it.
You can't please nobody now. You self couldn't tell me nicer have milk powder.
Where is that mumbling there?
I said I didn't know that nicer have milk powder.
Well, nicer have everything. This is nicer country.
Nicer is nicer.
For Mother's Day, give Mom a gift for good health and longer life from Modern Caribbean. Strong Magnetic Cup cures and prevents kidney and bladder stones, obesity, and other diseases. Slimmer Belts relieves back and menstrual pains and slims the waistline. Massage sandals and shoes relieves arthritis, tiredness, and improves health. Necklaces and bracelets relieves pain in neck, shoulders, wrists, and more. Available at Modern Caribbean, Roundabout Plaza, Gulf City Mall, and Mon Repo, San Fernando. Phone 653-0011 or 638-2682.
If you can dance, how long can you do it?
Yeah, the biggest dance-a-thon is on, so check the funky prizes to be won. Have some fun as you compete, but remember it's the clock you've gotta be.
Dance-a-thon 93 from Radio 95.
Caribbean Sound Basin, May 30th, 2 to 10.
Puff and Stuff for the freshest bread, the tastiest cakes and pastries, and delicious desserts. Kids love the delightful lunches. Check us for children's parties, meetings, and seminars. With a friendly and knowledgeable staff, Puff and Stuff is there for you. Say Puff and Stuff.
1993, dimensional, and life today ain't that conventional. So what we've got is quite intentional at Cork's Powerhouse. Our electrical range is sick sensational. It's new, it's oh so conversational, and all our prices inspirational at Cork's Powerhouse. Up to date and always fashionable, Cork's top brands are international, and your choice is always rational at Cork's Powerhouse.
Kids, here's great news from Royal Castle. Get a delicious Canning's Lolly absolutely free when you purchase Royal Kids Castle now. Better all over with your Canning's Lolly.
Are you serious about your investment? Let the Trinidad Cooperative Bank work for you. Your investment yields higher earnings with our fixed deposit. Rates are negotiable according to your deposit. Call us. We'll come to you to discuss and advise on your investment. The Trinidad Cooperative Bank.
Change your oil and you can be all in smiles, 'cause you can win 70,000 free miles. If you want a chance to win all this free gas, count on NP now and change your oil fast.
You know, Amanda's feel proud when he reach home and he have a nice door to open. A nice young sing door. Solid, secure, quality good, beautiful young sing designs, carved doors, flush doors, doors with glass, solid panel doors, secure doors, and at prices everybody could afford. Yes, man! With a young sing door behind you and a young sing door in front of you and the whole family could.
Yes, it's open house and free stickers for all kids this Sunday at Carnival Expo. Bring the kids for fun-filled day. There's Magic Fantasyland and Calypso Matinee at 4 o'clock. Open house, free stickers for all kids this Sunday at Carnival Expo. Admission free until 1 o'clock.
Want to know how to cross that bridge that separates you from the house of your dreams? Check with the Trinidad Cooperative Bank, now offering bridging finance for first-time builders. The Cooperative Bank at Charlotte and Duke Streets, Barataria, and Point Fortin.
The National Commercial Bank, we aim to give you quality service. Convenient locations to service your banking needs. Working specially to satisfy each customer, your affairs are handled confidentially and with empathy. NCB offers security, competitive interest rates and added value for your money. Our wide range of banking products includes the unique Life Insured Savings Plan. The National provides state-of-the-art banking technology, including our 24-hour self-service automatic banking machines. All this and more at the National Commercial Bank, the bank to help build the country.
Go ahead and get Miss Violet, tender juicy chicken. Miss Violet. Each and every bite is a sheer delight of the zesty chicken. Miss Violet.
The National Gas Company transports natural gas, a vital resource for our nation's industrial development. Trinidad and Tobago's economic turnaround is in our pipelines. See the light.
There are some things that neither time nor distance can change. With Illusion, there's no time or distance.
Because a man never forgets a woman whose fragrance he remembers.
With Illusion, there's reality. Illusion, the sensational new perfume and deodorant for today's woman. When you need to keep an important appointment, when you need to keep your cool all day long, make your day one of long-lasting confidence with Rage. With Rage, you're silently ready for any situation. Rage, the deodorant cologne for men. She'll never forget you for it.
When your job calls for a lot of brawn and plenty brain.
Go for a gold, go for a gold, go for a Nutriment. Gold!
Nutriment Gold. It nourishes all the parts of your body.
When you need to lose weight, you exercise. When you need a garden, you plant. You need your telephone, so pay your phone bill. When you pay your phone bill on time, you're doing what you have to keep your telephone. So pay it, and don't cut your lifeline.
Serving people.
Telco.
In the offices, on the streets, in the shops, and in the factories, the wheels of enterprise begin to turn as the country gears for yet another day of productive effort.
Well, you know me, I no housewife, but I know a good product when I see one. Well, all you don't know that a Breeze box holding more detergent than some of them other detergent box. But what I really want you to know and understand is that Breeze is unsurpassed in cleaning clothes and making them smell good too. So don't get tired up. With Breeze, you could see it clean and smell it clean all through. Still good economic sense. Don't doubt me.
I love the way you look in that blouse.
That's because I wore it when we met.
Really? But it looks so new.
Because I wash it in Softland.
What's Softland, Mommy?
Softland's a gentle detergent and I use it on all our delicate clothes.
Will you wash my nightie in Softland too?
I did it with my very own hands.
And it smells nice, too.
Softland. Tender loving care for clothes you care about.
Never before so much to see. Never before so much to do. Everybody will be at Caribbean Expo 88. See you at Expo 88.
Black in the raw. Gold when refined. NP Super Lube. Black gold. A supreme quality, high-performance motor oil. Super Lube. Only NP has it, so demand it. NP Super Lube guarantees protection for your engine. NP Super Lube. Quality you can depend on at all service stations.
Now in Trinidad, an executive limousine service from Henry's Taxi Service and Car Rentals, 3 Damien Street. Just take the Roxy roundabout by Hamilton Street, telephone 23716 for Henry's executive limousine service. Chevys and Cadillacs, and over 30 years experience of driving top businessmen and politicians in total air-conditioned comfort. Get yourself ready for your next meeting or flight in a limousine from Henry's Taxi Service. 24 hours. Telephone 23716.
You can paint? I thought we getting a painter.
Anybody could paint if they use kaleidoscope. It's tough and durable like you, and top quality like you, and long-lasting and colorful like me. With kaleidoscope, anybody's a painter. You and all. Color your home, kaleidoscope.
Think of what you can do when there's a lion in you. Royal Extra Stout. Look for the lion on the label.
Drink something solid, solid. Drink Royal Extra Stout. Drink Royal Extra. Solid, solid. Hey!
Get a fresh new deal. Now it's any Coca-Cola Premium of your choice with any marked crowns plus cash. Get basketballs, wraparound darkers, head and sweatband bands, Coca-Cola t-shirts. Get your choice now. In exchange for crowns with any premium marked inside plus cash at any Delimas, all banner stores and Almondos Tobago.
It's a Coca-Cola music.
Nestle sweetened condensed milk.
It's a taste that you never outgrow.
There's a toasted bun.
It's a Mario's burger.
That's no secret. There's lean beef.
It's a Mario's burger.
That's no secret.
There's fresh salad in a Mario's burger. That's no secret, no.
The secret is the sauce.
It's made with care.
That Mario's burger.
That's no secret. It's a short wait.
For a Mario's burger.
That's no secret.
It's a perfect meal. It's a Mario's burger. That's no secret, no.
The secret is the sauce.
Mario's?
Brilliant.
Dixie Cola now. Dixie Cola now. Dixie Cola now. Dixie Cola. Dixie Cola brings you cola in 16-ounce bottles. Cola you can use and use again. The plastic cap keeps it from going flat. Get with it, cause this is as good as it gets. Dixie Cola, now in 16-ounce bottles.
The grand finale of On Track, the most happening television program on air, videotaped on location at Club Platinum West Mall. On Track brings a countdown of the 5 hottest songs played in clubs throughout Trinidad and Tobago. This week we feature Kindred.
It's just a Trini vibration to African rhythm. You're begging for the music, so I reached to get you some.
Sister Run.
I'm a sister who can sink into a song, get down. Like a funky James Brown, my song. It's not one you can sleep to, so get a stand up and rock so you know what I can.
General Grant.
In the dance on the shot, boyaka, boyaka, they shut down, cause they shut down. In the dance on the back, boyaka, boyaka, holy papa, the bar.
And Victorian.
Look, kick it up and let me what I'ma do. I'ma take the mic and I'ma tell it to you. It's true, I'ma tell it to you. Here's a segment here, we have a brand new crew. And every time it come and top it Cram. Come on, jump it round and round.
The grand finale of On Track this Saturday at 12 right here on AVM channels 4 and 16.
Come down and see for yourself just how we are beating high prices at Quartz. It's amazing what it does to people. You've never seen anything like it. Guaranteed low prices, easy credit, low deposit.
With the down payments cut down and low, plus the chance to be a Quartz cash accumulator winner.
So come on down to Quartz now.
Come, and you're cook yet, Aloma, what you gonna do? Don't worry, I organize.
I'm hungry like a dog, girl. I'm going to be just for food on that table for me.
You mean please?
Yeah, like your flavor very pot. Holy girl, this is a meal fit for king.
Yes, only the best corned beef for my king.
Corned beef? What corned beef is this, girl?
Rainbow corned beef, darling, rainbow corned beef.
Distributed by ADM.
Yeah, again, audio. Let me know volume good, music too loud. We're gonna start back with we're gonna go from well, we just do lenses, so we're gonna do waves, and then vectors and forces, and then what's the last thing? Hydrostatics. I think after that we would have covered everything. I mean, I will probably go through one more radioactive decay curve, just as an example, because I mean that's what we photograph. But it don't get any more basic than finding the points and minus everything. Real long. Okay. Sorry about that. that slide was doing your own thing. Yeah, sorry. I was saying before that we were gonna go into waves, and then vectors and forces, hydrostatics, and at the end we'll probably just do one more example of a radioactive decay curve as the bots come back. And that should be it. Hopefully by then all it should be a little ready. I will link up a whole set of notes and past papers and all kind of thing at the end there. But you could check the if you see it in the comments in the video when the live go up, check the community pages, the little community posts on them. I'll post a whole set of links there. All I have tomorrow basically to prepare. Alright. So first let me start with waves day. So alright. Take that way. Alright, that's now and let's go back a little bit. Think that okay. So number think that should be okay. Right. So going through the basics here first before we get into any questions. What is a wave? Well, a wave is a propagation of energy from one location to another. And this could come in one of two things. It could come in pulses. And a pulse is basically a short wave with no repeated oscillations. You could think of it like a heartbeat or a single ultrasound pulse that's used to detect distance in like the seabeds or something like that. But basically it's just one oscillation or even just part of an oscillation. A progressive wave is a wave that moves through a medium, transferring energy as it does. So a progressive wave is like if you're listening to the radio and you have a constant, or you're listening to me and you have a constant stream of radio waves and microwaves and all this thing coming towards you. Progressive wave would be like infrared and ultraviolet being released from the sun and coming to Earth. Basically, think of it as a continuous wave as it going through. So the anatomy of a wave, we have the wavelength and we have the amplitude, but let me use a simulation here to make it a little easier to see, right? So just now, let me see if I can switch to my display. All right. So I don't know how well this is showing yet, right? But here we're gonna create a wave here, a transverse wave, and the transverse wave basically is gonna propagate to the right, and we're gonna set it to oscillate here. So the transverse wave is going to propagate to the right. Propagate basically just means move, right? It just means move in a direction. But in the case of a wave, remember the wave itself, if you imagine this as a rope, the rope itself is not moving to the right. It is simply energy being transferred to the right. So we don't really say the wave moves to the right, but we say propagates in that direction. Propagate just means like the energy is sent in that direction. So in this particular case here, we could see that the source of the energy is this little thing here bobbing up and down, right? This particle bobbing up and down. And that is actually what is creating this transverse wave. So the wave is propagating to the right, and the displacement of the particles is up and down. So we say that because the displacement of the particles is up and down, that means that it is perpendicular to the propagation of the wave. The propagation is horizontally right, displacement is vertically up and down. So to differentiate between a transverse wave and a longitudinal wave, a transverse wave, the propagation is perpendicular to the displacement of particles, right? Now, how do we differentiate things between amplitude, frequency, and so on? Okay, so amplitude refers to how much energy is being deposited into the source. So we have, if I lower the amplitude, you'll see that the wave is not displaced as much, right? So the wave is not displaced as high or as low as before. So the maximum displacement of the wave has decreased if I decrease the amplitude. In the case of a sound wave, this would be like I am lowering the volume of sound. For a light wave, it is like, or a light ray, it is kind of like I'm dimming the light. It has less energy in it. So if I raise the amplitude of a wave, the source of the particles has more energy. It means that it has a higher maximum displacement. So if you think as if you have a water wave of high amplitude might be like a tsunami, for example. A high amplitude sound wave would be a very loud sound. A very high amplitude light wave would be a very bright light. It means that more energy is being deposited in the particles to be displaced. So the frequency of the wave, on the other hand, let me set the amplitude back down to a kind of standard here. The frequency, so if you look here now, too bad I can't pause it, but if we look at these parts on top here, these are called crests. These are crests here, and the bottom parts, these are called troughs. So if we was to take, for example, I'm gonna take a screen grab of this, right? I'm gonna come back here. We're paint by, right? So if I was to come back here, I'm going to screen grab this. See if this is showing. Alright, okay. So the amplitude is going to be basically the max displacement of this wave from the neutral position to the top of a crest, or from the neutral position to the bottom of a trough. Alright, so this is the amplitude. So the amplitude is not the whole length, right? It's just from the neutral position, the resting position, to the top of the crest or the tip of the troughs. If I was to mark off 2 points on this wave, right? So let me say the top of this crest and the top of this crest, and I was to connect these 2 points here, this distance here, this is a wavelength. And wavelengths are depicted as lambda, which is a Greek letter, and is kind of like a Greek L. Lambda is also used to depict half-life, by the way, but we won't get into that. But this means wavelength. Now, it doesn't have to be between 2 crests or even 2 troughs. It basically could be any 2 points that are in phase. So if we was to take any 2 points that are on the same position on the wave, right? So for example, if I was to take this point here, right here, this point going up here, and this point going up here on the same position, It's almost the same. And I was to connect these two, that distance would be the same as this distance on top here, and that distance would be the same as this distance down here. All of these here would be a wavelength. And even if I was to take this point here from this neutral resting point, and I was to count one crest, this is one crest, and one trough, this is equal to one oscillation. So this is one oscillation here. This is a wavelength. So all of these here, all of these blue lines that I've drawn, all of these here is equivalent to one wavelength. Now remember, wavelength is a distance, and thus wavelength is measured in meters. So you can think of wavelength as the distance between any 2 points on an oscillating wave that are in phase. So in phase means it means on the same position of the wave. So now, what is frequency and what is period? So let me come back here. So if we come back here to what is frequency, if I was to raise the frequency of this wave, right? What you'll notice here is that more waves are passing that point per second, right? Frequency refers to how frequently the waves propagate, or how frequently these oscillations are formed, or how many oscillations pass a point per second. So frequency is measured in hertz, and basically it means that is how much waves pass a given point per second. So if you have a frequency of 3 hertz, it means 3 waves pass per second. So you could also call hertz per second. So that is frequency. So this is a high frequency, and this is a low frequency. So low frequencies means that less waves pass per second. You'll also notice a next difference when I change frequency. When I change frequency, the wavelength changes as well. So when there's a high frequency, there are smaller wavelengths. The waves are closer together. That means that more waves pass a given point per second. They pass more frequently, thus the term frequency. If I have a lower frequency, the waves get further apart, so the wavelength increases. So you get less waves passing per second. So the waves pass less frequently, thus lower frequency. Easy way to think about it. Now, that is what frequency is. So what exactly is period? So let me use a graph here so that we could understand what is period. So if you look back here, what exactly is meant by the period and the frequency of a wave? This is something that comes up a lot, no matter if it's waves or even if it's electricity with an alternating current graph. Because remember, current, electricity coming. Typically, if you have an AC graph, you're going to get something with frequency or period. So the period is the time taken so it's a period of time for one complete oscillation. So in this case here with this graph, the time taken for this wave, so this x-axis here depicts time. So this will be the time for one oscillation. So this will be one crest and one trough. There's no need to really calculate it. And that there is the period, which is in this case here 0.6 seconds. And you can see it right here. So even if we was to take this point at different parts on this graph, let me say that if we was to start here, right? So if we was to start here, this here would be 0.3 seconds. Right? That would be 0.3 seconds. If we was to start there, and we was to count one trough and one crest, and this would end between 0.8 and 1, right? This would be 0.9 seconds. As this is the same thing as the 0.6. If you find the difference, 0.9 minus 0.3. That's the period of a wave, is the time. So easy way, period, think of it like pendulum, the time taken for one complete swing, the time taken for one complete oscillation, and that's the period. The frequency is the number of oscillations passing a point per second. So if you have to determine that, so let me use an example question here, right? So let me say that we have a wave that's looking like this. So I just making up a little question here, you know that. Making up thing, man. Yeah, man. Right, so let me say that we have, let me draw a little thing there, right? And here we're drawing a wave, a transverse wave, and there's the thing here. It's a little break up, but I nothing. And let me say that we only have we have these measurements here, right? So let me say that this is 1 second, this is 2 seconds, this is 3 seconds, this is 4 seconds, this is 5 seconds, this is 6 seconds. Easy, just using an easy example here. Now, what if they say that the wavelength of this wave is 3 meters, and the way to calculate the following, the way to calculate, I'll type here, the way to calculate frequency and speed. Speed is velocity, right? So how are we gonna do that there? Well, the frequency we at first we had determined was the period, right? So this is the time in seconds, I should say. In fact, let me be a little wicked here. Let me say that this is the time in milliseconds. Right? Let me be a little wicked here. This is the time in milliseconds. So what is the period of the wave here? The period is going to be one crest and one trough. Right? So basically this part here are highlighted in orange. I'll do that back. One crest, one trough. So that's going to be the period of the wave is going to be 2 milliseconds. Remember that's going to be 2 times 10 to the power negative 3 seconds, right? Now, which is basically 2 over 1,000, right? Now remember, sometimes it is for milliseconds and millimeters and thing I tell it to convert it, and that is be our mark. So that's the period of the wave. And if I was to put as a decimal, that would be 0.002, right? So what type that? So that would be 0.002 seconds. So if I had to calculate now the frequency is easy. We just need to use this formula. Right? Frequency is 1 over the period. Now if you had the frequency and you want to find the period, you could say period is 1 over frequency. So this will be 1 over 0.002, right? And your answer thus is going to be 500 hertz. So that means every second that passes, 500 waves pass. So 500 waves per second. That's basically what that means. 500 waves per second. So how do we calculate now the speed? Or we have the frequency already. How do we calculate the speed? So the speed now, there's two formulas you could use. You could use distance over time. But you could also use V is equal to F lambda. So we're going to use this formula here. V is equal to F lambda. And the frequency is going to be 500. And the wavelength is going to be 3. So in this case here, your answer is going to be 1500 meters per second. I know this whole thing looking like a big mess here, but this is like a typical thing that is come. Sometimes you have to transpose V equals to F lambda to find for frequency. Again, that's easy. Let me say that we have a question like this. Let me say a water wave. A series of water waves have a wavelength of 20 meters and travel at a velocity of, let me say, 60 meters per second. Calculate the frequency and period. Easy. Work it out with me as we go in. So, first, we're going to say V is equal to F lambda. You're going to say F is equal to, remember, say always write the formula first, then transpose, in case you transpose the thing wrong. So V is the velocity, and that's going to be 60 meters per second. Lambda, the wavelength, is going to be 20. So the frequency is going to be 3 hertz. Right? And the period is just T is 1 over frequency. So that's going to be 1 over 3 hertz, 1 over 3 seconds, sorry, which is 0.33 seconds. And that's that. It don't get harder than that, really. It's just knowing, again, it's just knowing how to manipulate the formulas, knowing which steps to take. So sometimes I could give you that and say solve a period, but you know you have to find the frequency first because they're interconnected. So remember again, the difference between the two is that the period is the time taken for one complete oscillation. Right? So period is a time, but frequency is a rate. So if always play games and thing, and you know the frame rate is 30 FPS or 60 FPS or 120 FPS or whatever, or you have different TVs that show that frames per second is literally hertz. It just tells you how many frames get shown by the TV or the computer screen or whatever per second. Of course, the more frames it has, the smoother it is look. And that's pretty much what frequency relates to. Except frequency is not just for games, of course. Frequency is for all kind of different waves. So, here we have a next worked example for period. The maximum audible range for a human is 20,000 hertz. So, just a little fun fact here, by the way. Well, you should know this. The range in which you can hear is 20 hertz to 20,000 hertz. As you get older, that is actually drop. Like that value is actually drop. Babies have it real, so they could hear up to 20,000 hertz. So when they hear like a phone ringing or alarm or some kind of shrill noise, they just hear it real plenty. So the thing is, when you actually whisper, so if you whisper like this, like if you're doing ASMR, like if you whisper around a baby, the frequency of the whisper is actually pretty high. So the baby actually more liable, if the baby is sleeping, the baby is more liable to wake up if you're actually whispering like this, because it actually is a higher frequency when it's a low amplitude because the volume low when you're whispering, but when you're whispering there's a higher frequency. So the baby actually would quicker detect that because you know they have a much higher hearing range. So if you're around a baby and they're sleeping and you don't want to wake them up, you have to talk in a real low voice, real low whispers, low voices. So because a lower what we say a lower frequency has less energy in it and so on, because actually there's less waves passing per second. So anyway, so calculate the period of the sound wave. So this is easy. Remember, it's just 1 over the frequency. So 1 over 10,000, sorry, 20,000. And you get 0.0005 seconds. Or you could just say this as, if we was to jump this backwards, we have 5 by 10 to the power of negative 5. Jump 1, 2, 3, 4, 5. Math's done. We are going to do that. Okay. So I already described this. High frequency waves have more oscillations per second. So there's a high frequency wave right here. And high amplitude waves are taller and have greater displacements. So this, for example, would be a high amplitude, low frequency, this wave here. And this would be high amplitude, but a higher frequency, which means that the waves are closer together. Easy. Sometimes it's asked you to draw a few oscillations of a wave if there's high amplitude, low amplitude, high frequency, low frequency. High frequency means it has more waves per second. Put them closer together. Lower frequency means that they further apart. Just put them further apart. Less waves per second. Right, we're going through all of this. Okay. So what is the difference between a transverse wave and a longitudinal wave, right? So I described it before, that a transverse wave, coming back to this here, a transverse wave is when the displacement of particles is perpendicular to the propagation of the wave. So if I was to draw, I'll come back here. If I was to draw a wave like this, right? So remember, the wave is propagating to the right, let me say to the right in this case, and the displacement of particles will be going up and down, and that means that they are at a right angle to each other. So in this case here, this represents the propagation of the wave. Spell that correct here. And this here represents the displacement of molecules or particles or whatever. And in this case here, they are perpendicular, so transverse, right? Propagation perpendicular to displacement. All you know this. Yeah, man. Longitudinal, on the other hand, is a little more complex, because we actually do have crests and troughs and things with a longitudinal wave. So let me show you here for a longitudinal wave, right? Let me just get, you know, since they shut down Adobe Flash, I just had to open a kind of weird program to open some of these things here, but well, let me see if I can get this to run there. Alright, that's now it. I might have to show a display. Alright, so if all you see this here, if you was to visualize a sound wave, this is a longitudinal wave. So what you're seeing here is, I'll make the speed a little lower. This is the actual wave here. And you can see that in this wave, we have no crests and no troughs. In the case here, we have parts that are closer together. So these parts here are more highly pressurized. So they're more compressed. So you can see them here, they're moving to the right. These are just simply called compressions. So these compressions here are where again, you have a higher pressure, you have a higher density of the molecules. So they're more compressed at these areas here. So in between these compressions, you'll see that the waves are spaced out a little further apart. These are called rarefactions. So now rarefraction, you exactly get anything wrong if you say rarefract. It's not fractions that rare. Rarefactions. Not refractions, not rarefractions. Rarefactions. So this is where the density is less, they're less compressed, and we boy, using a stylus, but the stylus kind of big. Right, I don't need a stylus with what I just do. Anyway, so there's a longitudinal wave, and the way in which we could, by the way, since amplitude, since we don't have a crest and a trough, if we was to raise and lower amplitude, it is actually depicted by the compressions being denser and the rarefactions being less dense. Look at it here. If I raise the amplitude, compressions become a lot denser and rarefactions become a lot less dense. So, what's the difference between this and this? So let me come back here. Transverse and longitudinal. So with this one here, a longitudinal wave, for you to create this wave, I'm going to show you this thing one more time. For it to create this wave, notice how the displacement of particles is this line on the end here. This is the source of the energy. This is what's actually pushing it here. So this here is the displacement of particles. It's going left and right basically when you look at this diagram. So if the wave is propagating to the right, and this is the displacement of particles here. You can see that they basically going in along the same plane. So whereas transverse, we had the displacement perpendicular to the propagation, and that it had crests and troughs. Longitudinal, on the other hand, the displacement is parallel to the propagation of the wave because they are along the same plane. Of course, examples of longitudinal waves, the main example is sound, right? So the main example of this is sound and some seismic waves. Seismic is earthquake, but don't put seismic, just put sound because you don't think you learn that at this level. So like some earthquake waves. Transverse, on the other hand, examples would be basically any electromagnetic wave, right? So basically any EM wave. And if you want an easy way to just now, I'm going to label the compressions and rarefactions here for you. So this is a compression. There's a compression. These ones are marking in blue. And these ones are marking in green. These are rarefactions. And so on. How you spell it? Compression. Rarefaction. Right, so these here, them is rarefactions. Remember, it is less dense at those points. These are compressions. The distance between any two compressions, the center of any two compressions, or the distance between the center of any two rarefactions is basically equivalent to a wavelength. So this is a wavelength here. So you don't have crests and troughs, but we use compressions and rarefactions to determine it. Now, I don't think all again the EM waves, you never know now, but if you want a quick way to remember it, electromagnetic wave spectrum, problem not coming. So just remember, rich men in Vegas use expensive gadgets. And this is basically the order from lowest to highest frequency. So what does that stand for? That stands for radio, microwave, infrared, visible, X-rays, gamma rays. I don't think all you get that though, but the rich men in Vegas use expensive gadgets. Easy way to remember it. I think it coming. It is usually get paired with transverse waves now because all electromagnetic waves transverse. Right. Is different types of transverse wave. They could ask for examples, they could ask you for 3 examples, I say, and we had to study the thing. So I just telling you. Yeah, I need to know. I don't think all you get any order, but they could ask you for multiple examples. All they fussing so much. All they should have never get enough blasted broad topics. Okay. So, you have to know about sound waves, right? And how exactly sound waves different from well, usually when you talk about sound, you relate it to light. And we say that sound is mechanical in nature. Right? So sound is longitudinal. We just described that. Longitudinal and mechanical in nature. So what exactly mechanical means? Well, it means that it requires a medium in order to propagate. It needs molecules to propagate. If all you ever watch a movie that's set in space and you're seeing 2 spaceships shooting each other, pew, 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 and you know, like an explosion and thing in space. Correct, eh? I was watching this shipping movie, was that Star Wars? The episode 8 or whatever, nah. Them drop bomb in a them dropping bomb in space as if space are gravity, right? Them dropping bombs from one ship to a next ship in the middle of space, right? The bomb and them explode like it have air and space. Typically, a lot of these movies just get away with having the space battles and things take place on within the atmosphere or within like some kind of cloud or gas or something, because sound needs to propagate, or it wouldn't make any sound whatsoever, explosions and things. So radio waves and things can still pass because those electromagnetic, but it sound cannot propagate through a vacuum. So if you ever hear about like a soundproof barrier, soundproof room or something like that, it's basically two pieces of glass or 2 layers of material with a vacuum in the middle, kind of like a vacuum flask. But sound it requires a molecular medium in order to transfer. And of course, the denser this medium is the higher the velocity, because it means that the molecules have to travel from molecules. It has to propagate through those molecules. So the more molecules is the faster it will travel. So that means sound will travel fastest in a solid, right? But slowest in a gas. Because a gas has the least molecules. Molecules are spread so far apart because the bonds are so weak. The sun don't make a sound. The sound is actually really some radio waves and things, and people could pick up them radio waves, but as far as sound waves have none of them things make sound. So let's see in the intro there when I had the comet coming through and blowing up everything. Well, That actually from Final Fantasy VII, but when the meteor was coming and blowing away, that can't happen, man, because it had no sound in space. So the physics intro was incorrect with the physics. Anyway, so we're talking about properties of sound, right? We typically talk about pitch and loudness. There's something else that could be mentioned called timbre, and let me see if I could find it. It has something called a tone matrix. It's quite cool. Let me see if I could find it. A tone matrix does depict timbre and harmony, and basically it is a compilation of different pitches and frequencies. Let's call it a 12-tone matrix. Let's see if I can find it. But it's a good way to depict. Okay. Find it here. And if you look here, right? So if I was to do this, I don't know if all you hear it. Right? And this would be an increase in frequency. Increase in frequency. And this would be decrease in frequency. But they also have the quality of timbre, which makes them harmonic. So it has a kind of harmony to it. So which means that with this particular tone matrix, if I was to actually put a bunch of random things together, you would actually get like a harmonic kind of sound. So this would be low frequency, oh okay, just now, eh? Hold on, let's see if I can get the volume on it. Bridget, ripple tank experiment usually comes in paper 3, but you usually don't have to worry about that too much for paper 2. Wait, am I right? I look like I know how to use a computer, brother. Let me get back to the work. I'll then call it the thing. Right. So pitch relates with frequency. And so a high frequency sound has a high pitch. That means that a lot more energy is in the sound there. Low frequency sound has a lower pitch. All you know this. Loudness correlates with amplitude. So loud sound, high amplitude. Soft sound, low amplitude. Easy. Echoes. So I'm draw like a real crappy diagram here for you, right? Back in 2010, 2011, or kind of thing, BP. Oh well, if we talk about BP, talk about this thing in Trinidad with them divers and them in them pipe and them. All kind of shipping does this happen with these oil companies, yes? But BP, it had a pipe, right? Pipe bus. So the pipe bus, and this pipe going on for miles, right? There's the pipe, there's pipe, pipe bus. Pipe bus tanker overflow, all kind of thing, right? And what we get there is a bunch of oil come out in the ocean. That oil basically spread everywhere. All this is oil. All our oil spread there, right? Now, how they could determine where the pipe bus? Nobody could swim down there. Trinidad might want to send people to swim down there and kill them, but that not happening. We're outside of Trinidad, right? Who knows? So it's pipe bus, and of course, where we're pinpointing here, there's where the pipe bus. So what they're doing? They're gonna send a ship, and that ship now going to come equipped with an ultrasound transducer. Basically, what you're gonna do is you're gonna send an ultrasound signal down to where the pipe is, and they're gonna see where the oil is the densest. So when that ship come now, let me draw a real ship here. So there's the ship. When that ship reach, ship won't look this ship more like the Titanic, yes? Ship won't look like this. Look, let me draw the thing like the Titanic, huh? There's the ship. Right? There's the ship have a few windows and thing. The ship might have a little flag. And what you're going to do is right. So what we're going to do is we're going to send a sound wave down to all these parts of the oil. So where is the densest? You're going to come down here. You're going to echo back up here. Right? And remember, is water and oil and thing it traveling through. So the speed of that ultrasound wave is going to get predetermined. So let me say that the speed of the wave is 1500 meters per second. Sorry about that, 1500 meters per second. And they want to find out what is the distance where this pipe bus. Now, you have to remember when this thing traveling down, it traveling down and it coming back up. So it actually traveling a distance down. So it's an echo. So the thing reaching down, it bouncing off the oily surface and echoing back up. So it actually traveling a double distance for it to move up. So if we had to work this out, what the ship would do is that it would determine the time it take for that wave to go down and come back up. So this is why we use double distance in this formula here for echo. And I'll see in all the comments here, was all this shippiness by Royal Caribbean? I sure that's a good work. I wouldn't want to do it because I don't want to suck up to nobody to get tips. You know, when they go on them cruise and them, the room and them forever clean, or they could keep all their room forever clean, them room for distance over half the time. But we're gonna use double because that one easier to remember. So let me put a little problem. Let me put this as a problem here to solve. Let me say that there's the problem here. Now type. The ship sends out an ultrasound pulse and receives the data from the echo, let me say 150 milliseconds later. If the speed of sound in water is 1500 meters per second, calculate the depth. So how we doing this here? Okay. So to calculate this here, right? So the important thing here is the time. 150 milliseconds, so you know you have to convert that. And the speed of the sound is 1500. So you're gonna say speed is double distance over time. Therefore, (2D) is S by T. So that's gonna be, what is it for how old I is, by? Or they could keep guessing. People just get out wildly wrong with me. Sometimes some people think I'm real old, some people think I'm real young. I could be either one. So the speed is 1500 times, so remember 150 milliseconds, so that's 0.15, so you have to divide it by 1000. 0.15 seconds, right? So that'll be the double distance. So when you work this out, 1500 times 0.15, that's going to be, make this out here, this stylus real big, boy. So that's going to be 225 meters. But remember that this is double distance. So that means you divide this by 2, and that'll be your answer. 112.5 meters. And that's the answer there. Let me do one more example. So this one here is a common example. So you might see this one pop up. In an experiment, Ravi stands 60, I don't know if this is work now. He stands 60 meters away from a wall and claps 2 blocks together 20 times. Chantal records the time for 20 echoes as 7.2 seconds. Calculate the speed of sound from this data. So, S, speed, to distance over time. So what is the time though? So remember, 20 echoes is 7.2 seconds. So let me work out there. Let me work it out there. So 20 echoes, 7.2 seconds. But we have one for 20 echoes. I want for 1 echo. So that's 7.2 divided by 20. Yeah, man. Make this a little bigger. 7.2 over 20 is 0.36 seconds is for 1 echo. So when you're working this out, it'll be 2 times 60 over 0.36, which is basically 120 over 0.36. It worked out. And you're gonna get 333.33 meters per second. So watch now. This is something that you should at least keep in your mind. The speed of sound in air, or the average speed of sound in air, is approximately 330 meters per second. So if all you know, you're calculating the speed of sound in air, and you get something that is not around 330 meters per second, if you get something that's wildly off from that, it's wrong, eh? You lose marks. The one probably go on. There's no curve in CXC. You become a vagrant, probably dead and dead alone. Won't get no job, right? So just remember the speed of sound in air is 330 meters per second. Probably have to work Probably have to go KFC to give you a stale aloo pie and stale soft drink to make you eat it off the ground. And you probably get cholera, dysentery, and you're dead on the toilet, and that is probably a day. So the speed of sound in air is 330 meters per second. Right? You hear that? You won't go mad from having no job, you won't get bounced down the road and become a vagrant, a dead vagrant. Okay. All right. And that's pretty much it. That's pretty much it for sound and waves. Because spectrum, light, and easy. So what was the next thing? Vectors. Vectors and forces. There you go. Curve is a myth. Curve is a big myth. Curve go on through, all they go on through. If all they feel it a curve, boy, that done, boy. All they have to do all their best. The curve is something that that is take away responsibility from you. You be like, I really do not fail this exam, but I feel everybody else failing us. So I feel I do good. That know how it is working. That know how it is working. That is not how it is work. That's not what a 1 and a 2 and thing mean. No curve. Sorry to break it to you. Alright. Right, so sorry, I was looking at hydrostatics. They're not hydrostatics now. Vectors and forces. Okay, so this is pretty basic. A scalar is a quantity that has magnitude but no direction. Examples is like distance, speed, area, volume, density, half-life, heat capacity, specific heat capacity, latent heat. All of these things really have no particular direction, right? So these things here are scalars. A vector, on the other hand, has both magnitude and direction. So these things here would be displacement, velocity, acceleration, force, and momentum. So I'll just give all a basic example here. Let me say that we have so imagine you're playing, I can't remember what year it was, but it was 2014 or 2012, wherever is the World Cup where Brazil real lost by. Get seven goal against them from Germany. So imagine we have a football field. And them Brazilians and them, there's a goal post there. There's a goal post there. And there's where the ball starts, right? It had nothing to do with Brazil and Germany, yeah? So this ball traveling all over the place. Yeah, boy. Go and come there, all there, you're running down the thing, real time pass, the thing can score, right? The thing going outside and thing that they kick it back, it have a kind of penalty and all kind of thing. Nobody can score a goal yet. So you pass all day, go on all day, you have to kick it and all kind of thing, and finally it end up in somebody's goal. So what this blue line represents, this blue squiggly line, right? This represents a distance, because this represents how much ground was covered. This is a scalar because there's no one particular direction that this has traveled. It has gone all over the place. Now, if I was to actually take the position between where the ball ended and where it started, and I was to draw a line between those 2 points, let me say this this green line here, this has one particular direction. That there is called a displacement. That there is a vector, because there's only one associated direction with how this ball has traveled. So the displacement has a magnitude and a direction. It doesn't count all this individual ground that has covered. So that is the difference between a scalar and a vector. Vector has one particular direction. A scalar has no particular direction, right? It could be moving in many all over the place, but it doesn't have any particular one particular direction. So what if you had to resolve two vectors, right? So let me say that we have two vectors that are like this. So let me use the example here. Somebody, let me say that we have a box, or we have a box here, and we have two people pulling this box, right? So let me say that we have one person pulling from the top of the box here, next pulling this way. And these here would represent two vectors. But it's easy. Oh, and this is a right angle to each other, by the way, right? So let me call this vector A, and let me call this vector B. And let me say what would be the resultant direction and angle at which this is being pushed. So, or pulled, I should say, sorry. So in this case here, let me just give some values here. Let me say that this is being pulled here with 20 newtons, and this is being pulled here 30 newtons. So you can resolve it simply by drawing a vector diagram using a scale. So you could say, for example, 1 centimeter represents 5 newtons, and this would be 4 centimeters tall and 4 centimeters high and 6 centimeters across. So you could come up with a scale and draw it. Sometimes I give you the scale, or you could solve it using just simple maths. So if you had to draw it, what you would do is that you would just simply complete this rectangle shape here. So you'd complete, remember this is basically half of a rectangle, how it is right now. So you just complete the shape here. And well, this would be dotted. And you simply draw the resultant, which I mark in blue. Right, so this is the resultant force, basically from one end of the rectangle to the other end. If you think of it as a triangle, it would be the hypotenuse of the triangle, and this here would be your resultant. So if you wasn't feeling to do it, I didn't actually ask you to draw it. But actually, I don't think I ever see a question where they ask you to resolve it through calculation, but I mean, you could very easily. You could say that the resultant is C, and you could simply say, well, A squared plus B squared is equal to C squared. We boy Pythagoras. So it's 20 squared plus 30 squared is equal to C squared. And that'll be 400 plus 900 is equal to C squared. So C is going to be the square root of 1300. And that will be 36.06 newtons, if you was to do it like that. Now, if they ask you for don't forget all the protractor and thing on the exam, because if all again a vector diagram, they will likely ask you to measure the angle at which is being pulled, the measure between either A or B. So usually it'll be between, let me say, this horizontal vector here and the resultant, and you'd have to measure this angle here. It really depends. That question could change in many different ways. So that is how you would resolve this particular vector diagram. So you have to remember now that this resultant vector is actually the sum of this vector A and this vector B. So that's the next thing that is asked you to remember, that vectors are basically, you could think of them as net totals of other vectors. So if you get a parallelogram, let me say that you get this particular example here. So you get, there's a vector here, And there's a vector here. You see that there's 30 degrees or so. Not totally accurate. But if you see that there's the vector, so you get something like this. So it's not at a right angle, basically. Don't bother to solve it with the maths. So what you could do is you could just draw it. So in the case here, you see that this represents vector A and this represents vector B. What you would simply do is draw the same distance for B. So I just gonna cheat a little bit and I'm gonna paste it. Right? So you draw the same distance B over here, on top here, and then you just connect end to end. Basically, you're drawing a parallelogram. Math's done. All you should know how to do this. So you're drawing a parallelogram. Make sure the thing good. You're allowed to be a little wrong, but try not to be wrong. Or you know the thing. Draw these as dotted lines because there's not actual vectors. And the resultant, same thing. Connect it end to end. Connect the thing end to end at the parallelogram. And this is the resultant. Of course, at this point here, you would have a scale, so you just correlate how much centimeters relates to how much newtons, how much meters per second or something. But typically, when you get a vector diagram, it relates to force, or it relates to velocity usually. They're not usually drawn to, but they will give you a scale. Either they usually give you a scale, but all you should know how to come up with a scale. Anyhow, but that's vectors. And vectors here relate to forces. So let me come back here. Pretty much vectors, you just have to know how to resolve it. If they at right angles, how to resolve it. If they're not at right angles, basically parallelogram. If you're how to define what is a vector, how to define what is a scalar. Give at least 3 examples of each one, or fill out a table citing which one is which. And you have to be able to say that the resultant vector is the net total of two or more other vectors. So, coming back here now. Oh, I guess the other things, these simple things is parallel and anti-parallel. So of course, if you have 2 vectors going in the same direction, you simply add them once they are parallel to each other. So 5 and 5 is 10 in this particular case. If they are opposing, you just say you subtract. So if you have 4 newtons forward, 20 newtons backward, you are supposed to be able to say, well, the sum of these two is going to be 16 newtons because we're in opposite directions. And so this 4 newtons is really something like -4, if you know what I mean. And it is going in the direction of the bigger vector, in the case here to the left. Simple. Primary, you get at a 10-year-old, get at a 1-year-old, you could do that. Alright. So the next thing under here, under forces, somebody could probably confirm with me, but forces, it doesn't necessarily have to be -16. If you have, once you have the direction of the vector, you should be good. Whether or not it's positive or negative, you can say 16 newtons left. Or 16 newtons, whatever. Once you draw the arrow, typically you represent it as an arrow, so you draw the arrow, so you don't need to put, Anyhow, so the thing here about weight, this is easy. W is equal to mg, and this simple example question: if an astronaut has a mass of 70 kilograms on Earth, what is her weight on the moon if its gravitational field strength is 1.6 newtons per kilogram? So 70 is her mass. The gravity on the Earth is 1.6 newtons per kilogram. You just multiply it, 112 newtons. On Earth, gravity is given as 10 meters per second squared, or newtons per kilogram. It is actually around 9.8, 9.81, 9.82. But you use what they say to use. If they say use 10, use 10. If they say use 9.8, use 9.8 for it. You use what they say. They usually give it as a constant. Now, our next thing, I guess, that could come mainly multiple choice is that this, like, well, her mass is 70 kg, right? On Earth. What is her mass on the moon? So her weight on the moon would change because the gravitational field strength changes on the moon. But her mass, because she's the same person, she's the same number of molecules, she's the same amount of matter as before, she would have the same mass on the moon, which is 70 kilograms. The mass doesn't change. So that's the next thing that you have to know about forces, right? I don't think center of gravity. I can't remember. Somebody make sure for me now if all that fall under forces. I don't know. So anyway, let me show you a simulation here with a force, right? And vectors. So they might actually couple the two in one. Yes, now. And this will, I guess, kind of segue into Newton's laws. So we really boy. Alright. Okay. Right, so I'm gonna put this up here. Okay, so take a look at this here. As I have it, and let me say that we have a box, right? And this box here, we push in this box, we are applying a force to this box. Right now, you can see that the applied force is the same as the resistant forces. This is friction from the ground, friction from air resistance, all kind of thing, right? So right now, we could say that the force forward is equal to the force backward. That would give us a net force of 0. So what exactly does force be? This man asking if you can use calculators. Wait, that's a. Oh. Let me explain this here. This man want to do long division in the exam. Alright, watch me. Whenever I get anything about forces, I'll remember this. No force, no change. No force, no change. No force, no change, right? You have no change in motion. You have no change in direction. You have no change in velocity. You have no change in acceleration. You have no change in size. You have no change in shape. You have no change for nothing, right? No force, no change. You need a force in order to impact a change. No force means no change. So basically, no force means the thing will keep doing the thing until a force is applied, right? This is by Sir Isaac Newton. No force means the thing will keep doing the thing until a force is applied. So basically the real thing that this means, right, on the first law, an object at rest stays at rest. An object in motion and an object in motion stays in motion at a constant velocity. That means speed in a straight line until an external or unbalanced force acts upon it. Right? So that was the first law. If something is moving, right? And let me come back to the simulation here. If something is moving, so right now, the net force, the sum of the vectors, you're going to see on top there is this little green thing. And you'll see what is happening here. The speed is actually going to increase. Of course, when speed increases, it accelerating. So look at what happening here if I was to equalize these forces. Basically, the sum of the forces is 0. Right? No force, no change. No force, no change. No change in motion, no change in direction, no change in velocity, no change in acceleration, no change in shape, no change in size. No change. No force, no change. So in this case here, an object will stay at rest. An object at rest will stay at rest. An object in motion will stay in motion until an external force acts upon it. So that external force could be a Lego the box and it just have friction to stop it there. That's the external force. To have no forward pushing force. So in the case here, right? So the thing accelerating. Right? No force, no change. The sum of the forces, 0, no change in motion. Same thing here. If I was to have no friction in the thing, I push that, get a little push. But right now, there's no force to stop this box from moving. Of course, this can't be on planet Earth. There's on planet Wayne that is happening. So right now, it have no friction. Imagine it have no friction. It have no gravity. It have no air. Basically, kind of like outer space. So what happening there is this box will keep moving forever until it comes across some kind of external force, some kind of unbalanced force. The unbalanced force could be it hit something. The unbalanced force could be somebody jump on it. The unbalanced force could be it fall along a hill. The unbalanced force could be somebody bounce it. The unbalanced force could be Wayne fall into it. It could be anything. But in this case here, once this thing this thing is like this and it has no forces acting on it, this will just keep moving forever. Forever, ever, 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 forever, ever, ever, forever, unless it comes across some kind of unbalanced force to stop it. Right? That is Newton's first law. If you also go up in space, if you ever see this movie Gravity, and there's the hardest of time space is repairing this thing, and you just see how the asteroids come and go, it just knock up everything. But remember, it had no sound in space, so I can't say because it had no sound. But it basically knock up everything. And who it was by Sandra Bullock, she get disconnected by the rope boy, and she just get pelt out into space. And she there going, had nothing to stop she. It had no gravity in space, it had no resistance forces in space, it had no air resistance or nothing. But anyway, that's Newton's first law. So Newton's second law, right? Newton's second law is this. Leave probably friction a little bit to stop this box. Newton's second law is this. Newton's second law says that force is equal to mass times acceleration. F is equal to ma. Basically, it means, so let me type it here. So that's the first law. Newton's second law, right, says that the harder you push the thing, the more the thing will accelerate, right? And the formula to depict this is going to be F is equal to ma, which basically means force is mass times acceleration. And if we was to put the unit, remember force is newtons, but it's basically kilograms meter per second squared. This is force, this is acceleration. If we combine those two, we get a newton. So 1 newton is equal to 1 kilogram meter per second squared. Mass times 1 unit of acceleration. So the actual definition I should put on here, right? Newton's second law. For a given body of constant mass, or unchanging mass, the force applied to that body is directly proportional to its acceleration. Or they could write it if you want, that's not my problem. What you gonna do? Spooing, make me get it wrong. You be drinking an about 20 years and if you tell, hey, they spooing, tell me, it's sad, you think you're pushing it. You sound like a madman, right? Anyway, so F is equal to ma. And this is Newton's second law. Basically, the more force they apply is the higher the rate of acceleration. And just to show you here with the simulation again, you'll see if we look at the speed, if the force is small, look at the net force there. You see that green arrow, that's the net force. You see the rate of the increase of speed or increase of velocity is not much. The more force I apply is the higher that rate of acceleration, the higher the rate of the increase of speed. Of course, now the man fall along and the thing is decelerating. So, this is what's going on here. The third law, which is the one that shows up the most, let me come back there. So let me just show you a basic example here before we move on. Let me say we have a car, right? There's the car. Vroom vroom. There's the car, right? And the car have a forward force sprang along. The car have a forward force at 1200 newtons, right? That's the forward thrust of the car. And the car on a road, the road might be a little bumpy, and let me say that the total resistance that the car is experiencing, which is like the air resistance, the roughness of the road, let me say that is 1200 newtons as well, right? So the forward thrust of the car, right? So there's the forward thrust. And this is the resistant forces. What the car doing? Well, remember I said, let me imagine that the car is going at 60. The car is an honest driver. So not honest, he a safe driver. 60 kilometers per hour. So what happening with the car now? Well, the net force is 0 newtons. But if only remember what I say, no force, no change, no force, no change, no force, no change. So what is car doing now? Small brain people will say the car stop because the net force is 0. But remember Newton's first law. The thing will keep tinging unless the force stop the thing. So in this case here, 60 kilometers per hour, this is going to keep going at 60 kilometers per hour, right? And there will be no change in that velocity. There will be no change in the direction. There will be no change in anything, the acceleration. So it will keep going at 60 kilometers per hour because no force, no change. So use our next example here now. Let me say we have now same car, spowing mobile, and forward thrust is the same thing. Forward thrust is 1200 newtons. But now the man driving on a road in Guyana, Pinal, South Trinidad. Oh God, it's bad. And now the resistant forces and the wind blowing this way, all kind of thing is a bad day today for the spowing mobile. So the resistant forces is now 2000 newtons. What would be, and this car is driving at, let me say, the same 60 kilometers per hour, right? 60 kilometers per hour. 800 newtons in the left direction, right? So what is going to happen to this car? Again, small brain people will say the car will suddenly go in reverse. So that obviously if the car going forward, right, and it hit a bumpy road, the car is going to fly backward. that's not going to happen. In this case here, a net backward force means that the car will decelerate. Remember, all of this links to not so much the direction, like while it is moving, it links to the change in velocity and change in acceleration. In the case here, if we have the force going backwards, it's going to decelerate. It's going to slow down, right? And that's basically how you could resolve these forces in order to explain motion in the case. So coming back to forces here now. You got net back force net. The car had to slow down and stop before it back. Right. So looking here now, forces enable masses to overcome inertia. And inertia is basically that feeling when you gear up and you're feeling to gear up. Is basically resistance to change, right? Inertia just means you need a certain amount of force in order. The thing not going to start moving unless something get to start moving. The thing not going to stop unless it get to stop. The word inertia actually means laziness. So the thing lazy, it needs a force to get to start moving or to stop moving. All matter experiences inertia. So forces enable masses to overcome that inertia. That is, they are able to cause a change in an object's acceleration, deceleration, direction, even shape and size, but it cannot change the mass of the object. So, forces are measured in newtons. We don't explain that. These are different types of forces. You should be able to, like, sometimes just give you a little table to fill out with like type of force or description of the force or example of the force. So these are the ones you should focus on: gravity and weight, friction, buoyancy or upthrust, electrostatic, magnetic, reaction, tension, centripetal, and nuclear. So again, I will upload this after so you all could see it for yourself, or you could read it tomorrow. I won't go through each individual one now because unless all yours real hell hard sleeping in class, or they're real going through if all you know what's that. So the next thing here is air resistance. Air resistance has to do with forces as well. So if we was to have a piece of paper and a rock, right? And both of them falling in air. So, well, which one is going to fall faster? The rock, right? So this is because the rock, let me say that this is the weight of, this is gravity pulling the rock down. This is gravity pulling the piece of paper down. The amount of air resistance, I'll upload it in the description of the video or pinned comment on this video after I go up. Some notes and past papers and thing I'll upload for you. So in the case here, the paper, because of its wide surface area, has much more air resistance to it. Now, if you was oh no. Okay. Okay. So in a vacuum where you have no air, maybe it's like on the moon, for example. So when one of the first things when they went on the moon, right, is that they carry a hammer and a feather. And well, there's after the walk on the moon, of course, right? They carry a hammer and a feather. And of course, if you also drop a hammer and a feather on Earth, the hammer will fall down first because, you know, we think it heavier. But when they carry it on the moon, and you can actually, they actually record it, you can see the video online, on YouTube. When they drop the hammer and the feather, both of them actually fell at the same rate. So if you was to go up to the moon with a piece of paper and a rock, and you was to drop both of them, the same gravity is going to impact on both of them. And they won't have any air resistance, so actually both of them would fall at the same rate. So you can actually see it for yourself. It actually have experiments that recreate this hammer feather thing with inside a big vacuum chamber on Earth. So in a vacuum where air resistance is absent, all objects accelerate at the same rate, right? So like if it still have a gravitational force, of course. So it don't matter if it was if it's a car, or if it's a bowling ball, or if it's a feather, or if it's a coin, or it's a spoon mobile. If you drop anything, it's a piece of paper, a little piece of dust, all of it, once there's no air, would fall at the same rate. So, the gravitational constant G, right? I mean, we come into things that kind of normal, but I guess we'll be going into this but we have to do after hydrostatics. So the gravitational constant, let me use it as 10, right? 10 meters per second squared. So what this basically means is that every second that passes, the speed of a fallen object, not counting air resistance and air resistive forces, is going to increase by 10 meters per second. So basically what this means is that, so if we come here, and let me say we used to drop something, after 1 second of falling, it will reach 10 meters per second. After 2 seconds of falling, it reached 20 meters per second. After 3 seconds of falling, this is if you have a constant gravitational force acting on it. So basically, what 10 meters per second squared means is that you get plus 10 meters per second every second that gravitational force is acting on it. So this is, so of course on Earth you have air resistance and all kind of thing. You have air resistance, you have all kind of wind blowing resistive forces. But if you was to take away all that and just have gravity, it just means that the velocity is gonna increase by 10 every second that passes. So if they, in a lot of examples, they say discount air resistance. So if they say, this, right? Coconut falls from a tree from rest. After 2.2 seconds, it hits the ground. At what velocity did it hit the ground? And they will actually give it a mass. They will say that this coconut is 2 kilograms. That's kind of heavy coconut, but at what velocity and momentum? Right. So I'll talk about terminal velocity just now. So if you were to use this example here, we would say this. Right, so remember, acceleration. Although I don't think you will get a problem like this, but just saying, is change in velocity over time. Therefore, the change in velocity, which is v minus u, right, by the diameters, that will be acceleration by time. And remember, g, let me say g is 10 meters per second squared. So that's going to be 10 times the time, which is 2.2. So this velocity at which I hit the ground was 22 meters per second, right? And the momentum is going to P equals to mv right? So the momentum that it would have experienced upon hitting the ground would be 2, that's the mass, times 2.2, and not 2.2, sorry, 22. That's this here. And that'll be 44 kilograms meters per second. And so you never know if a question like that could come, because I say all of that is actually part of forces and momentum. But it kind of with motion, but you know CXC, they could bring all kind of thing. So coming back here now, Ariel, sorry for the cat boy. That I hope your cat come back. In all honesty, right? So let me explain here. Somebody asked about terminal velocity, right? And this kind of falls in between motion and forces, but basically it's forces relate to motion. So if you look at this diagram here, and we used to imagine you're on a plane, jump out the plane. Of course, there's a parachuter, jump off the plane, you have your parachute pack. What's gonna happen at first is the net force is gonna be downwards. The net force is gonna be downwards, and this is gonna cause the person to accelerate as they fall, because the net force is in the direction that they go in. So of course they don't want to hit the ground flatten like a pancake. So what you do is you pull your parachute, and you'll see now that the upward force, there's the air resistance, this is gravity. The upward force is now bigger than the downward force. The downward force in this case is pretty much constant because it relates to gravity. So what happens here now is that the net force is going to be up. So what happens when the person pulls the parachute? Do they go up? No. The person is still falling down, but the person now is going to decelerate. Now eventually what's going to happen is a lot of air is going to get caught in the parachute here, and eventually what's going to happen is their falling speed, sorry, their gravitational force is going to be equal to the air resistance. So what happens here, where both forces are equal? Well, what happens there? Does the person stop in midair? Nah. The person stops decelerating. No force, no change. Well, remember that. No force, no change. They stop decelerating. They stop accelerating. They stop changing in any type of velocity. So this is why it's called terminal velocity, because at this point the velocity it plateaus. But that's getting more into motion and dynamics and things. So I ain't gonna get too much into that. Finally, when the person falls, right? So let me say now, the person falls. There's a person here, a little stick man. This person falls and the person stands up on the ground. Well, the person has their weight pressing down here. This will be the weight. And well, gravity is of course impacting weight, right? If this was the only vector that was acting on this person, if this was the only force, this person here would fall right through the ground, plucks, right? So that's now going on. What happens here is that we have an action force and a reaction force. They balance out. So this is where we're going to get the ground is going to impart a reaction force in order to keep them up. Oh, shucks. Sorry about that. Now, right? So I was saying before, all I really missed nothing. I was talking about the diagram itself. It's only now I start to draw. So if this only had weight here, this man four plucks, plow right through the ground. But you're gonna have, as I say, a reaction force that's equal and opposite to gravity that's holding them up. So in the case here, these forces are going to be balanced. Nah, man, I was saying mark the thing because the diagram it is there. But anyway, so Newton's third law, and this is something that could potentially come to because this is the one that shows up the most. Newton's third law says that for every action force, there's an equal and opposite reaction force. You could also say it like this: if body A acts on body B will exert an equal and opposite force on body A. That's not like something I make up. If the thing act on the thing, the next thing going to impart an opposite thing on the thing. No sleep, boy. No sleep. No sleep. Where the no sleep there? No sleep. I can't find it. No sleep tonight. No sleep. No sleep. No sleep. No sleep. Time to stress. Time to chill out. Real thing. So sometimes I ask you to draw a diagram involving Newton's third law. Most typical diagram is either of a rocket or an airplane. So this is the typical diagram you want to draw. And I'm trying to get the one with the four forces on it. Look at right here, man. Right? So sometimes let us ask, hey, like I really need sleep there, right? So sometimes let's ask, draw a diagram depicting a vehicle or an object in relation to Newton's third law. Sometimes they would say label the forces and so on. Or sometimes they could say plane flying horizontally. So these are the four forces you wanna talk about here: the thrust, the drag, the lift, and the weight. Right? When these four forces here are balanced, this plane is gonna fly forward at a constant velocity. Now, if you just want to draw it like this, all right, give me a second here. Let me say that we have a missile. So I'll come to this here. Or even a rocket, you could use as an example. Lift is caused by the it is caused by a combination of the thrusters in the back, the reaction force from the thrusters, and the wings. The wings acting the opposite force to air resistance, basically. Opposite force to drag. So this is a simpler one you could draw here. And I'll just find it. Good thing only getting moments, but that might be a kind of them moments questions. Some of them just come like alright, some of them just come like real trouble. When I did write CXC, right? Did I bring this moments question? Boy, this moments question had like 8 forces in it, boy. CXC was hard back then. And this them really want to song and solve this thing, you know. The thing have the middle plank, the middle some piece of wood, the thing to lift it, all kind of thing. I was like, nah, man. If it just had a collective sigh in the room when this when they bring this thing, that was horrible. Why I write CXC? If you could find the question where it have like 8, if it have like 8 things in that principle of moments question, you could probably figure it out. Anyway, so if you're using a rocket as an example, action is from the thrusters going backwards, reaction going forwards. So the even when you walk in, think about when you're walking. When you're walking, you are actually pushing back on the ground a little bit to push yourself forward. If you're swimming, you're pushing the water backwards to push yourself forward. Yeah, I get one. I didn't get what elitist this is a distinction because that don't exist, eh? That don't exist, eh? But I get one. Anyway. So and that's pretty much it for forces, and unless I miss anything. So I think that's the last things we have to do. And when I ask things about forces, the most it is asked about is to label, like to do a table, name the forces, define what is a force. A force is a push or a pull that can overcome inertia, right? A force is a quantity that can overcome inertia. Now, time what else it have? Because this is pretty much it for forces. What else we have to go through? If it had a curve, that curve saved me, but it had no curve. I think I just do good. I don't know how I get catch up with this curve thing, you know. It have absolutely no proof. It have a curve. It had none. Somebody just make that up a day and start saying it have a curve, it have a curve. Since I was in school, them saying it have a curve. I sure since my father was in school, them saying it have a curve. Table with forces and descriptions of the forces and examples of the forces. Like if you say centripetal force, you could use a washing machine. Alright, hydrostatics. Alright, so hydrostatics, that's like Archimedes' principle and thing. Alright. Okay. Alright, so let me give an example here. Of a question. Alright, so I'm come back here. Alright, so first, when talking about density, we know density is rho is m over v, right? And the definition of density is pretty easy. Density is literally the formula. Density is mass per unit volume, right? And of course, the unit for it is kilograms per meters cube. But you could also, if they have the units as grams per cm cube, and I didn't say anything about converting it, you should be okay. I never really see anything where they say to convert it. So using like basic examples here, right? Let me say that we have let's see what's the density of gasoline. All right. So let me put a question here for you, and we go solve this like just to give an example of this. Shucks. That's not right. Okay, let me say that oil. Let me say oil has a density of 800 kilograms per meters cube, right? What volume, what mass of oil, sorry, meters cube, would occupy a volume of, let me say, 5 meters cube, right? What we want to do is transpose this formula. So all you know, you could use the triangle if all you're bad at maths, right? So you could use this. I can use this with any formula that is in this format here. So you can say rho is m over v. And what you're asking for, they're asking for mass, right? So you cross off the m, and your formula is going to be mass is density by volume. Sure. So therefore, rho is m over v, so m is equal to rho v. That's going to be equal to 800 times 5, and that there is going to give you 4,000 kilograms, right? Basic calculation there. But what could also be involved with density is when we have pressure in the mix, right? So let me say that we have this example here. Let me say that we have this question. So let me paste a question here. Right. So you say we have this question. A fluid has a depth of 8 meters. The pressure of the fluid is given as, let me say, 4 kilopascals. What is the density of the fluid? So this looks like, okay, they say G is equal to 10 newtons per kilogram or 10 meters per second squared. So this here looks like something that, could be a little difficult. But this is the other formula here involved in hydrostatics, where we say the change in pressure, or you could just say pressure, is equal to rho G delta H, right? Delta H being the change in depth or change in height. It's kind of like gravitational potential. It's like the formula is similar to that. So you all could work it out as we go into. So what would be the density of the fluid? So that would be rho. So if all you remember was, say, how you could treat this. This is a house, and this is a house, Rose staying home, and everybody else going next door, but they're going downstairs. Right? They're going downstairs. So how this will be done is like this. We're going to say row staying home, right? So row is going to be equal to pressure over GH or G delta H. I'll just put in it so it don't look too difficult. So the pressure is 4 kilopascals. So that is 4,000 pascals. G is 10 times, and the height is 8. So basically 4,000 over 80, and that would be the density of this would be 50 kilograms per meter cubed. So this is basically what hydrostatics is like pressure in liquids and things like that. So the formulas that you want to remember when it comes to this is there's 3 formulas for the pressure, right? No, we're gonna go through Archimedes' principle just now. So our rho is m over v, p is rho gh, and then p is F over A. Right? Pressure is force over area. So these 3 formulas here are involved with fluid pressure, density, and so on. Now, I'll come to Archimedes' principle in a little time. But let me show you one more question here. Let me say that we have a pond, right? Yeah, that there. Let's see, make sure I take a seat. And this is some water. And they say we have a point here P, and this is 10 meters deep. Right? 10 meters deep. So they say the density of water is 1,000 kilograms per meters cubed, and we have atmospheric pressure, which is just from the atmosphere as the pressure of the atmosphere pressing down at that point. Atmospheric pressure is 101 kilopascals. The question here is calculate the total pressure acting on point P. So we have 2 different pressures acting here. We have the pressure of the water, right? So we have the pressure of the water, and we have the pressure of the atmosphere. So the first thing we're going to do is calculate the pressure of the water. We're starting out them thing boy. Them butts and them calm. So this will be rho hg. So I can work it out too as we go in. So this is just the water. So this will be 1,000 by 10, and the depth is 10. So this is easy. This would be 100,000 pascals or 100 kilopascals. The total pressure, on the other hand, is going to be the pressure of the water, but you also have to add the atmosphere. Now remember, for some of these gas law questions, sometimes you have to add the atmosphere too. Plus, the atmosphere is 101 kilopascals, which is 101,000 pascals. So the total pressure here is going to be 201,000 pascals or 201 kilopascals. So these types of questions not particularly hard, but I have one here that I think is notable to look at. So let me find it here in terms of the past papers. I think is Jan 2013. Just let me see if I could find this thing, because I know this was a kind of bust up scenes. Alright. So let me work out a question here together. Alright. So there's a question here. Let's see how well this is showing. Figure 3 shows a scuba diver ascending from 20 meters below the surface, where the water temperature is 10 degrees Celsius to the surface, so the temperature is 10 degrees Celsius on the surface. No. Below here is 10 degrees Celsius, and at the surface is 25 degrees Celsius. And the pressure up here is 101 times 10 to the power 5 pascals. Right? So the question here is now, so there's the question. Wait, let me make sure everything's showing good. Calculate the pressure the diver is subjected to at 20 meters below the water surface. That's the first part. So I do it here, and then I will go through it too as we go in. And then they say using the general gas law, calculate the final to initial volume ratio of a bubble rising to the surface. Okay, so this how we're doing it here. I want to make sure everything fits in here. Make sure everything fits in this little tricky spot here. So the first part here, calculate the pressure the diver is subjected to at 10 meters, 20 meters below the surface, right? And sorry, I forgot to give the... Did they give that? Yeah, they give the density of the water as 1025 and G is 10. Sorry about that. So I'm gonna go through it here. We have a diver, he go on below. I don't know what that sound was, but he go on below. And below here the temperature is 10 degrees Celsius. On top here the temperature is 25 degrees Celsius. The diver is 20 meters below. Right? So the diver 20 meters below. What is the pressure he's subjected to down there? Okay, so we're going to use the formula. Pressure is density by gravity by height. And remember, this would be for the water pressure, right? This would be the pressure from the water. So to work this out, we're going to say the density is 1025. The gravity is 10. And the depth, H is depth, is 20. Worked out. And that's going to give you 205 thousand pascals. Now remember, that's just from the water. So the total pressure is going to be 205,000 plus 101,000. And that's going to give you 306,000 pascals. So instead, I'm going to put this as TJ just say he get through real good. I'm going to put this as 306 kilopascals just to make the number a little smaller now, just to make it a little, now. So that's 101 kilopascals. Now, the question now is, using the general gas law, that's the combined gas law, calculate the final to initial volume ratio of a bubble rising to the surface. So, all you remember now, whenever we do anything with gas laws, the thing had these Celsius values had to convert to Kelvin. So if you remember how to do that, easy. You just had to say 273 plus them values. So 273 plus 25. That'll give you 298 Kelvin here. And this will be 273 plus 10. And that give you 283 Kelvin here. So remember down here, this is the initial because the bubble is rising. And up here is the final. So right now we have the initial temperature, which is 283, the final temperature, which is 298, the initial pressure, which is what we just calculated, 306 kilopascals, and the final pressure, which is 101 kilopascals. Right? I'm give all you just a little while to look at it. See if you can calculate that second part there. I'll go through it just now. So using the general gas law to work that out. So I'm gonna give all you a little help here. This here is T1, right? This here is P1. This here is T2. And this here is P2. Alright, so let me work it out here. These are real hard questions, so hopefully the stream stay up and all they could just all they could go over it at any point. So using the general gas law, we're gonna say P1 V1 over T1 is equal to P2 V2 over T2. Right? So P1 is going to be 306 times V1, because you don't know what's V, over T1, which is 283. It's going to be 101 times V2. And over T2, that's going to be 298. So when you multiply these three here, 306 V1 times 298, 283, 101 V2, when you transpose, right? So when you write down the formula and rearrange everything, V2 is going to be equal to P1 times T2 Right, so I know all you get confused with this, but I expect all you to get now. Hopefully the streams stay up and all you go get through with it. So P1, the space what I have here, yes? Take a screenshot. All you take a screenshot. All you go figure it out. Because I feel all you in the mood right now to go through this. Take a screenshot. Take a screenshot of the answer there. And the year is this. I feel all you in the mood for this one. This is June. Is June? No, it's Jan. This is Jan 2013. And this is question. I go link it after. I go link up all the thing after. Hey, if this come and all you do it, who knows? That is question 3. Take a screenshot. Olivia's time to don't know. This hydrostatics thing is this will slow down the thing, boy. Is this how the brain could work? Pressure bus. Pressure. Reach pressure. Pressure bus. Pressure. Take a screenshot. Pressure. Yeah, well, take a little break. Take a 10 minutes. Take a 10 minutes.
As the adage says, you give a poor man a fish and you feed him for a day. You teach him to fish, you give him no. Let me give all you a rundown here
of, let me give all you a run. I do nuclear energy and thing already. I do that already. We on a kind of break. We on a kind of break. Well, let me give all you a rundown here. What I think coming. What I think coming really matter. Well, Q1 obviously going to be radioactive decay, right? Curve. You determine half-life by using two pairs of values. And then you might have to define half-life. And then they might ask us like some basic things like pros and cons of nuclear energy. We went through that already, or they could look early in the stream where they do that. Pros and cons, fission versus fusion, definitions, advantages, things like that. And remember this 25 marks, so the other things that could get thrown in here is safety, safety hazards or safety precautions. And those are the things I think coming. But the other things is we still on the break. We still on the break weapon. We are doing no work. Calculation of nuclear energy. So there's a big question. I think things like radioactive decay equations, those things don't fall under nuclear energy. And those things don't fall under half-life. Well, they can check that and just make sure, but I don't think those things fall under that. Radioactive decay equations and Geiger-Maslin experiment. Was it are the types of radiation? I don't think those things fall under half-life and things like that. Or they could double check it and make sure. Q2. I think what they'll have is like to define force. Name types of forces. Give examples. I think what they'll have is Newton's third law. Diagram, label. And it might have like a small momentum question. That's what I think. I don't know how much each would be worth. But this is just from observing what come in January and what come in the previous years. So if you look back to 2016, 2015 and thing, you could get a general idea what might come. Question 3 and 4. You might get something with, I can't tell which one is which, but you might get something with Archimedes' principle, density, definition and calculation, relative density, something to do with pressure. Pressure as in the rho GH formula. You know they have this one with the hydraulic brake, not the brakes, the hydraulic lift and thing. You might get something with that manometer. And then you might get, what's the other thing? I'm missing right. Gas law is the reason why I give all that diver question is actually mixed hydrostatics with gas laws. So I'm going to link all the solutions and all the papers and thing after. Well, I'll put it in a pinned comment when the stream done. But gas laws, thermometers, upper lower fixed point. Oh shucks. And what's this other thing? The define Kelvin unit, the Kelvin unit itself. So Kelvin unit is like the pressure, the graph, the Charles law pressure law graph where it touches absolute zero. How to define that, or using P over T is equal to K to define the pressure law or something like that. So I think what they'll do is that they will mix gas laws with that type of Kelvin unit, type of temperature, type of question, or they might mix gas laws with that kind of hydrostatics question with the diver. Question 5. Well, I think question 5 will be draw convex versus concave lenses, define focal point, real versus virtual images, lens formula, magnification, the normal things you see with that, but that kind of came in January, so I don't know if, like, the lens formula thing came in January, so I don't think it will come in full again. I think what they'll more focus on is like the drawing aspect of it. I think they'll more focus on things like labeling, focal plane, principal acts. I just have a fever. I don't know, but it just seeming like they won't bring the same thing twice. And well, Q6 could be anything. Q6 could be because that electricity thing does cover real things. So Q6 could be, I think what it'll be is like a combined series and parallel circuit. A feeler has something with DC versus AC, primary versus secondary cells, something to do with a diode, and the uses of the formulas: P is equal to IV, E is equal to IVT. That's just what I feel. No refraction, not coming. That's what I feel. But this is just from pattern checking, like from looking back at papers 5 years ago, looking at what come in Jan last year, looking at what come in June last year. Sometimes it don't repeat, but sometimes it is repeat. Like if I was to actually make a spreadsheet of questions, have a pattern, but sometimes that pattern is broken because June 2015 and June 2016 they bring the same type of graph twice in a row, which is a half-life curve. But 2022 is 6 years after 2016, so it seems like it's the time for our next half-life now. But we know that from the broad topics, of course. Next year it might be a refractive index one. It really depends. It have a kind of pattern, but it's hard to tell when they break that pattern. Logic gates not coming. No, cells is not part of cells is not part of current electricity. Oh shucks, I forget about waves. Sorry, I forgot about waves. Waves might focus more on echoes and thing, I feel. Since they say waves and sound and I don't know. It just feeling like an echoes question. Cells and thing not in cells not under current electricity. No, I'm not going live tomorrow. We're finishing up this today. Cells not under current electricity. Hold on, let me get the syllabus day. Hold on. Let me open the syllabus. Let me open that syllabus day. Current electricity is are you going mad or what? Current electricity, conductors, insulators, electric current flow, electron flow and conventional current. Well, you know this whole branch here, current electricity, all this involved in it and alternating current, analyzing voltage time graphs, electrical quantity, this whole thing, everything that Mach 3 point something, conversion of electrical energy, V is E over Q, P is equal to IV, conserving, wait now, circuits not coming? This is who's up on this, Junior? Oh, they're all good, boy. Circuit diagrams come in. I read this thing wrong, boy. Circuit diagrams by itself. Circuit and components in broad topics or circuit diagrams? Oh shucks. Well, if it's circuit diagrams, then it's just a circuit. If it's you doesn't even know if CXC know their own thing, yes? So IV relationships and thing. Look. Let me finish up this thing. Oh, so I am no again, huh? I am no again. Alright, told you. Let me go through this half-life thing one more time and I feel that's it, we go done. Let me just do one more question with it. What going on there, boy? What about Jamaica? What happened? What happened with Jamaica? Something happened? Alright, let me see if they could try to work this out with me as we go in. Alright. Alright, that's now I have to switch back the thing. Alright. Let me say that to get a question like this, and the question is calculate the half-life of the radioactive decay curve. So, how are we doing this day? Now, as I say, you choose two pairs, right? Two pairs. Choose two independent pairs of values. So in the case here, if we pick one, so remember it could be any two numbers, any two pairs of numbers, sorry. So the first one I'm gonna pick here is going to be 180. So if I pick 180 as my first one, my second one had to be half of that. So my second one here had to be 90, right? Which is between 180, 180. So you draw a line coming down there, going across, this little thinner, going across, coming down, and for 90, same thing, going across, coming down. What's all this madness going on in chat there? So this is what you call T1, and this is going to be T2. So the value now for T1 going to be about this here, right? So T1, and remember the seconds, going to be about 9 seconds. T2 going to be around here, and this is going to be about, is between 30 and 40, let me say about 34. Right? So now we're going to type, we're going to write here, T a half is equal to, I could start at any, I just start at 180, you could start at any point once one is half of the next one. So this will be 34 minus 9. So this is the first thing for half-life here. 25 seconds. So you choose now a second pair of values. So I'm going to choose, I'll mark these in green. I'm going to choose 120. And half of that, which would be 60. So I won't use 240 because 240 kind of beyond the curve on the diagram there. So you use at least 2 pairs. The safe thing is to do 3, but typically if you do 2, you should be fine. This will come down there. Come across 60. So you touch the curve, this will come down there. So this is going to be called T3 and T4. So T3 is going to be somewhere between 20 and 30. We'll say this look like 25. When all you actually draw the graph, all you'll be able to tell a little better. Right, so you see here, there's our 25. And this one here is somewhere between 50 and 60. It looks like about 52. So this is the second set of values for half-life. So this is T4 minus T3. So this is going to be 52 minus 25. And that's going to be I feel like my head stopped working. I use calculator now to do anything. So now what we have to do is do an average of these two values. It could be any two numbers. Once one is half of the next number. So the average here could be 25 plus 27 divided by 2. And of course, that's 26 seconds. It's easy. That's how you do your half-life. And I feel like doing no radioactive decay equation question now, nah? I feel like born. So I feel we're good to go there. I go upload all this stuff. Or they go fix all the mix tomorrow, man. So let me end it there. Let me end it one more time from we sponsor. Speaking of skills, let me take a few minutes to talk to you about a website called Skillshare. Have you ever wanted to try to learn something out of the ordinary, something interesting? Well, you can. Just take a few classes online at Skillshare.com. It's better than lessons.
You want me to show you tough? I'll show you tough.
We're taught by instructors and have their own class rosters. Hell, I learned how to juggle and make a peanut butter and jelly sandwich the right way using Skillshare. What are you waiting for?
I never lose.
It had dozens of online courses that you could take, ranging from physics all the way to finger painting, all the way to starting your own YouTube lesson channel. Come now, man. Skillshare. Oh yeah. Well, I feel like, no, it's not 10, but I feel I good. Well, they're going to take a rest because tomorrow is real studying. Alright, all you spooling out. Take care.